Hello.
Hello.
Hello, everyone. Alisa, when do we start?
There are still, good morning, dear Tom. There are still some participants in the waiting room, so we'll have a couple of minutes more, please. Can you hear me, Tom?
Yes, very well.
Okay. Good morning, everyone. Artyom, I think we can start now. In the meantime, me and Alice, we will be letting the participants in. Artyom?
Yes. Okay. So we I cannot show my screen.
Sorry. Uh, Now you can.
Perfect. Perfect. Okay. Good morning, everyone. I don't know if everyone is in the same time zone, if it's morning for everyone or already afternoon for a number of people. I guess we have a number of participants from China who are there and for whom it's afternoon. So good morning, good afternoon, good night, wherever you are. This is now the 19th USPECH workshop. In the last 9 years, we have conducted 18, so now it's 19th workshop. And it's the first time we conduct a workshop online. I'm really grateful to Vladimir Baturin, who really took the main charge of organizing this workshop, and Alisa Isaeva, who really was a phenomenal helper in all this process. Okay, I also must say that this workshop is supported by our grant from Russian Science Foundation, to which we are very, very grateful. Okay, USPECH code, perhaps, well, since you are users or beginning users of the code, you know that USPECH code is available for free. All you need to do is register, and I hope that everyone who is listening to me has registered for this code and has already downloaded it. It's the code with the biggest number of users in this field of computational materials prediction. More than 7,000 registered users right now. It took a lot of effort from people in my group over the years, resulted in many, many publications. At some point, we just stopped counting how many publications have used USPECH, a lot. And it's also the code with the widest range of capabilities among all the available structure prediction codes. You can predict stable structure in 1 dimension, or in 3 dimensions, 2 dimensions, 1 dimension, 0 dimension. That means for crystals, for surfaces, 2-dimensional materials, grain boundaries, polymers, nanoparticles, molecules. You can predict both stable structure and composition. You can optimize physical properties, and you can optimize several physical properties at the same time using multi-objective optimization. And you can predict mechanisms of phase transitions to great level of detail using a hierarchy of different methods. Some of these capabilities of USPECH will be discussed in this workshop, but there are so many capabilities that we just cannot discuss everything. We will discuss the mainstream parts of the code. All right, so it's the most used and the most versatile code. Many of the capabilities are unique. In fact, many of the structure prediction codes that you see now in the market have originated from USPECH, usually illegally. But regardless, we are still and in the foreseeable future the most versatile and the most widely used and the fastest code available today. Okay, every year we hold on average 2 USPECH workshops. We have a mailing list. I suggest that you join it unless you have already joined. We only have a couple of emails per year related to things like workshops, major upgrades of the code, and so on. We have USPECH forum. Please visit the website of USPECH. There you will see a link to the forum. I suggest that all technical questions are asked first in the forum. Usually these questions will be answered by other users, if not by a member of my team. And it's useful that these questions and these answers are seen by everyone. We have a Facebook page. You can join it. Some information can be found there. And users in China who cannot access Facebook can use QQ group. I frankly do not know how active it is. I know the person who maintained it. Hope he still maintains it, but you can check. Probably this group is still active. And also, if you want, you can visit my laboratory. Every year we host about 10 scholars, usually from other countries, but also from Russia. You can visit my lab here in Moscow. USPECH, by the way, for those of you who do not speak Russian, this is the right pronunciation, USPECH. And in Russian, this means success. And the reason for this is that the code is very, very successful. Here is a list of some of the capabilities of our code. Its core is evolutionary optimization. The algorithm of evolutionary optimization is also called USPECH, but it also incorporates many other algorithms for crystal structure prediction and beyond. You can initialize structures, so produce the initial set of structures fully randomly, or using space group apparatus or topologies which are known to be popular in nature, or structures which you think for some reason are interesting to start with. So you can use fully random or partly random or completely non-random initial generation of structures. We have our ways of fingerprinting and many uses of it, and optimization can be done for the energy or properties, or both energy and properties, or several properties at the same time using the so-called Pareto optimization. I will briefly talk about it today. You can do completely unconstrained optimization, like you do not need to specify even the chemical composition of your material. It will be found automatically. But you may also fix the composition if you know it. The same you can do with lattice parameters. If you know them, you can fix them. Otherwise, you can do completely unconstrained calculation. For organic materials, it's very important to start with molecules and build the structure not from atoms, but from ready-made molecules. You can do it in USPECH. And you can also study different low-dimensional systems, as I already mentioned. And if you're interested not only in the stable states, but in metastable states as well, you can systematically harvest low-energy metastable states using our code. Our code is interfaced with other codes, ab initio or semi-classical codes. In total, 19 codes are interfaced with USPECH. You can find the list of these codes and the ways to specify them in USPECH manual. We use these codes for energy calculations, for structure relaxations, and in many cases for computation of the properties. And the machinery for optimization and analysis of data and structure generation is done in USPECH. Automatic generation of space groups, convenient visualization, data analysis, large manual, and abundant examples which show you how this code should really be used. This is all provided. We have a very large number of users, more than 7,000. I have not updated statistics for particular countries for a long time, so probably these numbers must be increased by 50% or so. But you can roughly see where the code is used most. America, China, European countries, growing number of users in India, Korea. Okay, and many different funding agencies have supported in one way or another the development of the code. When I worked in Switzerland, where it all started, we were supported by Swiss National Science Foundation. When I worked in America, it was American different funding agencies, national and private. And now that I'm in Russia, and in strong collaboration with China, all these countries and a number of private companies, as I said, have contributed to development of this code. And the people, the most important issue is the people. We have a very talented group of developers who have contributed or are still contributing to the development of our code. By the way, our workshops are named Ляхов Schools because for a few years, the chief developer of Uspech was my postdoc, Andrei Ляхов, a phenomenally talented person. He unfortunately died of heart infection at the age of 30. And I have decided to commemorate him, his life, and his achievement by calling our workshops Ляхов Schools. He was also the organizer of two workshops that we have conducted back in 2012. Okay, so let me start with the talk itself, describing the ways of performing computational materials discovery using our code. Okay, first of all, crystal structure, as you probably all know, otherwise you wouldn't be here, is the most important piece of information about a material. By the way, let me close the door because my parrot is singing. Oh, okay. My parrot is singing very loud. I hope it does not interfere with the lecture. Okay, as you know, crystal structure is the most important piece of information about a material. Once you know the crystal structure, you can understand why the material has these properties that it has. And you can even predict quantitatively the many properties of a material. Unsurprisingly, research in crystal structure determination based on experimental methods has played a central role in the science of 20th century. This story has slightly more than 100 years of history. For the first time, crystal structures were determined in 1912. The first publications were in 1913 by father and son Braggs. And just a couple of years later, they received a Nobel Prize in Physics, one of the most deserved Nobel Prizes in history. And William Lawrence Bragg was the youngest Nobel laureate in natural sciences up to this day. So this glorious history really transformed the science of the 20th century. And I would say that crystal structure determination was one of perhaps 3 or 4 greatest breakthroughs of the science of the 20th century, together with quantum mechanics and relativity theory. And perhaps one could also put the solution of the structure of the DNA as another greatest discovery. However, determination of the structure of DNA was done using methods of crystallography developed by Braggs. Okay, in fact, at least 26 Nobel Prize winning works were done using this methodology developed by Braggs. and these are listed here. Okay, crystal structure prediction. If you are interested, you can read, for example, this review or other reviews that I have written over the years. The latest ones are a review written solely by me and a review written by my biggest competitors from Cambridge. So me and Chang Zhu, who will be a lecturer here as well, my former PhD student and postdoc and now professor in America. So we and our competitors wrote this review with the aim of providing the community a balanced view of our field. And also a couple of books that you can consult are listed here. Okay, crystal structure prediction does not have such an old history as experimental crystal structure determination. For the first time, we became confident in predicting crystal structures was, I hope I am not too immodest, when USPECH method was formulated. That was in 2005, and the first publications were from 2006. Before then, crystal structures were considered to be fundamentally unpredictable. You can see articles like this. Are crystal structures predictable? Question mark. That's the title of the paper. The first word is no. The main reason why people were so pessimistic is in the unfavorable combinatorics. If you want to predict the stable crystal structure, that is this arrangement of atoms with which gives the lowest possible energy, you could, in principle, sample all possible arrangements of atoms in space, compute their energies, and find the one with the lowest energy. However, the number of structures as a function of number of atoms in the unit cell is astronomically large. For a system with, let's say, 30 atoms, it's not a lot. In the unit cell, the number of possible structures is so large that it will take you longer than the lifetime of the universe to sample all these structures. Clearly, this cannot be done on an enumerative basis, trying all possible combinations of atomic positions. However, this can be solved if you take smarter algorithms, such as evolutionary algorithms that we have developed. Shortly after first publications of our works, our Indian colleagues wrote about our approach that it's not only evolutionary, but also revolutionary. And well, now this code is widely used. The strength of our approach comes from the combination of our carefully designed evolutionary algorithm for global optimization and quantum mechanical calculations. We do not incorporate empirical knowledge. We do not incorporate human bias. General purpose evolutionary algorithm for crystal structure prediction and fundamental laws of quantum mechanics can predict for you crystal structures which may contradict your intuition, as I will show later, but which are true, and discover new chemistry, new materials for you. This is the power. You can predict structures which have no analogs in databases, so you cannot predict it by any kind of empirical approach. And the structures often will surprise you. Okay, if we imagine this problem of global optimization, that is finding the lowest possible energy for an ensemble of atoms, this is equivalent to finding the lowest point on the energy landscape. This energy landscape will have many minima. And this landscape will be not a two-dimensional landscape as I showed. This is just a projection of the energy landscape of real gold palladium alloy. But this will be a multi-dimensional energy landscape. Crystal structures are described by many variables, let's say of the order of 100. So this will be a 100-dimensional or so landscape. And our goal is to find the lowest point on this landscape. Evolutionary algorithm, by their philosophy, by their design, what they do is they zoom in on the most promising region of the search space. So they start with broad, unbiased sampling, but very sparse sampling of the whole landscape. Then they discover where the lowest energies are, and more densely sample this part of the search space. Okay, we have random or not fully random, depending on how the user specifies initialization. The initial structures have to be relaxed. By the way, all structures that we produce must be relaxed. Then you rank these structures by the value of their relaxed energy. Those structures which are not sufficiently stable are discarded, and the lower energy part of your population is used for producing children. And the children are produced using the so-called variation operators. Heredity or crossover is a variation operator producing one child from two parents. What we do, we cut slices shown here and here from the two parent structures and put these slices together, also using periodic boundary conditions. And then we relax the child structure and we obtain something like this. We use also different kinds of mutations. Mutation is a recipe of producing one child structure from one parent. In mutation, we select a small number of variables describing the structure and greatly perturb these variables. We do not perturb everything. We select a small number of variables, such as lattice vectors, or such as shifting all the atoms along directions of softest vibrational modes, or swapping unlike atoms in order to find a different ordering of atoms on a predefined lattice. If you have variable composition systems, then you have to do transmutation. That is a non-conservative change of atomic identity. You had lead here, you switch it to gold, and the chemical composition of your material changes. If you have molecules, you have to take into account that the molecules from which you build the structure are not point particles, not material points, and they have shape, they have size, and therefore you have to do, for example, rotational mutation and translational mutation of these molecules as well. Let me see, I never showed movies on Zoom, but let me see if it will work here for you. Yeah, do you see a movie?
Yeah.
Okay, so let me show it again. So this is how USPEC calculations work in practice. We start with, in this run, with fully random structures of carbon, aiming to predict the stable structure of carbon at high pressure of 1 million atmospheres. We start with random structures. They are nothing special. And from these random structures, more and more stable structures are produced until we find quite quickly the structure of diamond. You see that a very complex problem of global optimization actually turned out to be very simple. Of course, diamond is a very simple example. We can do much, much more complicated things. For example, quite a complicated structure of boron was discovered. It was synthesized in the experiment. It turned out to be super hard and turned out to possess quite unusual chemical bonding, where a subset of boron atoms attracted electrons from the other boron sites. So you have positive charges and negative charges of the same atom in the same structure. The same year, we published also in Nature another, even more surprising finding, that sodium, which we used to call an alkali metal, under pressure is not a metal anymore. At pressures of less than 2 million atmospheres, sodium was predicted and experimentally confirmed. Here you see the experimental sample to be a transparent insulator. Here you see it transmits orange light. And electrons are no longer smeared over the whole crystal structure. Electrons are now concentrated in rather small pockets in the interstitial space. These electronic concentrations are shown by orange clouds. They are in the cavities of the structure. and each of such localizations contains exactly an electron pair. We call such materials electrides, materials where strong electronic localizations in the interstitial space play the role of anions in the crystal structure. Such materials are known, but the simplest one is our transparent sodium. You can greatly speed up crystal structure prediction using machine learning. Here in this workshop, we will have a lecture and a tutorial by Alexander Shapeev, who is a very bright young professor from Skoltech, from our institute. Together, we wrote a paper, which already has become a highly cited paper, about using machine learning for speeding up crystal structure prediction. You can see a very complicated case of boron allotropes. Boron has many crystalline modifications, usually with very complicated crystal structures. For the simplest crystal structures, the speed up was 100 times. For the most complicated crystal structure of beta boron, which contains more than 100 atoms in the unit cell, the speed up was more than 10,000 times. You can see how complicated this structure is. In fact, beta boron is disordered, which means that it has many nearly degenerate, very similar variations of this crystal structure. And we found a number of such versions of this disordered structure. The record for USPECH is 152 atom structure. This is lithium silicide, which was synthesized, which is actually a known compound, and under pressure it was found to transform into an unknown crystal structure. We determined this crystal structure and it beautifully matched the X-ray diffraction spectrum of the experimentalists. Okay, we can also work with organic things. For example, Chang Zhu was able to find a new third polymorph of resorcinol, a simple molecule which was known to form only two polymorphs. Several years ago was found experimentally to form a new third polymorph, the structure of which could not be found by experiment. Experimentalists could not solve the powder diffraction data. We, or actually Chang Zhu, have been able to find the structure using USPECH, and it matched beautifully the experimental X-ray diffraction data. You can work with polymers as well. For example, tests show excellent performance on tests such as nylon 6 or cellulose. Also, this has been used for predicting actual new materials, polymers with high dielectric constants to be used in flexible capacitors. We predicted several new polymers with high dielectric constants, with record high dielectric properties, I should say, and these polymers were synthesized. The crystal structure and physical properties were confirmed in the same work. You can consult this paper. Okay, we are also playing with predicted structures of proteins. And for simple proteins, at least, this works very, very well. You can see how accurately we predict the structure of this small protein or large polypeptide, hignalin. Larger protein, TRPKG, is also predicted quite beautifully in comparison with experiment. We keep developing our method. Last year, we published a very, very important methodological development where the initial structures are produced not fully randomly and not using randomly picked space groups, but using topological types. It is known that the majority of inorganic crystal structures belong to just a small set of crystal structure topologies. About 2,000, just 2,000 topologies are responsible for about 75% of inorganic crystal structures. We decided to go in the inverse way. If you take, okay, let me explain you how these topological types are obtained. Imagine a crystal structure. Remove all one coordinate and all two coordinate atoms. Two coordinate atoms will be now represented as an edge. One coordinate atoms are fully removed. In this simplified structure, you have to color all atoms as if they were identical atoms. So you lose distinction between different atoms. And then you transform the resulting structure to its highest symmetric version. This is called a topological type or ideal net. In our code, we use the following philosophy. We take an ideal net, we color its nodes to produce different atoms, and we color them not randomly, but using highest subgroups of the given space group. And if needed, for chemical reasons, we can add also two coordinate and one coordinate atoms. Using this approach, you can recover the majority of known crystal structures and generate an infinite number of new hypothetical and low energy structures usually because we have learned something that nature wants. We use what nature likes in this generation of crystal structures using topological types. Here is a comparison. Here is a comparison of the energies that you obtain using topological random generator. You can see that a very large number of low energy structures are obtained, and structures which you obtain using randomly picked space groups. This way is also fully theoretical. You can generate an infinite number of structures using this way as well. But the distribution is shifted to higher energies. The use of random topological structure generator is a big step forward, and it allows you to reduce computing costs by about 3 times, according to the tests that we have conducted. Okay, I hope I have shown you that we can predict structures given the chemical composition. Now I will show you how we can predict the chemical composition without knowing it. All you need to do is to know which elements you want. So you specify elements A and B, and Uspech will be able to predict stable chemical compositions. This is done using the so-called Maxwell construction or convex hull construction, which was invented by James Clerk Maxwell something like 160 years ago in his famous works on thermodynamics. You have to plot the data on different compounds in the following coordinate space. In the x-axis, you plot the chemical composition, percentage of A and B. And A and B could be atoms or could be molecules, depending on what are the boundary conditions of your problem. And on the y-axis, you put the enthalpy of formation or free energy of formation of all the different compounds formed by A and B, hypothetical compounds formed by A and B. And importantly, you have to normalize it per atom or per molecule, again, depending on the formulation of your problem. Okay, let's say per atom. All the different compounds that you have will have different energies of formation from the elements. If the energy of formation from the elements is positive, then these compounds will spontaneously decompose into the elements. Therefore, they are unstable. If the energy of formation is negative, they are more stable than the mechanical mixture of the elements, but it does not mean that they are stable relative to other compounds. The only compounds which are stable, thermodynamically stable in this system, are AB and AB4. You will see that these compounds are below any line joining any compounds that we have found. Therefore, they should spontaneously form from any relevant mechanical mixture or any relevant starting composition. Depending on the starting composition, you will have different stable states. The energies of the stable states are given by these broken straight lines by this convex hull. If you start with, let's say, this composition, 25%, the stable state will be here on this straight line, and it will be a mechanical mixture of A and AB. If your starting composition is exactly AB, your stable state will be AB itself. If your starting state is here, the stable state will be a mechanical mixture of AB and AB4, and so on. Okay, the convex hull construction allows us to find in the multi-component system what are the stable states. In this case, it's A, AB, AB4, and B. These stable states will never decompose into any other compounds. And it also gives us a measure of instability. The height above the convex hull is a measure of instability. This is a quantity that we want to minimize in our calculations. You can define convex hull construction in the binary system, in the ternary three-component system, or in any system as complex as you like. Okay. This method, the variable composition prediction of stable compounds, allows us to achieve really great results. For example, you can ask a question: sodium chloride. Any chemist knows that sodium chloride can have only one composition, NaCl. But what will happen if you change conditions, pressure, temperature, and so on? Will you be able to stabilize other chemical compositions? We know that chemistry of the elements is very different at high pressures. So I have shown you that sodium becomes a transparent nonmetal, for example. Will this have any consequences for stable chemical compositions? So we ran the calculations. Here are the results. Along the horizontal axis is pressure, along the vertical axis are chemical compositions. Chemical compositions and their stability ranges in terms of pressure. You can see that NaCl is stable throughout this large pressure range. So it's from 0 to about 3 million atmospheres. At all pressures, NaCl is stable. So nothing will happen to it. But remember that other compounds can be stable as well. We know a number of stable iron oxides or nitrogen oxides and so on and so forth, hydrocarbons. So several stable compounds can exist. At normal conditions, only NaCl. But as you increase pressure, NaCl3 becomes stable, Na3Cl, Na2Cl, Na3Cl2, Na4Cl3, and NaCl7 in these corresponding pressure ranges. Most of these compounds are metallic. So just think about it, that under pressure you form NaCl7, which is metallic. This is completely against rules of classical chemistry. But this is not surprising at all, because rules of classical chemistry were formulated as a generalization of experimental data at zero pressure, at atmospheric pressure, which is very close to zero. And as you change conditions, of course, you will get different chemical behavior from what we are used to. And these compounds are predicted by quantum mechanics and found by experiment. Experimentalists attempted to synthesize NaCl3 and Na3Cl. In both cases, they were successful. They observed a chemical reaction, and they observed X-ray diffraction peaks, fully matching our predictions. Okay. If sodium chloride system can do such things, then you can find such unusual chemical compounds in pretty much any chemical system. Oh, by the way, perhaps I should say how to obtain these new chemical compounds. As you see, NaCl is stable throughout the pressure range, so it will not decompose in this particular case, but it will react with sodium, forming Na3Cl or Na2Cl and other compounds, or it will react with chlorine, forming NaCl3 and NaCl7 at the corresponding pressure ranges. Okay, so this is how these compounds were synthesized. Another very surprising illustration of the power of USPEC is the prediction of compounds of helium. Helium was thought to be the most inert element in the periodic table. It was considered to be extremely difficult to make it react with anything. You can form extremely unstable molecules, and that's about it at normal conditions. But at high pressure, at pressures of about 1 million atmospheres, we predicted that helium will form a very stable compound with sodium. This compound, Na2He, is stable from about 1 million atmospheres to at least 10 million atmospheres. Helium was predicted to react not only with sodium, but also with sodium oxide, forming Na2HeO compound, also with calcium fluoride, magnesium fluoride, and a number of other compounds. Na2He, which we have predicted, by the way, is an electride. You can see strong electron localization in the cavities of the structure shown by these red regions. And this compound has been synthesized. You can see X-ray diffraction spots from the single crystal of sodium helium compound. Helium is the second most abundant element in the universe. About 24% of all the atoms by mass is helium. So it's a very, very important element. And we have just learned something fundamentally new about its chemistry. Okay, but probably the most interesting and the most important story is the story of high temperature superconductivity. In 2014, a group of Professor Tsui, they are users of USPEC, and using USPEC, they have predicted that hydrogen sulfide, H2S, under pressure is unstable. And a very unusual, unexpected compound, H3S, becomes stable. Well, they were shocked by this finding, and they tried to write down the formula as a combination of known molecules, H2S and H2. But in the structure, you do not find any molecules. It's better to write the formula as H3S. And they predicted that H3S should be an extremely high temperature superconductor. Before then, the record was 135, 138 Kelvin, rising to about 166 Kelvin under pressure for complex mercury cuprate. And here they come and they predict H3S with conventional electron phonon type superconductivity to be superconductor at much higher temperatures. This record was confirmed 1 year later in the experiment by Drozdov and others. And this was published in Nature. Experimental temperature of superconductivity was 203 Kelvin. This was done by USPEC and confirmed by experiment. And this really started an avalanche of works, theoretical and experimental. This record was soon afterwards broken. Lanthanum H10 is now known as a superconductor with TC of about 250, 260 Kelvin. Two different groups, one published 250 Kelvin, the other published 260 Kelvin. There is absolutely no doubt that this is true. This was confirmed by two different groups. And again, lanthanum H10 is a highly unusual compound, contradicting rules of classical chemistry. A couple of weeks ago, even that record was broken when experimentalists made a sulfur carbon hydrogen compound superconducting essentially at room temperature, 288 Kelvin, at extremely high pressure of nearly 3 million atmospheres. But now room temperature superconductivity is basically a reality. People were dreaming about it for more than a century, and this dream finally came true. However, so far only at very high pressure. It's interesting that this compound, of course, it was inspired by theoretical works and experimental works following from them. But this was actually a compound which we still are struggling to understand. Neither the exact chemical composition nor the crystal structure of this compound are known. All we have is experimental measurements of superconductivity, published in Nature, believable, but the nature of this compound right now is unknown. Okay. Superconductivity seems to be, of these hydrides at least, seems to be strongly linked with the periodic table. My PhD student, Dmitry Semenok, a very talented young scientist, has plotted the temperature of superconductivity of all the hydrides in binary hydrides in the form of Mendeleev's table. For each element, he plotted the highest, he plotted a kind of skyscraper with the height equal to the highest TC of a hydride formed by this element. Here you see sulfur. Its hydride has TC 203 Kelvin. Around it, you can find very good superconductors. But the best superconductors are formed by elements between the second and third groups of the periodic table. Our friend lanthanum here, 206 Kelvin. Yttrium hydride, yttrium H10, was predicted to be even above room temperature superconductor. But later, this compound, yttrium H10, was found to be unstable. Other yttrium hydrides exist. They are exceptional superconductors, but with slightly lower TC. I will talk about it a little bit later. Among binaries, lanthanum is the record holder. Among ternaries, this mysterious compound, as I already showed you. At the time when we formulated this hypothesis, two elements and their hydrides were not really studied. Actinium hydrides and thorium hydrides were not explored. According to our views, actinium and thorium belong to this belt of superconductivity, and their hydrides should be high TC superconductors. We checked this idea, and indeed, they were predicted to be exceptionally high temperature superconductors. You can see the highest TCs of about 240 Kelvin for both. Well, a number of experimental works have been done. Experiments are very complicated at such high pressures, but this was done for a number of elements, and the number of growing. Now, the number is growing. Also, my group, the above mentioned Dmitry Semenok, has started doing experiments as well. So in my group, we do a large number of experimental studies of this high temperature, high pressure superconductivity. This is a work which has just been accepted in Nature Communications. It's a very fresh work. Barium dodecahydride, nearly record content of hydrogen. Superconductivity is found here, but it's not very high TC superconductor because of Peierls transition, which breaks the three-dimensional sublattice of hydrogens into H2 and H3 molecular groups. So it's an interesting molecular superconductor. Yttrium hydride, yttrium H6, phenomenal superconductor, 224 Kelvin, and extremely high critical magnetic, upper critical magnetic field. This was done by extrapolation, but even if you look at the slope, you will see that it's extremely high. This slope and this upper critical magnetic field are about 2 times greater than theoretical prediction done by us. We do not understand why this upper critical magnetic field is so high. Possibly there are some unconventional physical mechanisms at work here. Neodymium hydride, neodymium hydrides NDH7, NDH9 were predicted, were synthesized. They have beautiful structures, very unusual chemistry, but they are not superconducting because of magnetism. They are antiferromagnetic. By the way, I want to show you here. I want to show you here this periodic table of superconductivity. This periodic table of superconductivity implies that, that these high Tc superconducting hydrides should not be considered as metallic hydrogen. The role of the metal atom is not just to donate electrons to the hydrogen. The role is much deeper. And with some elements, you get high Tc superconductivity, and with others, you get nothing. I would like to draw your attention to lanthanoids. Lanthanum forms high Tc binary superconducting hydride. Theoretical Tc is 286 Kelvin. Experimental Tc is very close, 260 Kelvin. Next after lanthanum is cerium. Cerium hydrides have superconductivity with Tc of only about 100 Kelvin. It's good, but it's much worse than lanthanum. After cerium, next is praseodymium. Tc is only 31 Kelvin for the best praseodymium polyhydride. And next is neodymium. If you ignore magnetism, then predicted Tc will be only 6 Kelvin, the highest. But if you include magnetism, superconductivity will be completely lost. You can see how lanthanoids, which were viewed as chemically identical, as twin elements, how different they are with respect to superconductivity. So the metal atom really, really matters. It's not just metallic hydrogen and metals as a source of electrons. The role of metals is much, much deeper. And it's possible that these unusual, unconventional physical effects, which we suspect drive the extremely high critical magnetic field, it's probable that they are related to the physics of yttrium, the physics of the metal atom. Okay, then thorium hydride. We predicted thorium hydride to be an exceptional high temperature superconductor. Tc of thorium hydride was predicted to decrease quite fast with pressure. At high pressure, experimentalists were able to do measurements of Tc. Actually, usually people do experiments at lower pressures. In this case, higher pressure was for some reason easier for them. At this pressure of experiment, 174 GPa, predicted TC is about 160 Kelvin, and experimental TC is also about 160 Kelvin. So very good agreement between theory and experiment at this pressure. What is the future? The future of increasing TC to room temperature and beyond is, in my opinion, in the greater chemical complexity. Look at the standard table from physics, solid-state physics textbooks. Elements are not great superconductors at normal conditions. The best is niobium, only 9 degrees. Among binaries, you can find much better superconductors. And the best superconductors at room pressure are very complicated cuprates. We think that the same will be true for hydrides. Among hydrides, we already reached 260 Kelvin. And if we want to go higher, we should go for ternary, quaternary, and more complicated systems. And the experimental result, which I already mentioned to you, for sulfur, carbon, hydrogen compound, confirms this. Room temperature superconductivity was reached exactly using this route of going for greater chemical complexity. We do not know if room temperature superconductivity can exist at room pressure, at ambient pressure. But we think that the insights that we have generated in this study for hydrides will be useful there as well. In particular, this superconducting periodic table of the elements. It's quite likely that it will be useful in designing room temperature and room pressure superconductors as well. Okay. We have trained a neural network on binary systems for predicting superconductivity of more complicated chemical systems. And you can see that a number of ternary systems are expected to possess TC above 300 Kelvin. These systems are now being studied experimentally and theoretically. In fact, we have predicted a very large number of such systems. So these systems, one by one, are now investigated by us. Prediction of stable chemical composition can be done not only for crystals, but also for clusters. But here there is a very important complication. In atomic systems, molecules, clusters, solids, the greater the size of the system, the more atoms, the more stable the system. Look at the binding energy of a Lennard-Jones cluster. It increases pretty much monotonically, and it will increase indefinitely until infinite size. The most stable nanoparticle is the infinite crystal. So if we operate by notions of absolute thermodynamic stability, then we cannot predict nanoparticles. We will always predict infinite crystal. But designing the experiment in a smart way, you can force the system to form nanoparticles, not crystals. And when you do so, and you analyze mass spectrum, you will find that some nanoparticle sizes are dominant. For example, for lead nanoparticles, small lead clusters with 7 and 10 atoms are predominant. Why? And how to predict this dominant, so-called magic nanoclusters? The apparatus for this exists. We have to give up absolute thermodynamic stability and operate with local stability. If you look carefully at this curve, this line rather, you will see that some clusters possess better binding energy than neighbors. So if you average nearest neighbors, this cluster with 13 Lennard-Jones atoms is better. It has greater binding. So it means that it's doing something right. If you look at the structure, you will see what it's doing. It's a closed shell cluster, closed geometric shell or closed electronic shell. You can identify the stable nanoparticles this way, and they are indeed the ones that dominate in the experimental settings. You can put this condition of local stability mathematically. You can generalize it to variable composition, multi-component systems as well. This is very easy. And once you have done it, you can build an algorithm for optimizing chemical composition and structure of nanoparticles and molecules. It works also for molecules. Molecule nanoparticle is actually pretty much the same. The algorithm is extremely powerful. Here you see the stability diagram of silicon-oxygen nanoparticles. N is a number of silicon atoms, M is a number of oxygen atoms. You can see that most chemical compositions of silicon-oxygen clusters are unstable, correspond to blue region, the sea of instability. This is always dominant. But you also have ridges of stability and islands of stability. One ridge of stability, SiO2, is standard. Any chemist would expect the composition silicon O2. Structures are beautiful, symmetric, chemically very, very reasonable. But surprisingly, there is another stability ridge, completely unexpected, at least for me, silicon 2O3. Structures are also chemically reasonable, symmetric, beautiful. If you look at the literature, you will see that such clusters are actually well known, and in fact, they are used as precursors in the synthesis of silicon quantum dots. You also see a number of islands of stability, such as Si4O18. What a bizarre composition. Such a molecule, silicon 4O18, is not known, but its close analog is well known. It's P4O18, phosphorus analog, with a pretty similar structure. I believe that this molecule can also be synthesized if people try. I hope people will try. Well, this gives us a map of the likeliest nanoparticles in a given multi-component system. You can see that unusual chemistry can be formed not only at high pressure, but also at normal conditions in the nano state. And this stability diagram with the sea of instability, with the ridge of stability and islands of stability is very similar ideologically and topologically to the diagram of stability of nuclear isotopes. You can see that nuclei of the chemical elements are also clusters made of two kinds of particles, protons and neutrons. And particular combinations of the numbers of protons and neutrons give rise to unstable nuclei or stable ones which form ridges or islands of stability. The fundamental difference between this diagram for atomic nuclei and this diagram for nanoclusters is only in the type of long-range interactions. Long-range interactions in atomic systems are always overall stabilizing, so the more atoms you add, the more stable the structure is. So my stability ridge, SiO2, is infinite, and the bigger size, the better. For atomic nuclei, the only long-range interactions are Coulomb repulsions between protons, destabilizing interactions, and this is why you cannot make an arbitrarily large atomic nuclei. They will spontaneously decay. So this diagram is fine. Okay, when we look at the magic or stable nanoclusters, you will see that they are all chemically reasonable and symmetric. Even if the chemical composition is strange, the structure is extremely reasonable and intuitively right. If you look at the lowest energy structure of an unstable composition, you will see that this structure does not make much sense. It's asymmetric and chemically not very reasonable. Nature somehow, using the language of energies, filters beautiful symmetric solutions and favors them. Metal oxide nanoparticles were explored as well, and they show the same, exactly the same trends. Okay, finally, what I want to show you is how we predict optimal materials. Materials with the properties that we need. Okay, first, how to predict the property material with the property that we need. For example, for a fixed composition or for a given chemical system. Let me show you this on the example of thermoelectric materials. Thermoelectric materials have a wide range of applications. And there has been a steady growth of thermoelectric figure of merit ZT. This is the key quantity that we need to maximize to find better and better thermoelectric materials. This quantity is dependent on the electrical conductivity, Seebeck coefficient, thermal conductivity, and temperature. We really know how to calculate it. It's not an easy calculation, the calculation of this figure of merit ZT, but we know how to do it. If we want to, we can calculate it. Here is one of the illustrations. And once you know ZT, you can estimate the maximum efficiency of your thermoelectric device. So it's extremely useful to have ZT. You can try to find the crystal structure with the highest possible ZT. Well, for great materials that we have today, ZT is of order of 1 or 2. These are really the phenomenal values, kind of record values for bulk materials. On the computer, you can predict ZT equal to 50. But when you look at this crystal structure and its energy, you will see that it's a completely unstable structure. The energy is so high that you will never be able to synthesize it. So when you optimize physical properties, you cannot just take the physical property and optimize it alone. You have to optimize it somehow together with the energy. So you have to optimize ZT and energy at the same time. This brings you to the concept of multi-objective optimization, the so-called Pareto optimization, named after Italian economist and mathematician Vilfredo Pareto. In Pareto optimization, solution of multi-objective optimization problem is not one state, not one material, but a set of materials such that each of these materials, it may be beaten by ZT, for example, or it may be beaten by energy, but it cannot be beaten by both properties at the same time. These solutions are the so-called non-dominated solutions. They represent the optimum in the problem of multi-objective optimization. The optimum is not one solution, but a set of solutions, the so-called first Pareto front. And if you imagine to remove the first Pareto front and construct Pareto front again, then you will obtain the so-called second Pareto front and third Pareto front and so on and so forth from your data. Looking at Pareto fronts for bismuth telluride, for the problem of finding highest ZT and at the same time lowest possible energy above the ground state, we find that it should be quite possible to find much better thermoelectric materials if we look for metastable states. This echoes an independent work done using completely different approach by American scientists who used data mining, so chemical analogy and crystal structures from the databases. Here as well, you clearly can improve ZT greatly if you go for metastable low energy states. We have also developed, by the way, a program called ICON, ab initio conductivities. The first version of this code contained calculation of only thermal conductivity. The second version, which we now submitted for publication, allows you to quickly and reliably estimate thermoelectric properties as well. Here you see one of the materials which we played with recently with quite a decent figure of merit ZT up to about 0.5. As I told you, values of about 1 are just phenomenal. 0.5 is already quite good, and you can do something with it. And we have found also much better materials, which I'm not showing on this slide. ICON code, by the way, can be downloaded also from our website if you are interested in thermoelectricity. Okay, so we know how to quantify the materials in terms of their properties. We have to build a Pareto front with many different materials. So we have to plot many different materials and determine the Pareto front. Pareto optimization is the key here. Now let me show you how we solved the most ambitious problem of the central problem of theoretical material science, finding the best material among all possible compounds formed by all possible elements. Okay, the number of possible compounds is absolutely breathtaking. We have 118 elements which form several thousand binary systems, and in each binary system you can have hundreds or thousands of possible stoichiometries for each an infinite number of possible structures. How to find the best material among this huge multitude of possible solutions? You cannot do it enumeratively, trying all possible chemical compounds with all possible structures. This is just completely unrealistic. You have to do it in some form of evolutionary way. You can do it if you build a chemical space. You need to build a chemical space such that nearby points in this chemical space possess similar properties. Imagine that you arrange the chemical elements not by their atomic number, hydrogen, helium, lithium, beryllium, but in another way, in some kind of continuous way, such that neighboring elements have maximally similar properties. Then compounds, binary compounds, for example, will be points on this diagram. And neighboring points will be maximally similar binary compounds. This is the idea of the chemical space. Then imagine you have the best possible material, for example, the hardest possible material, which is located here. Close to this hardest material will be other very hard material. And if you have one or two, a small number of such islands of very hard materials, then you can use the concept of evolutionary algorithms, zooming in on these islands of high hardness and finding the hardest possible materials. This is the idea of our new method called Mendelevian search. which we developed together with my PhD student and now postdoc, very talented scientist working in Moscow, Zahed Alahiari. You will see him in this workshop. Such a concept of chemical space, in fact, was developed by David Pettifor many years ago. He proposed the so-called Mendeleev number, the origin of which was quite obscure. He walked up and down the groups of the periodic table, but sometimes by diagonal or horizontally, without real explanation of what's going on. But once you construct such chemical space, you really can find, for example, all exothermically formed alloys grouped together, clustered together in one region of the chemical space. So it works. I was not satisfied with the empirical and obscure nature of the Mendeleev number developed by Pettifor. In fact, there were a number of attempts of redesigning Mendeleev number using different empirical considerations based on databases in the literature. But I was not satisfied with any of these empirical considerations and redesigned Mendeleev number on the basis of fundamental properties of the atoms, their sizes and their electronegativities. If you want, I will explain you how exactly this was done. We just published, in fact, this paper just came out a few days ago in the Journal of Physical Chemistry C, and our thus designed chemical space turns out to group much better compounds with similar properties. So now we know where, in which part of the chemical space, the hardest compounds are hiding. And then we can use the apparatus of evolutionary algorithms and zoom in on this region of the hardest compounds and find what is the hardest possible compound. For example, but it doesn't have to be hardness. You can optimize any property of your materials using this Mendeleevian search. Here you see our non-empirical Mendeleev numbers, how they work not only for hardness, but for other properties, such as magnetization. They work very, very well. And for enthalpy of formation, you can see that the highest negative values of the enthalpy of formation belongs to compounds of very different chemical elements, metal atoms and fluoride. Metal fluorides have the most exothermic enthalpies of formation, and they are followed by metal oxides. We knew that electronegativity difference is important for exothermic enthalpy, highly exothermic enthalpy of formation. And here we confirm it very, very strongly. Okay, so we have constructed the algorithm which starts with random chemical systems. In each chemical system, in each of these points in the first generation, we perform a short evolutionary calculation, optimizing, for example, hardness in this case, and enthalpy, enthalpy above the convex hull. So these are variable composition calculations, as I explained to you before. Those systems which are not able to generate high hardness are discarded. Those systems which are more promising are given right to produce children through chemical mutation, chemical heredity, and transfer of structural information. After a few generations, you see that we very densely sample this most promising region of the chemical space, producing many super hard materials. Then we find diamond, and as you continue longer and longer, you will not find anything harder than diamond. So we also find Lonsdaleite, hexagonal diamond, which has the same hardness as diamond and practically indistinguishable properties. So this is a computational proof that nothing harder than diamond can exist. In one calculation, we found the solution to the problem which people tried to solve for probably more than a century. People tried to find what is the hardest possible material. Here it is, as a result of one calculation. But remember the property of evolutionary algorithms to zoom in and sample more and more densely the most promising part of the search space. In the same single calculation, we find cubic diamond, hexagonal diamond, famous super hard material, cubic boron nitride, and all super hard binary systems that have been that you can find in the literature, and a number of other new hard and super hard systems that have not been discussed in literature yet. Many of these can be stable at normal pressure. Many of these can be synthesized more easily than diamond and cubic boron nitride, which require pressure. Many of the materials that we predict, actually, although they are softer than diamond and cubic boron nitride, but their synthesis does not require any pressure and is therefore cheap and highly technological. Here is the treasure map of these hard and super hard borides and carbides. Let me not dwell on it. One of these materials was synthesized and structurally analyzed. This is by itself quite an interesting story, but I would rather wrap it up. I mentioned to you that nothing harder than diamond can exist. Earlier this year, a group from Japan published a paper in Physical Review Letters where they constructed by hand, not using any kind of algorithm, but just by hand, by imagination, they constructed a pretty strange structure which they called pentadiamond. Pentadiamond has very high energy, so it's pretty much unlikely that it will ever be synthesized, but according to the calculation of the Japanese scientists, it has very high elastic moduli. The Young's modulus is several times greater than that of diamond, and if you evaluate the hardness, you will find that it's twice the value of diamond, twice harder than diamond, if you believe these elastic constants calculated by Fuji and others. We have a machine learning algorithm developed by us which predicts the whole elastic constants tensor. You will see that our tensor components are completely different from the elastic constants of Fuji and others. Then we did two kinds of ab initio calculations which confirmed machine learning results and killed the result of Fuji and others. Their work is clearly incorrect. I really don't like writing comments to other people's works, but this was a special case because pentadiamond and its great properties were really publicized all over the place, Nature, Science, CNN, News, and so on. I really didn't want my children to learn from textbooks where these incorrect results would be publicized. So we wrote a comment, we submitted it to Physical Review Letters, and as a result, Fuji and others checked the results and found them to be incorrect. And the paper of Fuji and others has been withdrawn, retracted, as a result of our comment. So time and time again, whenever people try to find a material harder than diamond, it is found that results claiming that something is harder than diamond are wrong. Nothing harder than diamond can be found. Okay, I would like to thank very talented people from my laboratory. You see some of them here, and external collaborators for contribution to this work. And I showed you some of the capabilities of USPECH, how we can predict unusual chemistry, novel materials, composition and structure of stable crystals, nanoparticles. I think this really opens a new chapter in chemistry, new breathtaking chapter of chemistry, and you as users of our code have the opportunity to make great discoveries, one of which I already illustrated, done by users of USPECH, the breakthrough in high temperature superconductivity. Thank you very much for your attention. There are lots of things remaining to be done. Prediction of protein structures is only in the beginning. It's a very complicated problem if you do it from theoretical basis. Grain boundary structure prediction is a rapidly developing and very important field, and many, many problems that remain to be solved. Thank you for your attention.
Thank you, Artyom. We have several questions in the chat, and I think probably we can ask people to ask them by themselves.
Perfect.
We have a couple of questions from Lucas Francisco, if you don't mind. You can
Actually,
ask. Yes.
hello, everybody. They can unmute themselves. We
Okay.
can do it one by one. Start with probably Akshay Mahajan because he was the first one to ask the question.
Mhm.
And
Perfect. Or maybe I can just read the questions and answer them. Yes.
Mm,
Good morning. Good morning. Lots of good mornings. Okay. Okay. YouTube broadcast. Uh,
I think the first question was at
yes.
10:38.
Can you explain the difference between mutation methods like soft mode mutation and permutation method? Mm, soft mode mutation has something to do with soft modes and phono dispersion. Yes, exactly. Both permutation and soft mode mutation, and also lattice mutation and rotational mutation for molecules, they are different, and transmutation for variable composition systems. They are all different kinds of mutations. Mutations act on a subset of variables. If you do permutation, you swap chemical identity of atoms. So the overall chemical composition is conserved, but the ordering of atoms in the given crystal structure is changed. If you do transmutation, you do not act on positions of the atoms. You act also on chemical identity. This was lead, one of them becomes gold. The overall chemical composition differs. So you do not work on positions of the atoms, you work only on the chemical identities, but then you relax the strength. Lattice mutation, you do not change identities of the atoms, you do not change positions of the atoms, but you change the cell shape. Suddenly, discretely, by a large amount. Soft mode mutation does a different thing. You do not change identity of the atoms. You do not change lattice parameters. You take atomic positions and move them along the eigenvector of the softest phonon mode. So your understanding is correct. Lucas Francisco writes, good morning. I would like to ask about structure prediction convergence. When the correct stable structure is found, does it keep appearing across the generations? Yes. We make it survive through the generations. How can we know when such structure is actually more stable? If we perform more generations? We have different ways of knowing it. Of course, we cannot guarantee that the global minimum is global, not local. But we have important heuristics. One heuristic is if for a large number of generations you cannot find anything lower in energy than this structure, then this structure is global minimum. You will see in the exercises how it is done. You need to specify a sufficiently large number of generations during which you trace the lowest energy structure. If it is not changed, if nothing better is found, then this is a global minimum. If you want to make sure, you can perform calculation again. If you these calculations, evolutionary calculations, they are stochastic. So if with the same input you perform the calculation 2 times, hopefully you will find the same lowest energy. But the trajectory will be different. You will sample different structures on the way. So you can do the calculation twice and see if you produce still the same global minimum. And finally, there is a so-called anti-seed technique. Please check in the manual. Anti-seed technique performs aging operation. So the lowest energy structure and all the structures that you have encountered so far, when they are found the second time and the third time and the fourth time, their fitness, their energy is artificially worsened. So they become older and weaker, and eventually they die. And this allows you to divert the sampling of the energy landscape away from those low energy structures, just in case you need to sample other parts of the energy landscape. Umesh Roy asks, I would like to, is there any correlation between magnetic materials and high temperature superconducting materials? Kind of. If you have magnetic ordering, superconductivity is impossible. This is well known. You can have superconductivity in systems with unstable magnetism, with fluctuating magnetic moments. Cuprates are one kind of such materials. But if you have magnetic ordering, superconductivity is impossible. So ferromagnets, antiferromagnets, ferrimagnets, none of them can be superconductors. Another question from Lucas Francisco. When we perform energy calculations via DFT, we choose one target pressure. How the stability pressure range of different phases, such as sodium, is determined? Do you have to perform many structure predictions at many pressures? Yes. You have to perform structure prediction at several pressures. You have to look at the lowest enthalpy structures. In fact, it's even better if you plot um, the found structures at a given pressure in the space enthalpy, volume, and then you form some kind of convex hull. You can view it as convex hull as well, which shows you the likely structures that will be formed at higher or lower pressures. So you take low enthalpy structures, and you take also these structures forming the convex hull in the pressure enthalpy space. And then you carefully relax them at a number of pressures and trace when enthalpies cross. This will give boundaries of stability ranges of the phases and compounds. Kamal Chinatambi asks, I saw many studies of structure prediction at high pressure. What about the structure prediction at high temperature? This is complex because high temperature necessitates the use of entropy as part of the free energy, minus Ts term. And entropy is a statistical quantity that requires sampling many different states. This means that instead of one single state, structure prediction at zero temperature, you need to sample perhaps thousands of states. And this increases computing costs by orders of magnitude. This is computationally very expensive, but we found a way to solve this problem. And later in this workshop, Ivan Kruglov will talk about this. Shiv Prasad Shastri asks, can we do calculations on structures with defects and disorder present in order to predict stability? Well, at zero pressure, defects will not be stable. They will be stabilized only at high temperature, and only some kind of defects, like point defects, will be stable at high temperature. Right now, we cannot do it, but we are trying to find ways to do it in a computationally tractable way. Juan Beltran says, thank you for great talk. I'm happy that you liked it. Can you talk a little bit more how to obtain the Mendeleev map where similar property materials are nearby? How can one extend to binary and ternary compounds? Well, what I showed is already for binaries. Okay, let me clarify it a bit more. I had to skip quite a lot of details in order to fit in the time limitations. Okay. Yeah, this is also a map of hardness. In the x-axis, we plot all the elements with their Mendeleev numbers. Each atom, each element has a Mendeleev number. 1, 2, 3, 4, 5. But this is not like a sequential number of the elements, hydrogen, it's different. We plot elements in this sequence in the x-axis. We plot elements in the same sequence in the y-axis. This is binary chemical space. Each point, for example, this point, gives you a binary system of element number 10 and element number 20, whatever this is, whatever. Sodium and yttrium, for example. All sodium yttrium compounds will correspond to this point. This is the chemical space for binary compounds. Ternary compounds would be done the same way. You will have the third axis. So element A along this axis, element B along this axis, element C along the third axis. And the same will be true in the ternary space as well. Nearby points will have similar properties, and good materials will be surrounded in this chemical space by other good materials. So you can use the concept of evolutionary optimization. I hope I have clarified this point. Ashley Williams asks, since USPEC ranks by enthalpy, is it possible to have an accurate search if your crystals are at different pressures? In principle, we can do it. But then it will be not enthalpy, but a different quantity. In principle, we can do it. But in this case, you need to construct convex hull in the space enthalpy volume, and you have to minimize the distance in this convex hull, distance from this convex hull. We have not done it. We have not done it. We might. I'm not sure how well it will work, but we might. Okay, BPLAB sun. So right now, if you want to do it, you need to sample different pressures, and at each pressure you do, for example, variable composition and find the stable compounds at each pressure. BPLAB Sanyal asks, is it possible to do crystal structure prediction and magnetic structure prediction simultaneously? Absolutely, yes. You can do it in the currently developed version, and we submitted a paper about this. You will be able to see it, but it's very easy. You can do it with USPEC using the version that you have. And by the way, there is a limitation. Right now, USPEC can only optimize collinear magnets. So magnets where magnetic moments are parallel or anti-parallel to each other. Canted antiferromagnetism, all kinds of non-collinear antiferromagnetism, this stuff is not possible yet. Anum Shahid Malik asks, I think, asks, when we do calculations using DFT for some structures, we freeze fix some bottom layers of the structure. Why is it required to do this? Well, this is only required if you do surfaces. If you do prediction of the surface structure, you have to fix the substrate, because remember the kind of problem that you're solving. You know the surface structure. You are interested in the behavior of rather few atoms on top of a fixed crystal structure. So you fix crystal structure and study the arrangement of atoms in the field formed by the substrate. So when you have the substrate, you have to specify the substrate. If you don't do it, then the problem becomes meaningless. The calculation becomes meaningless. But we do it only in such kind of constraint problems. When we do crystal structure prediction, we do not freeze any kind of bottom layers. This would be meaningless. Okay, have I answered all your questions? Does anyone else want to ask anything?
Okay, I think Artem, that's it, and thank you very much for your great talk, as always. And we have next talk coming by Xavier Gons.
Let me stop my screen sharing.
Xavier?
Yes, okay. Thank you, Vladimir. Hello, everybody. Shall I start now, or in principle, it's in 2 minutes?
Well, I think we're not as such a precise. We may start now.
Okay, yeah, I will start now then. Let me share my screen. Oops. Yes, here, share. Yes. And now, is it okay? Do you see my screen correctly, Vladimir?
Yes, it's fine.
Okay. So yeah, I will now present a work which is still ongoing, where we are looking for applications that might have an impact in real life. Sorry, first principle study of phosphors for white LED applications. Well, my collaborator in this work are mentioned here, some from UC Louvain, Yongshao Jia, Julien Boucchio, Anna Milio, Matteo Giantomasi, some from APFL, Switzerland, Samuel Ponce, and some from a company in Japan, Masayoshi Mikami. And it must be emphasized that lighting is a very important source of electricity and energy consumption. It's similar actually to the amount of electricity generated by nuclear power. And there's been tremendous improvement recently in the field of lighting, but still there is some possibility for improvement. Let me show you this figure in which, in chronological order, the efficacy, the luminous efficacy of different lamp sources, light sources is plotted. One started with incandescent lamp, then halogen lamp, but this had a very small luminous efficacy on the order of 20 lumen per watt. This is the international unit for the total visible flux emitted by a source. And as a, let's say, reference, 1 watt of green light at this wavelength would deliver, if fully transformed in light, would deliver 683 lumen. Well, you see the scale here goes up to 150 lumen and is actually achieved nowadays by the white LED light emitting diodes devices that appeared in the last years of previous century. But there is still room for improvement. For white light, one might go to 300 lumen per watt at the maximum. Another information about what has been done recently is the evolution of the light emitting diodes. I will discuss them later. Again, in chronological order, the red diodes are here. The wall plug efficiency, this is the ratio between electrical power and optical power in logarithmic scale, maximum being 1. You see that in the 60s, 70s, the emphasis was on red, but then in the 90s, the blue light emitting diodes have been constructed, and this was for a Nobel Prize in Physics 2014 by Akasaki, Amano, and Nakamura. When one combines a blue light emitting device with a phosphor, and I will emphasize this fact later, one can indeed produce a light that seems for the eye white. But still, there is some loss of efficiency of producing not pure blue, but white. Still, the result is not too bad, but subject to improvement. Okay, at the level of indeed producing light from electricity, this is the principle of light emitting diode. I guess most of you knows it. There is here a source of a current, and one connects a P layer with an N layer, and just at the junction between these P and N layer, we have that holes that are injected, and electrons that are injected will recombine and generate light. Pictorially, this is represented here. You see the electrons are injected here, the holes are injected there. There is a change of Fermi level because of the different doping of these materials, and the light is generated by this recombination of electron and holes, but has a very specific energy. It's not at all white, it's just in this case blue, for example. Actually, the standard white LED are have the following structure. Well, this is a representation of what you can find nowadays in many, many places. You enlarge it, you get the following picture. You see the light is generated in this direction. You inject electricity by this contact, some gold wire. And then at the heart of this device, just on top of the cooling element, we will find the following. The substrate, the electrical injection, the emissive layer of blue light, but there is also some yellow phosphor that is represented here, which is in most of the commercial devices nowadays so-called YAG doped with cerium. But actually combining the blue light emitting device with a phosphor, will allow to get the impression of white light. A yellow phosphor will generate so-called cool white light, not very good for the eyes. If one makes some phosphor blend with red and green emitting phosphors, one will obtain a warmer light, warm white. Actually, let's have a look on what is done really in these diodes. You know that white color might be obtained by combining different colors, red, green, blue, but also simply blue and yellow will succeed to make white light. And indeed, in the simplest case, that's what is done. The spectrum, as a function of wavelength, the intensity of the light of a typical white emitting LED nowadays is the following. You get a blue peak, an enormous blue peak due to the diode. And then thanks to photoluminescence, this phosphor will absorb part of the blue light and generate this broad peak in this region of the spectrum, which is broadly speaking yellow. This is done thanks to this YAG phosphor. But you will notice particular shape of the spectrum, a peak here, then something broad, but it is not at all like the light from the sun. Indeed, the light of the sun, which is represented here, the visible range as a function of the wavelength is here. You see that at the sea level in red, we have indeed some depletion in the blue, but then the intensity is nearly constant over the whole visible range. So compare this behavior with this one, you will see that there is quite a difference between these two spectrum. And in particular, for such photoluminescence from the phosphor, there is here a lack of red component, and this is quite detrimental for the eye perception. We are lacking a good red phosphor, and not that there is no red emitting phosphor, but it should be a narrow bandwidth phosphor, not a large bandwidth phosphor. Why? It is because the human eye sensitivity is like this, between the blue and the red. And if we go from this blue to a wide red emission, we will waste a part of the light. We need something that is more adjusted to the sensitivity of the eye. And there are indeed many possibilities to obtain, to do research in this field. There is a wide diversity of LED plus phosphor. The conventional type is indeed blue LED plus yellow phosphor. There are high color rendering types, blue LED plus yellow plus red, but that should be sufficiently narrow, and this is a problem. Near UV LED plus blue plus green plus red, blue LED plus green and red, etc. There are many different possibilities. And also the tuning of the emission band of some typical dopant like europium-2 can be achieved by using different hosts inside which the europium is inserted. So how shall we find new phosphors? What is the role of the host? What is the role of dopant? What are selection criteria? So now I will indeed present information related to all these and present our work. I would like at this stage to make the connection with this USPEC workshop and school. So my talk will present an example of search from material, which is ongoing. It is important to find new materials that have indeed the possibility to be synthesized. But in this case, we are looking for optical properties. And this is a region of the search for new material in which, to my knowledge, USPIC has not yet been applied, but that might have indeed in the future large developments of USPEC capabilities. The coupling of with first principle codes is very important in that level. And here I will show what kind of indicators might be used in the future to do a large scale search from new materials. In what I will show, I will use as basic references the work that we have published with my collaborators starting in 2015, etc., up to some recent work. I will speak about the roles of phosphor in white LED. This was already somehow targeted. Working principles, selection criteria, the so-called 4F5D phosphors, how to model them. First principles, yes, but not too much because its optical properties might be very difficult. I will show an application theoretical study of lanthanum silicon nitride host plus cerium, then some study up to 28 different hosts, and then the recent work that we have been doing at the level of the so-called thermal quenching, the width of the emission, and how to go beyond the simple model that I will rely on for most of my presentation. Okay, so typically what happens in a phosphor, as I've emphasized already, we have photoluminescence. We go from absorption of blue light to emission of yellow light. And a phosphor will indeed be characterized by its spectrum. The absorption might be in the blue with a peak here. And then the emission will be more in the yellow range, for example, with a peak of emission. We will indeed try to obtain for different materials what is the absorption energy peak, what is the emission energy peak. The difference between these two quantities is the so-called Stokes shift. And also an important characterization will be the width of the emission. How can we explain the absorption and emission difference? Well, when absorption occurs, there is a one electron that will go from the occupied state to the unoccupied state, absorbing the photon, and this will trigger a change of geometry inside the solid. Atomic configuration change that will decrease the energy, hence the Stokes shift. And then we obtain the emission, which is again purely electronic. In addition to the characteristics that I have presented, I have to mention also the effect of temperature. Indeed, not all phosphors behave the same way with respect to temperature change. When we take as a reference room temperature for the emission intensity, 100%, let's say, raising the temperature up to working temperature of the device, the phosphor, which is usually on the order of 150 or 200 degrees Celsius, might be accompanied with a moderate loss of emission intensity, like in this case, 20% only, or a dramatic loss of emission intensity. Here, only 20% of the efficiency is still present for this other host material. And actually changing slightly the composition of the host might induce dramatic changes of the temperature. For example, if one dope with europium this material, barium 3, silicon 6, oxygen 12, nitrogen 2, or this material, barium 3, silicon 6, oxygen 9, nitrogen 4. You see only small differences at the level of the oxygen and nitrogen. You see that the emission intensity will go from this peak at low temperature, 4 Kelvin, to something at 300 Kelvin, which is not too bad. But for this material, we dramatically decrease the emission intensity from this peak to that value. So details matter. The criteria for selecting phosphors are as follows. First, we must have an emission spectrum that complements adequately the one of the light emitting diode, the blue emitting diode, for example. Possibly, there might be some other phosphors to be generating this emission spectrum. The line width is very important, as I already mentioned, and the search for a good red narrow width phosphor is ongoing. Now, phosphor may also have a spectrum of excitation, of absorption, that should overlap with the one of the pumping LED, and a large absorption strength. This is the second very important criterion. Third important criterion, the optical characteristics should be unchanged at elevated temperature. The thermal quenching is very important. Also, the shift of the color of the phosphor should not occur, and the change of the width of the emission should also be very much controlled. Quantum efficiency should approach unity. This is irrespective of the thermal quenching. The stability of the material should be good, and also there should be the absence of emission saturation at high fluxes when we want to obtain a large emission of light with a strong current still from a relatively small device. Of course, the temperature might be higher in this case because, yes, the Stokes shift means that some energy, some part of the energy is emitted, is transformed into heat from the initial photon blue being transformed in photon yellow. The best choice at present, so the search space that is defined, usually is relies on cerium and europium doped inorganic host. They have a 4F5D transition inside the band gap, as I will show, which is tunable, which can lead to adjustable emission color. But the space of host is huge. People have looked at silicates, ternary, quaternary, phosphate, oxynitride, oxysulfide, fluorides, etc. There might be more anions type to consider. Usually cerium and europium will be substitutional to trivalent or divalent metallic ions. In general, with these two ions, one has a large absorption strength, an excellent quantum efficiency, and as I mentioned already, it is tunable thanks to the host. Now, is it always providing a good thermal stability? Is the thermal quenching strong? Is the emission band adequate? Is the width adequate? This is depending on the host. How can theory help for such complex materials? We should do a high throughput search, but with which indicators? And with USPECT, one should also come with kind of Pareto front in which one trade off between the energy above the convex hull and the relevance of the material for the emission characteristics and thermal stability. There is a model which is very well known for these type of phosphor linked to 4F5D transitions. Let's take, well, the electronic structure of the cerium is mentioned here, and of europium is mentioned here. You see in the case of cerium, Well, we will have in cerium 3 plus 4f1 5d0 electronic structure. So it is possible to excite this one electron from the 4f to the 5d. In the case of europium 2 plus, we have 4f7, half of the shell is filled, and 5d0. And what will happen is indeed we go to 4f6, 5d1. So if the ion were free, we would have simply 4f going to 5d. But it is placed inside a host, and then one can see that the 5d orbital will interact a lot with the host. There will be first a kind of so-called centroid shift of the 5d level, then a crystal field splitting, and here we start to have some level below the conduction band. For the unperturbed geometry of the ion inside the host. But as soon as we have absorbed the light, there is a relaxation, Stokes shift, to a still lower level, and then we have emission. Blue absorption, yellow emission. Dorenbos, with this model, actually quantified a bit the excitation and emission spectrum, the peak, in terms of basic indicators like the average nearest neighbor distance for the dopant, or some polarizability, or the coordination number. But is it enough? And in our search, in our work, we have started to do first principle calculation. But the search for better phosphor might be done, of course, at the level of the Dorenbos model. That might be semi-empirical, or yes, indeed, there are experimental data for more than 100 doped hosts, something like 200 or 300 doped hosts. But are these data of sufficient quality? And in particular, are the material quality that were experimentally synthesized sufficient? And also, for not all these doped hosts, we have data for the line width and the thermal quenching. One might say, oh, one should start to do machine learning, but no, you cannot really do machine learning with something 100 or 200 doped material. Usually you need 1,000 to 2,000 material in order to have good predictions. First principle approach might either give new data from machine learning or allow direct high throughput search. But then in this case, one would need accurate data, and in this case, one would need speed. And indeed, at the level of first principle calculation of optical spectra, we face some problem. Is it possible to obtain good spectrum while optical excitation that are neutral needs electron-hole interaction? The state of the art is the so-called Bethe-Salpeter equation. But Bethe-Salpeter equation is notoriously really slow and CPU time consuming. Bethe-Salpeter calculations can be done for up to 10, 20 atoms reasonably fast, but to do a high throughput search with Bethe-Salpeter equation for doped materials with supercell of 60, 120 atoms, because the europium or cerium doping is usually on the order of a couple of percent, is really not cannot be envisioned nowadays. Moreover, we have cerium and europium, which means we have 4f electrons, and this is an additional technical challenge. So for this reason, we cannot afford Bethe-Salpeter, and moreover, we need to relax the geometry. So what are simpler approaches to generate indicators? Shall we rely on ground state only? Should we rely on doped material, bulk or undoped? How to address line width? How to address thermal quenching? You see the complexity of the problem. So To summarize what I have sketched until now on this Jacobs ladder between accuracy and speed, we might try to simply look at the undoped bulk. We might look at the doped ground state plus kind of a Doornbos model. At the extreme, we might look at Bethe-Salpeter equation, but this is accurate, but the speed is very bad. And actually, I will show you that there is another technique. But also at the level of the Doornbos model, we have some problem of predictability. You see that when comparing the semi-empirical energy from Doornbos and the experimental energy, although the trend is correct, there is a large spread of the points. And this is only for the absorption. Actually, the Doornbos model needs to know the geometry of the system in order to predict the difference of energy. So one needs to predict the emission. What is the excited state geometry? We have used the delta SCF method, delta self-consistent field method, in which in a supercell, we consider first the ground state, where we have indeed one electron on the 4F level between the valence band and the conduction band. But then we compute the total energy when we have occupied the, when we have unoccupied the 4F state and a 5D level because of this emptying the 4F state has gone from the conduction band down, and this 5D state, we occupy it. And what we built are so-called configuration diagrams. At the geometry of the ground state, we compute first the total energy of this configuration, obtain A0 geometry by the state and the E0 energy. Sorry, I have some problem here. Then we excite indeed one electron from the 4F to the 5D. We obtain another energy without first relaxation, the configuration. Then we relax the configuration. We use the forces that can be computed if we do DFT calculation in this excited state. And then we compute the fourth energy when we have relaxed the occupation number to the ground state, but without relaxing the coordinates. This will be our workhorse, delta SCF with one-dimensional configuration diagram. Indeed, it is called one-dimensional because we simply explore the space along the change of atomic coordinates between the minimum of the atomic geometry when we are in the ground state, electronic ground state, and the minimum of the geometry when we are in the excited state. So these calculations have been done using density functional theory plus U, using the Abinit software, projecting augmented wave, PAW plus plane wave. Some technical details are given here. So Abinit is a free software, which is on the same class of software application as VASP or Siesta or Quantum Espresso, that is particularly strong at the level of many-body perturbation theory and also density functional perturbation theory to compute phonons. That was started already 23 years ago, and we have a large user base. Although it is not the most used code, VASP is kind of the leading code in this domain. I will show you the calculation that we did for first lanthanum silicon nitrides, showing the issues that we have encountered, and then I will scale up to more materials. When we place a cerium-3 ion in lanthanum silicon 3 nitrogen 5 or lanthanum 3 silicon 6 nitrogen 11, this is what we observe. In the first case, we have this spectrum with emission at 2.58 electron volt in the blue. In the second case, we have an emission which is in the yellow, 2.25 eV. You see that the difference is not very large, but for the eye, the color is very different. Of course, we are looking for trends, definitely, and we might select materials that are in the correct zone and not accurate to 0.01 eV. But while in the first case, there is only one doping site to put cerium, actually the cerium will replace one of these lanthanum that are all equivalent thanks to symmetries. In the second case, there are two sites for the cerium to replace the lanthanum. In Wyckoff notation, there are two A sites and four C sites. And actually the question is whether the emission come from one of these two sites. Is it actually detrimental to have several sites? Is the line broaden? Apparently there is indeed a broadening, but this is not due to the different sites, as I will show later, but it is due to the spin-orbit coupling. So what is the reason for the different emission color in these two apparently very similar materials? You see the neighborhood of the lanthanum. It's just a couple of nitrogen atoms in both cases. And what is the luminescent center in the lanthanum 3 silicon 6 nitrogen 11 doped with cerium material? A simple calculation of the band structure shows some difference. Well, not very large, 0.22 eV difference at the level of the band gap. But is this the source of the different emission value, 2.58 and 2.25 eV, while we know that actually it's the transition between the 4F and 5D electronic level that will occur, not between the bottom of the conduction band and the top of the valence band. Well, when we dope the LSN with cerium, either at the one possible place or at the first or second possible place for the 3,6,11 compound, one obtains the following. A simple cone-sham band structure will show that the cerium 4F is indeed present in the band gap, not really very, not much, it will not much differ with the band gap in this case, but still there is a clear line just above the band, the top of the valence band. It is a bit better for these two cases, but the cone-sham band structure do not give a cerium 5D state inside the band gap. We observe simply lanthanum 5D as the bottom of the conduction band. So the straight DFT calculation without excitation is unable to help. But by doing the delta SCF method, and I have already shown this slide to you, so exciting, really emptying the 4F state and exciting one electron to the 5D, we obtain the following bottom of the conduction band. In the excited state absorption geometry or the excited state emission geometry, one sees first that indeed there appears to be a cerium 5D levels in the three situations that we are exploring. So this is good for the ability to predict a 4F to 5D transition and to predict the energy absorption. But when we look at the excited state emission geometry, we find that in one case, the cerium 5D band has disappeared. It has gone back to the conduction band level. The bottom that is observed here is lanthanum 5D, which is non-luminescent. So by this approach, we were able to first obtain indeed an emission at the level of the LA silicon 3 nitrogen 5 state, or 3611 cerium 2a site, and we have shown that the site cerium 4c is actually not luminescent. And then when we compare all the data of total energy with the experimental data, we see that we have a reasonably good prediction capability. For the absorption, our theoretical results and experimental results are here. Prediction experiment for the 135 case. For the 3611 case, you see prediction and observation, while for the emission, we have also some good prediction. We have simply a small shift that is nearly constant for all materials in the case of cerium of 0.1 EV between our theoretical prediction and the experimental prediction. We actually can correct for this prediction. The Stokes shift is not as good, but still it is reasonably predictive. So we can indeed obtain an understanding of the absorption and emission. How can we now explain the difference between these two polymorphs of the host, LSN? Well, according to Doornbos model, which is not very predictive actually, but it brings understanding, and this is quite important. The big difference between these two materials will be the numbers of nearest neighbor surrounding the cerium atom. In the 1, 3, 5 compounds, we have 9 nitrogen present, while in the case of the 3, 6, 11 compounds, we have 8 nearest neighbor. And this will indeed bring the small difference that makes this material emit in the blue and that material emit in the yellow. So you see, it's quite interesting to obtain the description and the understanding thanks to a semi-qualitative model. Now we have made a large scale of study of different materials, and I will show you the kind of results that we have obtained. Well, this is a full table where the compounds are listed. They will be often denoted by only 3 initials, like LSN, lanthanum, silicon, nitrogen, yttrium, aluminum. This is for garnet, yes, for this material, and some other you will see L, Y, S, etc. So we predict usually the absorption and emission in good agreement with experiment, still with some outliers. And the Stokes shift is also quite good, but let's have a look at the, oh, what, why does this appear? Huh. Very strangely. Okay, well, don't mind. Okay, this is better. So for the absorption, the correspondence between the first principle and experimental energy is, as you see, quite, well, very good, a small deviation, small fluctuation. For the emission, it is also quite good. And the Stokes shift is a bit less good, but still trends are accurately well, the average is well obtained with some outliers nevertheless. The Doornbos model do not work as well, especially because already at the level of the absorption and emission, there is a large spread of value, and globally at the level of Stokes shift, it is not predictive. As I have indicated, one might actually correct by hand for the small error that we are making. Also at the level of the Stokes shift, this might be corrected. And the statistical analysis might be done on all these data, computing, for example, the mean relative error or the mean absolute relative errors. In percent, we are at the level of 5 or 6%, while the semi-empirical errors can be much, much larger. We did this also for not only for the cerium doped material, but for the europium doped materials, also with a very satisfactory set of trends and quite good predictive behavior, which is represented here. Now, I will finish my presentation. So I think I have convinced you that it is possible to have some predictive power to find some indicators that are not really basic, because the basic band gap does not help very much in the prediction of the emission and absorption energies. And Stokes shift that are all very important. Now we have pursued our investigation, trying to obtain a better description of the emission width and thermal quenching of these material. I will really go very fast in this part. The width of the emission can be obtained by the following representation. You see, when we have an emission going from this level to that level, if we do not start from this geometry, but from that geometry or from that geometry, we observe naturally a spread of energies that will be seen as a shape which is a Gaussian-like with a full width at half maximum here. And actually, indeed, the system, due to quantum fluctuations and temperature fluctuation, will emit from this different region of the configuration coordinate model. So this is a representation of the first principal calculation and experimental data for the width. And you see that for most of the materials that are represented here, we are within 25% agreement between first principle and experiment, with unfortunately some outliers, but still it is relatively predictive. We can also compute the shape and shift of the spectrum. We did it for recently discovered phosphor, also using the one-dimensional configuration coordinate model, but also beyond. And you see that the theoretical behavior for different temperature between 300 Kelvin room temperature and 500 Kelvin operating temperature is in rather good agreement with the experimental data. So this is also quite encouraging that one can produce good data. The thermal quenching was also investigated. There are two models for thermal quenching. The first model considered that there will be non-radiative recombination between the 5D and the 4F if this electron first go to this place where the 4F and 5D bands or level crosses, and so naturally there will be only emission of phonon to go back to the lowest level. The other possibility is that the electron goes to the conduction band minimum, it becomes delocalized, and then both the hole and the electron might travel and meet a so-called killing center, where they will also emit their energy without emitting any photon. What we did is actually to compute the difference of energy between this level and that level in the 1D model, but also beyond. Okay, we did this, and I will not describe the detail. I think at this stage I'm done with my presentation. To summarize, it is established that the most efficient white LED are phosphor-based, the most efficient, but also the most economical. It's not a blend. Well, okay. It is obtained by down conversion of blue light, but one needs really to optimize, and there is ongoing research at that level. The emission spectrum of the phosphor, the excitation spectrum, the quantum efficiency, the optical characteristics at elevated temperature. The best dopant ions are cerium and europium in some doped inorganic host that can be taken in a very large source space. because these ions give a tunable 4F to 5D transition represented by this Doornbos model. I have shown you how we can indeed address the prediction of properties like emission spectrum, quantum efficiency, thanks to first principle methodology, the absorption emission, the Stokes shift. This has been done for more than 30 materials, and it's actually not very costly to obtain for one material the total energy that I have shown you. It's a couple of hours of calculation on 50 cores. That's enough. We outperform the semi-empirical methodology that is nevertheless useful to get physical insight, and one can even predict the width, the temperature dependence, and the thermal quenching. So we are waiting at some stage to be able to predict new phosphors that might bring an added 20%, 30%, perhaps more efficiency to the lead that might be used in everyday life. Thank you for your attention.
Thank you, Xavier. We have a couple of questions in the chat, but I would also allow myself to ask one maybe stupid question. How well does the structure prediction using the standard simple DFT methods like PBE and like with no corrections work for the F elements? Can we, well, speaking of USPECs, can we use USPECs with our standard functionals to predict the structures containing these elements?
Oh, yes, I think that materials that contain cerium,
Sorry,
europium.
excuse me, just for the very basic, not the excited states, just the ground state stable geometry.
Yeah, the DFT plus U is indeed quite powerful. There is a part of semi-empiricism in the choice of the U parameter, but in the materials project, you know, there you can find 100,000 band structure that have been computed. They include a lot of rare earth containing materials. The people from the materials project had to find some rule to select which U value has to be used. But yes, in general, it is quite powerful, this technique, DFT plus U. You might have some trouble only when it comes to materials in which you have really not static correlation, but more mixed correlation that is present. For example, cerium, just straight metallic cerium, will have a phase transition that is not very well described by DFT plus U. You have to rely on DMFT to obtain correctly the two phases of cerium. But the percentage of materials that have such characteristic is very small, I would say, even if there are a lot of them. But you know, the space of material is so large that indeed there might be a... So for this search of on phosphor, we do not expect to have any problem with that kind of
phosphor, of course, yes. But it's just that I saw a lot of GGA potentials for these atoms, and that made me curious. For example, we can put, well, for example, in VASP, we can put potentials for Syria. And the structure that we get, is it absolutely nonsense, or it has to do something with reality? Apparently so you have to include U or some corrections that...
Yes, indeed. Just GGA plus PBE will not give good structure. You have to work with DFT plus U.
Yeah.
Now, well, let me be a bit more specific. If you are interested by properties of these materials that have, for example, 4F electrons, but for which you do not care about these 4F electrons, you might say, for example, I want to deal with europium 2+, and the 4F electrons have to be frozen. Then, of course, you do not care about a U value, and the pseudo-potential, such pseudo-potential might do the work that you want it to do. And actually for ab init, we have indeed the pseudo-dojo, a set of pseudo-potential that exist. And if the people are interested in such frozen 4F state for the rare earth element, we provide such pseudo-potential in which there is no F4F electrons at all treated explicitly. It's just the 5D scattering potential that is present.
Okay, I see. And so, and what about heavy D elements? They are also not well described by the GGA. What do you think?
As you say, GGA alone is definitely not able to describe correctly the uranium, well, all the actinides. At that level, what I said about the relevance of DMFT is even more important, because with the plus U, I think you can still obtain many materials that are correctly described with a plus U. But if I remember correctly, the amount of materials that in which you have fluctuating valence is bigger with the 5F than with the 4F electrons.
Okay, thank you. We have a few questions from chat. Do you like to read them by yourself, or I can read it for you? Or we can ask participants to... Actually, participants can unmute themselves, as far as I know, and you may ask by yourself.
Yes, perhaps I will start from the bottom, the later questions, because it will be easier. First question, I have a question about delta ICF method. Do you avoid variational collapse to the ground state when relaxing your excited state structures? It happens that for all the materials of interest in our search, the delta ICF works very well. You're right that it might spontaneously enter a instability, the delta SCF method. When you start to occupy a state and below which there is some unoccupied state, you might at the self-consistency level start to oscillate between occupying different levels. But in this case, the 5D and the 4F levels are really well defined, and we do not have observed any problem with the delta SCF method. Yeah. I hope this answered the question. Julian Beltran asked, then there are experimental measurement of the energy absorption and emission when cerium is substituting a lanthanum 2A or lanthanum 4C site. While for the lanthanum 4C, there is some experimental evidence of emission, why there should not be. Another question, what are the primary source of incompleteness for the 1D model you discussed? Experimentally, they cannot distinguish between the lanthanum 2A or lanthanum 4C. They just observe emission, no more than this. The study that I have shown was simply to try to understand whether both sites were emitting, whether there would be a widening of the emission because of both occupations, and if there was only one side emitting, which one was emitting, and so yes, this is what I want to answer. Valencia Kadome, well, Hubert Valencia asked, how did you involve USPEC in your calculation? No, USPEC was not involved in these calculation. I guess I was invited to present to make a presentation here in order to see the future possibility, the future challenges of USPECs in the domain of optical properties. To my understanding, it is still very limited. The number of investigation of optical properties based on USPECs. I don't know whether I can get confirmation from the organizers, whether Vladimir, what do you think?
I remember that at some point, I might be wrong, but I thought that Abonit was coupled with USpecs, not
Yes,
in terms of
indeed. I mean, it is
optical
completely
properties, but not for optical properties. But I think that these calculations that involve some many electron effects, they are very costly computationally. So usually we do like this: we find the stable structure in some very simple approach, which allows us to like pick a lot of generations and candidate structures, and then we take, well, say all the structures that fall into the range of 1 EV, for example, 100 structures, and then we do the like more exact calculations using this approaches to like DFT plus U or something.
Yeah. Okay. Well, this in part answer also the next question that I read. Rodrigo Castillo asked whether there is any possibility to interface Abinit code to USpec. As was mentioned by Artyom and by Vladimir just now. Indeed, Abinit is interfaced with USpec. It was done well one year ago, basically. Okay, next question.
There is one more question, the last question on the bottom of the chat.
Yes. Yes, the question whether RDMFT, reduced density matrix DFT, could be an alternative theory to DFT plus U. I'm not sure of what is the status now of reduced density matrix DFT. It was pushed, I would say, between 5 and 10 years ago in the group of Hardy Gross. But is there anybody really practicing reduced density matrix DFT nowadays? I'm not able to answer this question.
Okay.
Yeah, there is indeed another question: why the core-hole interaction in the single particle level works so well? Yeah, it is a specific case. I know that one should do Bethe-Salpeter calculation in principle, but since we have very well identified state for the electron and state for the hole, the electron state is the 5D and the 4F is for the hole. Even if we were trying to use the Bethe-Salpeter equation, I'm pretty sure we would obtain that the correlated system between electron hole that should indeed describe the probability to have different electron hole pairs with each coefficient, like is done in the Bethe-Salpeter equation. I'm pretty sure that 99% of the excitation from Bethe-Salpeter equation would simply be 4F to 5D. Okay, so this is the answer to Biplap Sanyal. Then Alfonso Gallo mentioned, I think it is about our reduced density matrix functional theory. He mentioned that he couldn't get good results, and the idea is kind of that. No, yes, this might be true. Last question. No, is it possible to apply the approach presented to model the emission for undoped band-to-band transition when the electron and hole are not localized at some specific atom? I think the delta SCF for solids, undoped solids, is very bad. There is no hope to use it to get good predictions. One should use Bethe-Salpeter on top of GW calculations. Now, there are some alternative techniques like TD-DFT to predict excitation spectra. I have a mixed feeling with respect to TD-DFT with some good kernel, even with some good kernel, with respect to the predictive power of TD-DFT. It's a nice theory, But I think that the predictive capabilities still might not match what is really needed to obtain good predictions. I think, of course, then one should avoid doing beta-salpeter calculation as much as possible and try to rely on first indicators, lightweight indicators, like the effective mass, well, a characterization of the conduction band minimum, characterization of the valence band maximum, the dielectric properties. The first search should be done on the basis of light, easy to compute indicators. Yes, at variance here, I think the message is more, we have the possibility to do a light calculation in supercell, in DFT, that are rather predictive. And on the other hand, we can see that the relevant indicators might not be bulk values. It might have to do something with the real place where the dopant atoms are. But with the computing power that is really, that keeps increasing, if not the frequency of the processor, but simply the number of processors that we can use cheaply, I think a real search with few specs plus coupled to other first principle calculators it is amenable to, it is workable. It is realistic nowadays.
Okay, thank you. I think we have next presentation coming. Thank you very much, Xavier. And our next talk is by Alexander Kvashny. Sasha?
Yeah. Hello, everyone. Let me share my screen. Okay. So, good afternoon, dear colleagues. Now let me give you a talk about the search for materials with optimal properties as a part of our USPECH school. And basically, my talk will be divided into two parts. First part is devoted to search for new super hard materials with optimal properties for some industrial applications, and the materials which I will talk about mainly based on the binary transition metal borides. And the second part of my talk is devoted to superconductivity, to high temperature superconducting hydrides, metal hydrides, which are stable at high pressures and possess really high critical temperature. So let's start from the super hard materials. Nowadays, there are many different materials developed, and basically we can divide all these hard and super hard materials into several parts, several classes. One class is devoted to diamond and cubic boron nitride, and they are super hard materials with the hardness of about 100 GPa for diamond and 60 GPa for cubic boron nitride. So they're really hard, but the main disadvantage of this material, which limited their practical application, is that to synthesize both of them, we need to apply a pressure. So this really limits the application and increases the cost of the synthesis of such material. Another class of material devoted to transition metal carbides and nitrides, and the best examples are tungsten carbide, titanium nitride, shown here. They are really widely used. To synthesize these materials, you don't need to apply high pressures, you need only apply high temperature, which is a big advantage, but the main disadvantage is that they possess quite low hardness for wide applications. And the second class of materials is devoted to transition metal borides. So here you can see titanium boride, titanium diboride, and chromium tetraboride shown here. To produce these materials, you also don't need to apply high pressure, you need only the high temperature, and they possess really high viscous hardness, about 50 GPa. So the perspectives of using these types of materials are really wide in different industrial applications, again, because of the ease in synthesis and production. the only high temperature. Most of these materials have high melting temperature, which is also useful properties, and high hardness. And due to these characteristics, you can use these types of material for different protective coatings, different equipment, but the main field of application of these materials is uh, industry, is gale and oil. For example, in the drill bit cutters, so you can see here example of a drill bit, and nowadays here is a cross section of drill bit. You can see that exactly the cutter of this equipment is based on the polycrystalline diamond or cubic boron nitride. Then the base of it is based on the on the tungsten carbide. And the main direction of development in this field of technology is replacement of traditional materials like diamond and tungsten carbide by new ones with improved physical properties. And the most prospective system for this study is tungsten boron system, because this system was studied during the last 60 years, and there are many different experimental studies which devoted to synthesis of different superhard compounds, and the highest hardness is devoted to material with preliminary composition of tungsten boron 4. It is preliminary because there are many theoretical studies which are reported about the compositions of this material, which varies from tungsten boron 3 to tungsten boron 12. And here you can see different models of these compounds. And due to this controversial data about the crystal structure of this high tungsten boride, we cannot distinguish the physical properties. We cannot precisely calculate the physical properties. And this uncertainty also indicated in the high temperature phase diagram of tungsten boron system. You can see this region where there is a region of high tungsten boride, is tungsten boron 4, and it's denoted by a dashed line, which means that the crystal structure and some fields of stability is still unknown. So to solve this issue, we performed a variable search for stable tungsten boron compound using Uspech algorithm. And here you can see the constructed convex hulls for tungsten boron system, where you can see many different phases which are stable at zero temperature. We also calculated the convex hull both without 0-point energy contribution to free energy and with 0-point energy contribution. Here you can see that we predict new phase with the composition tungsten boron 5, which is slightly metastable. You can see here that the point located a little bit higher than convex hull, but if we calculate the enthalpy of formation with 0-point energy contribution, you can see that it lies directly on the convex hull and it becomes thermodynamically stable. And this is unique material because, again, structurally it contains all the flat graphene-like layers of boron and the layers of tungsten, where the some tungsten atoms are replaced by the boron triangles shown here by orange color. And this compound has unique mechanical properties with the weakest hardness of 45 GPa, which is really high, and thus it can be used for different practical application instead of known materials. Then, of course, we study temperature stability because all the real application of materials, they are carried out at room temperature or even higher, especially in the mining industry, right? So we studied temperature stability of all predicted phases of tungsten boron system. You can see here tungsten boron 5. It is stable in the whole studied temperature range until 200 and 250 kelvins. And thus the wide temperature range of stability of tungsten boron 5 makes it a perspective material for big number of applications together with high weakest hardness. And for successful application of material in different types of industry as a superhard material, it's not only useful to use material with the highest possible weakest hardness. Another important property as fracture toughness also should be high. So we perform the optimization of these two properties of studied tungsten boron compounds or predicted tungsten boron compound, and plot here so-called HB plot in the coordination of weakest hardness and fracture toughness. And here you can see our tungsten boron 5, which has really high hardness compared to chromium boron 4 and relatively high fracture toughness, higher than for known systems, which shown here by blue color. And these materials locate in the same Pareto front. If we are talking about the Pareto optimization, we can construct the Pareto front. It lies between chromium boron 4 and tungsten carbide, and our new material lies directly on it, which again confirms that this material is display really optimal properties within weakest hardness and fracture toughness. Then, as we have calculated data about crystal structure, physical properties, stability, and even temperature stability, we use this data to experimentally synthesize our material, and then in collaboration with High Pressure Physics Institute of Russian Academy of Sciences, we use the high temperature sintering of boron and tungsten nanometer sized powders and synthesize the highest tungsten boride. And we actually developed a technology how we can produce such samples of our material in a large scale, and we test the micro hardness, the weakest micro hardness of synthesized samples, and found that here, if you look at this graph, you can see that weakest micro hardness of tungsten carbide alloy with the cobalt, it has the average hardness of about 22 GPa, while our two samples, first sample was made using the high temperature sintering of the powders, and second sample was made using the arc melting, and they both have a higher weakest hardness compared to tungsten carbide. Even the arc melting sample has weakest hardness of 35 GPa, which is 50% harder than tungsten carbide. And again, I repeat, the tungsten carbide is a widely used material in the mining industry. So it means that we predict and develop the technology for synthesis of new material, which is harder than tungsten carbide. But the main issue and main challenge comes from the crystal structure, because we need to directly define the crystal structure. And if we compare the simulated and experimental X-ray diffraction patterns for tungsten boron 5, you can see here that on the experimental picture, on the theoretical picture, we can find some additional low intensity peaks, which means that our orthorhombic structure, that our orthorhombic structure has lower symmetry than that material which we synthesize. And it also means that synthesized material should be non-stoichiometric with disordered structure. So we need to consider some disordered structure in order to understand the composition and physical properties of our material. To do so, we propose several models for structure refinement shown here. One of them has a composition tungsten boron 4.18, another tungsten boron 4.86. They are shown here. They both have hexagonal symmetry, as was proposed by our experimental data. And then if you compare the experimental X-ray diffraction pattern with simulated ones, you can find that tungsten boron 4.18 describes the experiment better than other models, as well as our orthorhombic structure. So based on this data, we can conclude that crystal structure of our synthesized structure is disordered, and composition may vary from tungsten boron 4.18 to tungsten boron 4.86. Then, as we have average models of our crystal structure, based on them, we can construct local structures in order to calculate enthalpy of formation and study physical properties and stability. So we did this, and here you can see the boron-rich part of the convex hull. Red triangles shown our structures, which we constructed based on our models. And you can see here that the lowest enthalpy of formation is devoted to tungsten boron 4.2, which structure is disordered, and which this data confirms our experiments. But in order to understand the precise composition and calculate the energy of structure which is fit better our experiments, we need to study all possible composition with a range from tungsten 0.3 to tungsten boron 5. We cannot do this with DFT because it requires the construction of big supercell with big number of atoms, and we totally cannot do this. But we proposed a lattice model and developed a lattice model which allows us to estimate the total energy of different supercells of our material. So each side of this lattice model consists of either boron triangle or tungsten boron 3 structure unit, and then by changing the arrangement of boron triangles and other structural units, we can construct big number of different disordered local structures. And using this equation, this formula, we can easily calculate the total energy. All the parameters of our models were fitted based on the DFT calculations, and then we can perform the direct search for the most stable composition which will correspond to optimal arrangement of the boron units in the wide range from tungsten boron 3 to tungsten boron 9. And we did this, and here you can see the boron-rich part of the convex hull, where blue points were calculated using our latest model. And you can see that a big number of different structures located very close to the convex hull, which confirms that during the experiments, the structure with different composition can be formed, which also confirms the disordered nature of our samples. And here you can see some examples of lower energy structures. And the main structural feature of all these structures that the boron triangles, which are shown here, they are almost uniformly located in the volume of crystal, which decrease the energy of this phase. Then we try to study the thermal stability of this model, even of this tungsten boron 4.2, as it has lowest energy compared to other phases. Here you can see the convex hull evolution with the temperature. So this is convex hull constructed for 500 Kelvin, this for 2000 Kelvin. You can see that increase of temperature leads to stabilization of tungsten boron 4.2 and also leads to stabilization of tungsten boron 5. So at low temperatures it's metastable, at high temperature leads to its stabilization. Thus, we showed that at high temperature the probability of formation of disordered structure with composition tungsten boron 4.2 is the highest, which confirms again our experiment. Then we didn't stop only with these systems. We tried to study another transition metal borides, and not even borides, carbides and nitrides, in order to optimize the most important properties for hard and superhard materials, which are viscous hardness and fracture toughness, and plot a treasure map of superhard materials shown here. So this map directly shows you which material you should try to synthesize in order to obtain material with properties which you desire. For example, if you'd like to get some material with the highest possible fracture toughness among transition metal borides, you probably need to look at the rhenium diboride. Unfortunately, rhenium is quite expensive material, so maybe you need to look at some cheaper material, but with a little bit lower properties, for example, tungsten boron 5. So these maps give a crucially important information for experimentalists who are working in the field of superhard materials, because you don't need to try materials one by one in order to understand which material you'd like to obtain. You need just look at this map and decide which material you'd like to synthesize. Now let me move to the second part of my presentation about the superconducting materials. So nowadays there are two different types of superconducting materials which are widely used in different applications. One of them is high temperature superconductors of generation 2, which are mainly based on the composite cuprates, and the technology of the fabrication of ribbons of different multi-layered composite is well developed, and the critical temperature for these materials is about 100 kelvins, but they are really expensive, and their mechanical properties also limit the widespread applications. Another type of materials are conventional superconductors, and the best example of these materials is magnesium diboride. So there are several methods, well-developed scheme how to produce a magnesium diboride superconductor in large scale, and it's quite cheap, but unfortunately the critical temperature is not as high as 30 kelvins, which also limited some application. And the big challenge is to find material which will combine a high critical temperature and will be quite cheap compared to magnesium diboride. And if you look at the progress in development of superconducting materials, you can see here that at the beginning of 20th century, there is conventional superconductors based on simple metals were developed. Then a big step in superconductivity devoted to development of cuprates with the highest critical temperature about 170 kelvins, which approach at the pressure about 30 GPa. But the most interesting part is devoted to these 2 points. They are hydrides, as Artem told in his speech. And these 2 materials is H3S and lanthanum H10, which were predicted and synthesized recently. And again, I will repeat that this big study of metal hydride started from the prediction of H3S superconductor in 2014. Then 1 year later, this material was experimentally synthesized and critical temperature of 203 Kelvin was confirmed experimentally. In 2017, there was one theoretical paper where the 2 systems of lanthanum and yttrium hydrides were predicted to have nearly room critical temperature of superconductivity. And then in 2019, 2 independent experimental observations were published where the lanthanum H10 was synthesized and critical temperature was about 250 and 260 kelvins. And we also try to do some computational search in this field using our evolutionary algorithm USPECH. And we perform a search for the stable thorium hydrides, as thorium has similar electronic properties with lanthanum, and we suppose that it should possess high critical temperature. So using variable composition search, we predicted the high pressure phase diagram of thorium hydrides. Here you can see big number of different hydrides predicted which are stable at different pressures, even thorium H4, thorium H6, H7, and the most interesting one is thorium H10, which has a cubic structure, and it's as a structure to lanthanum H10. It's dynamically stable and thermodynamically stable at the pressures higher than 100 GPa. And again, this pressure is about 2 times lower than for lanthanum H10, because lanthanum H10 is stable at the pressure higher than 170 GPa. Then we studied superconducting properties of this material and calculated dependence of critical temperature on the pressure and found that it can display superconductivity at about 220 kelvins at the pressure close to 100 GPa. Well, what's this? Yeah, then again, as we have data about crystal structure, field of stability, and all physical properties about this compound calculated using density functional theory or other method, we try to perform the experimental synthesis of this material in the European synchrotron radiation facility in the high pressure diamond anneal cell, which scheme you can find here. And we actually predict thorium H10 at the pressure of 183 GPa and temperature 1800 kelvins. Here you can see X-ray diffraction patterns, which perfectly match with our theoretical results. So thus our computational result was totally confirmed by experiments. However, we are not only synthesize this thorium H10, but we synthesize all previously predicted hydrides, thorium H6, thorium H4, even the phase transition between 2 thorium H4 phases. But also we found some puzzle in this equation of state, you can see here we measure some points which we cannot identify using the data about predicted phases. So thus we need to perform additional computational search, additional investigation in order to understand which structure do we synthesize. We performed additional search in the pressure of 150 GPa and found that if you will look at the hydrogen-rich part of the convex hull, you can see here that thorium H10 is stable, while thorium H9 is metastable. And if we will include 0-point energy contribution, the red line, you can see that it stabilizes thorium H9. So 0-point energy contribution is crucially important for description of stability of metal hydrides under pressure. Then we calculate the equation of states of thorium H9 and find that it's perfectly matched with our experimental data. And then we can put here our new phase thorium H9 in our phase diagram, which we miss because previously we considered only stable phases without contribution of 0-point energy. And thus, in our future works, we usually require to study this stability within the temperature contributions. Then we investigate superconducting properties of thorium H9 and found that it is a high temperature superconductor with a critical temperature of about 140 kelvin, which is stable at the pressure of 100 GPa. And after the theoretical calculation, we need to confirm our data by measuring the superconducting properties. Here you can see the dependence of the resistance of the temperature for thorium H10 and thorium H9 at without magnetic field and in strong magnetic fields. And our experiments confirmed the superconducting nature of these two hydrides. And the measured critical temperature was about 159 kelvins and 146 kelvins for thorium H10 and thorium H9. So let's then look at our periodic table and put here which compounds do we know that are high temperature superconductors. So it's definitely H3S, which was synthesized and theoretically studied. Then it's H3P, which was experimentally synthesized at the critical temperature 100 Kelvin. Then we can put here theoretical study of yttrium H10, and then some others, including the lanthanum H10, our thorium H10, cerium H9, which Artem talked about at his lecture, and also we studied, synthesized, and predicted critical temperature of uranium hydride. But still, we have lots of gaps in our periodic table, which we need somehow to fill out. So we studied the hypothetic actinium hydride. So it's not possible to study actinium hydride experimentally due to the radioactivity of these elements, but we can study them theoretically. And we predicted that in actinium hydrogen system, even at not so high pressures, we can find a big variety of different hydrides, even actinium H10, actinium H12, and actinium H16, which display high temperature superconductivity about 200 kelvins, and they are stable at the pressure about 150 GPa. Then we moved to neodymium hydride. We predicted big number of different hydrides which could be stable. It's neodymium H4, H9, H7. And with our Chinese colleagues in Jilin University, we performed experiments and synthesized this material. Unfortunately, yes, all of them have antiferromagnetic ordering, even at really high pressures. Thus, they are not a superconductors, even not a high temperature superconductor, but this is the first case of magnetic hydrides at high pressure known to date and synthesized. Another example is the barium hydrides, where we synthesized and predicted barium H12, study their stability theoretically, and perform measurements of superconducting properties. Unfortunately, due to the molecular nature of this metal, this material is not a high temperature superconductor with a critical temperature about 20 kelvins, but this is again the first example of another structure rather than high temperature superconductor hydride. So now we have information that metal hydrides cannot be only the high temperature superconductor, they can be magnetic or even they can be molecular crystals. So what is next in the investigation of high temperature hydrides? Do we need to test hydride systems one by one across the periodic table in order to understand which compound has high critical temperature, which is not? So basically, it's not necessary because we can predict critical temperature for all possible hydrides of all elements from periodic table. Yes, we can do this, as I said, and as Artem said in his lecture. So we combine all the results about the DFT calculation of different hydrides. We perform statistical analysis and develop the neural network in order to predict critical temperature and other superconducting properties of different hydrides across the periodic table. And this map you can see here, from which you can easily understand which part of periodic table is the most prospective for future experiments in high temperature superconductors. This is this region of the second, third, and fourth groups of periodic table where you can find this compound. Again, this information is crucially important for experimentalists because now you don't need again to test hydrides one by one in order to find material with the highest possible critical temperature. You need just to look at this picture and find that I need go to synthesize strontium hydride or calcium hydride, lithium. I don't need to go to this region because we cannot find any good materials here in terms of superconductivity. And again, what's next? We need to move to search for more complex compounds, as shown by the recent publication in Nature, where in the carbon sulfur hydrogen system, there is a room temperature superconductor was synthesized at really high pressure, but still the crystal structure is unknown. And maybe in other ternary systems, we will find really good materials with the highest critical temperature. And in this topic, you should listen to the lecture of our colleague, Dmitry Semenok, which will be November 13th. And that's it. I'd like to thank my colleagues listed here. I'd like to thank Russian Science Foundation for financial support and other organizations, and you for attention.
Thank you so much, Sasha. I cannot see any questions. I can see one. Sasha, there is a question in the chat. What was 1800 Kelvin in case of thorium hydride 10?
It was the temperature at which we synthesize this material. So we compress the samples which were made of thorium, and the hydrogen source compresses up to 183 GPa, and then use the laser beam to heat this sample. And this is the temperature. Cannot see chat.
Well, I think that this is pretty much it for this session. Thank you very much again, Sasha, and thank all of the participants who joined us today. And okay, so there is another question here.
Okay, can you please give an idea about how temperature effect is considered in tungsten boron 5? So in tungsten boron 5, we use the quasi-harmonic approximation in order to take into account temperature contribution. We just calculate the phonon density of states, then using the integration over it, we can calculate the Helmholtz free energy and calculate the Gibbs free energy at different temperatures. And we also use anharmonic approximation, which requires additional terms. Yeah, but the data are almost similar of quasi-harmonic approximation and non-harmonic approximation. So this is the most widely used way how we can deal with the temperature right now.
I see.
And no, temperature contribution was not calculated using USPEC. It was calculated separately for each phases on the convex hull and for each metastable phase, because it's quite resource consuming, so you cannot do it right now using the global optimization.
Yeah, but actually there is an approach developed by Ivan Kruglov, whose talk will be in the next session, who is developing actually consideration of temperature during the calculations. Okay, dear friends, I think this session is over, and we'll see you in about hour and a half. Please don't forget to state to have your name clearly stated in your Zoom account, and see you in hour and a half. Thank you.
Can I also please ask the participants not to leave the Zoom meeting because it takes time to admit everybody. If you have such an opportunity, just stay in the meeting, please. Thank you.
Thank you. Okay, see you.
Okay, so I'm going to talk about our recent developments for coevolution research for materials with optimal properties, and also briefly about multi-objective optimization, which is very important for optimizing materials which with multiple properties. So this work is supported by Russian Science Foundation and is based on these papers. Okay, the objectives of this work is first to solve the challenging and the main problem of material science, which is predicting optimal materials for given properties. And second, we need to make sure that our predicted materials have a high chance to be synthesized. We are not looking for unrealistic materials which are only perfect on the computers. So since such searches are huge, we need to find a way to reduce the time and computational cost of our calculations and searches without significant loss in the results. And finally, we would like to have an automatic and unbiased search for hard and super hard materials, and once forever, unempirically, using our method at least, find the answer for the question if diamond is the hardest material in nature or not, and are there any other super hard and hard materials that we need to discover or not. So in this talk, I'm going to introduce our Mendelevian search and tell about some of the important submethods that are implemented in our Mendelevian search. At the end, I will show the results of our Mendelevian search for hard and super hard materials, basically binary systems. In this talk, whenever I say materials, most of the times I mean only binary systems. So under zero pressure. So looking at this picture, one can see that up until 2013, only 72% of binary systems, 16% of ternary systems, and less than 1% of quaternary and more complex systems have ever been studied. Among those studied systems, every day we are witness of new discoveries. So that means that there is a big room for discovery of new materials. All of you know that it is essential to have the crystal structure of a material for calculating the properties and computational study of the material. So by having the crystal structure of the material, we can use ab initio codes to calculate the energy and properties. But these ab initio codes do not generate a new structure for us. for generating a new structure, we need to use structural search methods. These structural search methods generate a new structure, give it to ab initio codes, and get back the energy and properties. And using their powerful algorithms, like evolutionary algorithms, they try to make a better and better structures during generations. If we call this process aspects, because this is what aspects does, basically aspects needs two main input file, which material and what properties. And at the end, it will find the most optimal phases and structures of a given material regarding the given properties. But what if we don't have the material? For example, we are looking for the hardest material, whatever it is, or we are looking for good thermoelectric materials or materials with high magnetization. This is what Mendelian search MENS does for us. So the input of MENS is desired properties, and it will find for us the most optimal materials regarding to that properties. So in the title of my talk, I mentioned coevolutionary search, and I need to clarify what is coevolutionary. So, and what is the difference of coevolutionary algorithm and evolutionary algorithm? So basically, evolutionary algorithm is in evolutionary algorithm, we are talking only about one kind of species, while in coevolutionary algorithm, we are talking about more than one kind of species. Let me just make this like, okay. In coevolutionary algorithm, we are talking about more than one kind of species in which these species have influence on each other. So these gentlemen here are the best individual in their own species and came here to compete and understand which one is the best individual overall. So we can define coevolution as joint evolution or evolution of evolution. But the heart and central core of every evolutionary and coevolutionary algorithm is latent in its variational operators, the place that we make a new individual, a child. In evolutionary algorithms, it is easy to understand what is the child of two giraffe or two structures. But in coevolutionary algorithm, it is a little bit more complicated. What is the child of these two gentlemen or these two material? Obviously, the child should be similar to its parents. But how to solve it? For solving this problem, we need to design a space, a map, which is based on the similarities of materials. So materials with similar properties have some relation to each other, for example, are sitting next to each other. We took the idea from the chemical scale and Mendeleev number that was suggested by Petitfor in 1984 for the first time. He suggested if we change the order of elements to another sequence rather than atomic number, here is the order of elements or so-called Mendeleev number that he suggested, we can get a map of binary systems in which binary systems with similar structural type are sitting next to each other on this map. But Petitfor found his chemical scale and Mendeleev number empirically. He mentioned that he used valences, electronegativities, and atomic radius to obtain this sequence of elements, this Mendeleev number. And since this is an important part of our model, we didn't stop there and try to redefine our own Mendeleev number. For redefining our own Mendeleev number, we used several important works. One of them is Goldsmith's law of crystal chemistry, which states that crystal structure is determined by stoichiometry, atomic size, and polarizability of atoms and ions. Later in 1932, Pauling introduced the concept of electronegativity. And in 1955, Ringwood added the modification to the Goldsmith law of crystal chemistry by adding electronegativity as another important parameter for determining the crystal structure. In 1990, Nagel showed that electronegativity and polarizability are strongly correlated, and only one of them can be used. So from these important properties of elements, we only took electronegativity and atomic size or atomic radius for redefining our own Mendeleev number. We plotted the elements in the space of atomic radius and Pauling electronegativity. And you can see these properties of elements in this space. There is a correlation between these two properties. Although it's not a linear and nice correlation, but it's a correlation, although crudely. So we projected the elements, these points, on this regression line of the elements. And the first element were given to the first element, the first Mendeleev number was given, and second Mendeleev number was given to the second projected element on this line, and so on to the last element. At the end, when we plotted the correlation of our Mendeleev number and Pettifor's Mendeleev number, we saw that actually these two Mendeleev numbers are very well correlated. There are some differences, especially in the beginning for these elements, but generally we have a good correlation. And these elements correspond to noble gases, which we found Mendeleev numbers for these elements, just like other elements using our method that I just explained. But since Pettifor found his Mendeleev number empirically, he preferred to put all noble gases in the beginning of his Mendeleev number. So that can be a reason for that. But we need to understand that if our Mendeleev number works as good as Pettifor Mendeleev number or better than that, because that is important. So for that, we plotted the chemical space, the Pettifor map, for our results of searching for hard and super hard materials, and using atomic number, periodic number, Pettifor's Mendeleev number, and our own Mendeleev number. And it turned out that our Mendeleev number indeed clusters materials with similar properties better than other Mendeleev numbers. It does not produce a periodic patchy pattern like atomic number, and also it clusters materials in a smaller area in the chemical space, which is very important for reducing the time and computational cost of our search for optimal materials. But the point here is that if our Mendeleev number, which was obtained using the correlation of crudely correlation of electronegativity and atomic radius, if this Mendeleev number works so well, so of course, if we go back to the space of initial parameters, I mean atomic radius and electronegativity, we will get more precise and more accurate results. So that space, the space of electronegativity and atomic radius, is the space that our variational operator, the heart of our coevolutionary algorithm, works. I will get back to that in a couple of slides. But here, let's see if our Mendeleev number work also good in other properties and not just hardness. So for that, we plotted the Pettifor maps, the chemical space, for a number of different properties: hardness, magnetization, enthalpy of formation, and atomization energy, using different sequence of elements or Mendeleev numbers, atomic number, periodic number, Pettifor's Mendeleev number, and other suggested modified Pettifor Mendeleev number. and our Mendeleev number. Using naked eyes, we cannot understand which one of these maps are better than the other, because first of all, our eyes are not powerful enough to distinguish between some of these maps. And secondly, our minds might be biased towards some of these Mendeleev numbers. So we need to have a tool for evaluating these maps. But what we can see is that atomic number in all the cases produced kind of totally different map other than other Mendeleev numbers. Usually atomic number produced a periodic pattern, a splotchy pattern, which is not good and desirable for predicting of new materials, because materials with similar properties can can exist in different part of the chemical space. So for evaluating these maps, we use the clustering method, which was introduced in this nice paper in Science. Using this, the method that they introduced, we are able to find the clusters, cluster centers, and clusters. So we can find the number of clusters. Based on this method, which we can find clusters, we can define some approach for evaluating our Mendeleev numbers. Before that, let me explain what I mean by cluster. Cluster is a set of points that these points have similar properties and are next to each other. I mean, close to each other. So the distance between 2 points in one cluster should not be more than some cutoff radius, and the difference of their property should not be more than some property cutoff radius, which is shown by dp here. So the first approach for evaluating our Mendeleev number is simply number of clusters. A Mendeleev number that can produce a map with a smaller number of clusters is more favorable and better than a map with more number of clusters. And second approach is based on some ideal Mendeleev number. Ideal Mendeleev number is an unrealistic imaginary Mendeleev number that can cover all the systems in the minimum possible number of clusters. And we can find this minimum possible number of clusters by having the range of property and DAP. So in the second approach, the fraction of systems that can be clusters in the minimum number of clusters is our evaluation tool. Let's look at this example to for better understanding of this approach. So here we have two examples, number 1 and 2, and in both of them we have 25 points and 2 different properties, red and black. So we have 2 different properties, and we can cluster all the points here at minimum 2 clusters, one for red and one for black. So n a minimum number of clusters, NMin is equal to 2. And just looking at these 2 examples, by the way, we can understand that second example is much better than first example for clustering points. So let's see our approach, how it works. Using our first approach, which is basically number of clusters, we can see that the second example clusters points in 3 clusters, while in the first example, we have 9 different clusters, 7 clusters and 2 isolated points. So second example is better because it has less number of clusters. And using the second approach, the fraction of systems that are clustered using 2 clusters in the first example, 2 biggest cluster, contains 36% of all systems, while in the second example, the 2 biggest cluster contains 80% of all systems. So it has bigger percentage of systems included in these two clusters, and therefore it's better again. Okay, so these are the results for evaluating our Mendeleev numbers using the approach which I mentioned. On the left, we have evaluation based on number of clusters, and on the right, we have evaluations based on fracture of systems that are covered by minimum number of clusters. In almost all of these maps, you can see that atomic number is the worst one. It has the worst evaluation, which was expected. It was expected even initially. And for hardness, you can see that our Mendeleev number in whole range of DAP is the best among all Mendeleev numbers, which was also expected from the maps which I showed you initially. And for other properties, we can see that there is an up and down between different Mendeleev numbers, but they are very, very close to each other. And all of them can be considered to acting very good. And the evaluation for all of them is good. So based on all of these maps and all of these evaluations, I can say that overall our Mendeleev number works the best, if not one of the best, if not the best, one of the best, but I would argue that it's the best overall. And it can cluster materials with similar properties in different properties, totally different properties. So let's get back to our Mendeleevian search. I mentioned earlier that the heart of our Mendeleevian search is our variational operators, generally for any evolutionary and coevolutionary algorithms. And also I mentioned that our Mendeleevian search, in our Mendeleevian search, variational operators work in the space of electronegativity and atomic radius, which you can see here clearly for more precise results and better prediction of materials with optimal properties. So we have three variational operators in our Mendeleevian search: reactive heredity, chemical heredity, and chemical mutation. In reactive heredity, basically we took two parents, and a child of these two parents contains the combination of the elements of its parents. For example, A, B, and C, D are two binary systems, and a child can be AC, AD, BC, or BD. And for chemical heredity and chemical mutation, in chemical heredity, we have two parents, and children can be chosen from the space between these two parents. And there is a possibility that child, let's say that the point with closer distance to the parent to be chosen as a child. So in the chemical mutation, the same thing applies here, but we have only one parent. And the point with smaller distance to the parent has more possibility to be chosen as a parent, as a child. Here you can see the algorithm of our Mendeleevian search. So after defining the chemical space, the first generation is totally randomly. We select materials randomly from the chemical space, and then we give them to evolutionary algorithm USPECH. And USPECH finds the most optimal phases and compounds of those materials for us. And then we evaluate these results and rank them using multi-objective optimization, which I'm going to talk about it briefly in the next slide. And then we rank them, we find the best structures, and based on some possibility, they can be chosen as a parent for the next generation, for generating the offspring of the next generation using heredity and mutation and also random selection. So this loop continues until we reach some maximum number of generations until the calculation finishes. As I mentioned, we implemented multi-objective pair-to optimization in both USPECH and Mendelian search. So this is very important, and the reason for that is because in the real world, we usually look for materials which are optimal in more than one properties, materials that are good in more than one properties. And usually these properties are conflicting. This means that improving of one property of a material would end up to degrading the other property. For example, the body of this racket needs to be hard and strong, thermodynamically stable, and light at the same time to save energy. And being light and strong at the same time is kind of conflicting, usually. So for solving such problems, we need to have a method to obtain materials which are optimal in more than one property. Unlike single objective optimization, which we are looking for only for one objective, one property, and we can have one single best solution, in multi-objective optimization, it is possible usually that we don't have one single best solution, but we have a set of best solutions. And these solutions are shown by pair-to-France. You can see an example of pair-to-France here. So we tested our algorithm several times actually, and right now I would say that most of our calculations are using this multi-objective optimization. So one of the examples that is important and I'm showing here is searching for compounds of molybdenum and nitride. The reason that this example is important is because in 2016, when we didn't have this multi-objective pair-to method, our colleagues tried to find the most stable structures of this material using single objective optimization of USPECH. And this is the convex hull that they found for this material under zero pressure. So we calculated the same system using multi-objective optimization searching for low energy and hard materials at the same time to see if we can find all the materials that they found on the convex hull or not. And interestingly, we found almost all of them. We missed one here, but okay, you all know that evolutionary algorithm does not guarantee finding all the structures and all the results. So it is possible, even if you search for some materials using evolutionary algorithm using single objective optimization, it is also possible if you don't find that material. But on the other hand, we found another very, very low energy system very close to the convex hull that they didn't found. So we can say in overall that our implemented multi-objective pair-to method works pretty well, very good and efficient. And the good news is that at the same time, we not only optimized the energy, but also optimized hardness. So at the same time, we also looked for materials with higher hardness. And we found several materials, several hard materials that they had no idea about it. So this is very important and very powerful method, which I suggest people use in their calculation if they need. And it works very well, at least for two objectives. So in our Mendelian search, we need to understand if our Mendelian search works efficiently. For that, we need to track how our Mendelian search selects materials during the generations. You can see here the picture of our Mendelian search for hard and super hard materials and the procedure of system selection during generations. So in the first generation, when algorithm had no idea about the promising regions of the chemical space, every systems was selected randomly in the entire chemical space. But little by little, when algorithm learns about the promising regions in the chemical space, you can see that it started to focusing in those regions. And in the 10th and 20th generation, you can clearly see that most of the systems are selected from those promising regions. We had also another calculation using Mendelevian search for materials with high magnetization, and the same thing happens also here. So in the first generation, all the systems were selected randomly, but little by little, when algorithm learns about the promising regions of the chemical space, systems are mostly selected from those promising regions. And I need to mention that these contour maps at the background of this figure, of these figures, are obtained after the calculation was finished. And in the first generation, we had no idea about the promising regions of the chemical space. Here we can see how Pareto front was improved during the generations. So in the first generation, when we selected all these materials randomly, we had this figure for Pareto front. You can see that there are very small number of hard systems and very small number of low energy systems, basically no super hard and not very good systems, not many good systems. But later, when algorithm learns about the promising regions and focuses on the promising regions, it selects good materials. And you can see how Pareto fronts improved during these 10 generations. We have got a lot of low energy systems and a lot of hard systems, hard and low energy systems. And these numbers were even increased until 20th generation. And our algorithm found diamond as the hardest material in the nature. Some of the promising systems and structures that we found for hard and super hard materials are shown in this table. So you can see many different type of materials here, materials that have reported to be hard, materials that reported to have a potential to be hard, materials that have never been reported in the literature, and even materials that are usually soft. So for example, a compound of boron and sulfur is usually make soft structures, soft compounds. But our search suggests that it is possible to find even hard compounds in this system. Or this totally new system, manganese and hydrogen, was also found using our Mendelevian search, which we found a lot of hard and low energy, very symmetric structures for these materials, which is unexpected, and no one even thought about this material to go and study this material before. And this is the beauty of our Mendelevian search, because it gives you an unbiased search, and finally it gives chance to every system that have that can be potentially hard. So you can find any system without any, I don't know, biased mind toward any systems. In addition to these systems, we also found several hard phases of materials that have been reported to have a potential to be hard. Several new hard phases were predicted. And for those materials, for those phases that have already been reported in the literature, we have shown here the value of hardness using theory and experiment in parentheses and brackets for the sake of comparison. And you can see that in all of the cases, we have a very good agreement between the value of hardness that we calculated and the hardness that were reported previously in the literature. There is one exception for that in FEB4, that experiments suggest that this material is a super hard, but this has a long story. So after they suggested that this material is a super hard, many theoretical work started focusing on this material, and none of them reported that this material can be even potentially super hard. They, all of them, I'm talking about 4 or 5 papers, all of them mentioned that the range of hardness for this material is about 24 to 30, something about this. And our calculated hardness is 28, which is closer to theoretical values, which is obvious because we also use theory for calculating hardness. So if we plot the Ashby plot of hardness and toughness for these materials, which I showed in the previous table, we will get this map, this beautiful map. And in addition to those promising systems, I added to this map chromium nitride, chromium boride, and tungsten boride, which we indeed found all of them in this calculation and published in separate papers in JPCL into separate papers. And for better understanding of the hardness of these systems, here I drew the line of corresponding to the 30 gigapascal, which is for tungsten carbide, the main material for drilling tools. And you can imagine how hard is 30 gigapascal and how many systems and structures we found harder than 30 gigapascal. And these materials, chromium nitride, chromium boride, and tungsten boride, which we published in these papers, are almost lost among all of these materials that we found in one single calculation. I need to mention that this tungsten boride was published by our colleagues, and they found a very super hard compound of this material, tungsten boron 5, and it was synthesized, and you can see the sample of this material in the hands of Artem, actually scratching glass with it. So basically we searched for material, we found several hard and super hard materials, and we could even synthesize some of these materials. This is what we wanted. Still, we are looking, and we are sure that there are more super hard materials out there, but at the end we had very good results, very promising. We almost achieved what we wanted. And what is important, which I want to mention, is that during this one single calculation, we found almost all the materials that are reported to be hard and super hard in the literature during decades and centuries. So decades and centuries was briefly produced in one single calculation, the results of this period, which shows how powerful is our Mendelevian search. And we can use these methods in future, especially when we extend our models to machine learning models to reduce the computational cost and time for the calculations. It will be very, very useful. So to summarize my talk, at the first, we defined a chemical space using the most important properties of elements, electronegativity and atomic radius, which helps us to find a Mendeleev number that clusters materials with similar properties next to each other on the map of these Mendeleev numbers. And multi-objective Pareto technique makes it possible to search for materials which are optimal in more than one property, and it works very efficiently, at least for 2 properties. Combination of coevolutionary algorithm, multi-objective Pareto technique, and a well-structured chemical space, which is in the one package Mendelevian search, works very efficiently in searching for materials with optimal given properties. And our Mendelevian search suggests that diamond is the hardest material in the nature. So we have an unempirical answer for this problem, maybe for the first time. And of course, our Mendelevian search works at arbitrary pressure, and not only for binary systems, at least ternary systems, because we can define Mendeleev numbers at various pressures, because we have electronegativities and atomic radiuses at different pressure, so we can define Mendeleev numbers at different pressures. Okay, thank you very much for your attention. We'll be glad to hear your questions.
Thank you very much, Zahed, for a really well done presentation. There are several questions in the chat. What do people ask? Zahed, can you read the questions in the chat? Or should I read them for you?
I can read them. Okay.
The first question on the session was at 3:10, I suppose.
Yeah. How do you precisely define the desired properties of the material?
How do you precisely define the desired properties of the material? So desired properties for different properties, of course, is different. If we are talking about energy, the lowest the energy is, the more desirable it will be. And if it is hardness, the highest hardness is more desirable. So maximization and minimization of the energies, I would say.
Yeah, I would say that it depends on which problem you are solving. If somebody from industry comes to you and says, I want soft and light material or whatever, this is what you need to optimize, low density and low hardness. If they want to get light and hard or whatever, electrically conducting and whatever, non-magnetic or whatever magnetic material, then this would define which properties you optimize.
Okay, can you elaborate on the concept of bias? How precisely does human bias influence our view of Mendeleev numbers and by consequences crystal structure properties? Well, Mendeleev numbers are generated by people, and I believe that everyone believes that his own Mendeleev number can work better than others. And using the maps that I showed you, in some of those maps, you cannot say which one is better. So you need to, I don't know, have some tool. You cannot just look at the maps and say, okay, this is better or this is better. Probably if I want to look at the maps and say which one is better, I will probably say mine if the maps are very similar. But basically, using naked eye, you cannot say. Your mind will affect it. That's why we need to have an evaluation tool.
Yeah, so in the way that you evaluated, there is no human bias. It's based on rigorous metrics.
Yeah. So third question, sorry for my English question. The graph of the hardness distribution using the atomic number of the element looks more crowded to the area of the most solid compounds than the hardness calculated using your method. On the other hand, your method had more pronounced pattern for other properties of materials. How can this result be explained? What might not have been taken into account? For hardness, our maps actually gives much better map. If we look at it, I showed the map. I can maybe go back to that slide and show it. But for example, here, one can see that, for example, this is atomic number, and you can see a periodic pattern hard systems, super hard systems are here, 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 here. And here for periodic number and Petitverse-Mendeleev number, they are not really condensed in some region, and they are spread in a bigger region, and still it's much better as an atomic number, but ours is totally different. I would say for hardness, not only I say, but the results of our evaluation to say the same thing, that our map gives much better results, because you can see all these super hard materials are here, and these are also similar to them and close to them, but the color is different, and all of these colors are again in neighboring places. All of these colors are in neighboring places, and you can almost see that all the materials are clusters in 1/4 of the chemical space. Okay, if I answered the questions. But I would suggest that maybe we cannot have an ideal Mendeleev number that works the best for every property. If we don't have it, we don't have such things now. Okay, can you please explain what is mutation and atom? Okay, mutation, if you mean in Mendeleevian search, mutation means that we have a parent here. Parent is a material which has the best properties or some of the best properties. That's why it was chosen as a parent. So this material, if it is a binary system, it has 2 elements. And by mutation, we take one of the elements of this parent and mutate it to another element, and also for the second element. And by mutating on this space of electronegativity and atomic radius, we try to find with some possibility another element which is close to this element, because as I mentioned in my talk, in this space, materials with similar properties are close to each other, are sitting nearby. That's the reason that it is more possible that a close element to the parent element to be chosen as a child of that parent. So mutating is changing the elements of the parent like this. Can machine learning be used to map out the properties instead of Mendeleev mapping? I don't understand this question very well. So machine learning to be, you mean instead of Mendeleev number, we develop some machine learning model that finds such Mendeleev number, maybe? If that is a question, maybe I think, I don't know, maybe it can work like that. I don't know. Okay. Having really good a small query for Moxney and system when multi-objective algorithm is applied, one phase was missed out in the convex hull compared to the single algorithm. Does that mean if we run algorithm again, do we get the same result? Okay, as I explained, there is no guarantee in evolutionary algorithm. If you want a good guarantee, you need to continue for longer number of generations or repeat the calculations. What I missed to tell is that the work which was done in 2016 using single objective optimization was done during 60 generations, while we did during 30 generations. So if we have got longer, maybe we could get that material too. But basically, I mentioned, yeah, maybe if you repeat the calculation, you will get it, or if you go for longer, more number of generations, you will get all the structures, but nothing is guaranteed, even with single objective. So can I go to the next one?
Yes.
Okay. Sorry for being not very precise in the question in advance. One of the aims was formulated as to predict materials which are likely to obtain experimentally. Could you please provide some more explanation to this part? Example, is there any chance to understand which experimental method should one choose to obtain predicted materials? Or this was about stability of the predicted phase? Many thanks in advance. The question is a little bit general, but okay. We are trying to optimize the properties for different properties. I already mentioned we are minimizing or maximizing, and or Pareto front tries to make a balance between this minimization and maximization of the properties. But at the end, we are trying to get to the materials which have the best properties. For example, if we are talking about energy, we would like to get materials with the lowest energy, because it is reasonable and practically experimental findings should be correspondent to, or better say, these low energy materials should be corresponded to experimental results. So that's why we are looking for them. And many of these results which we can find can be synthesized experimentally. So at the moment, maybe experiment doesn't know them, and they look at our results and try to synthesize them. This happens quite oftenly, frequently. So I don't know I don't know if that gives your answer or not, but we are trying to get confirmation from experiments. Do you have an approximate release date of Mendelian search code? Well, I don't know, actually.
Yeah, we haven't decided yet.
Yeah, we haven't decided yet. Okay, is it possible to predict materials having highest dielectric constant in a ternary system? It is possible. Yes. And thanks for the nice talk. Could you please elaborate a bit on the relation between electronegativity and crystal structure? Well, I'm not very expert in that. We maybe Artem can explain that, but okay, we use the Goldsmith law, which this is kind of law of crystal chemistry, and they state in their paper they fully explained why. But okay, I don't know much. I read that paper a long time ago. I just
yeah, electronegativities or first of all, electronegativity determines if the material is metallic or semiconducting or insulating. For example, if you look at the elements with high electronegativity, they are insulators. Elements with low electronegativity, they are metals. For metals, interactions are non-directional, and you tend to form close packings. For non-metals, you form other structures like diamond structure, graphite structure, molecular structures of nitrogen, oxygen, and halogens, and so on. If you go to compounds, then electronegativity difference determines if the material is significantly ionic or not. If the material is significantly ionic, then atoms with the same charge will try to avoid each other as much as possible. So this has a lot of consequences for the crystal structure. Type of chemical bonding. Electronegativity determines type of chemical bonding, and this, of course, affects crystal structure.
Okay. Does MENS implemented for searching only for hardness and magnetic materials, or also other properties? Any properties that you can calculate using USPECH is by default implemented in Mendelian search. So you can check the manual. How are the properties calculated, such as hardness, fracture toughness, etc.? Why cannot be the Stokes shift be calculated? For how these values are calculated, we have different methods. So initially, we calculated our hardness using Oganov-Lyakov model. You can look at the paper. It's based on the bonds between atoms and bonding energies. And because this is a good model, but it doesn't work for maybe all the materials. At the end, when we found those promising systems, we did the calculation of hardness for those systems using Vickers hardness using elastic models. And I think you know how that is calculated, or you can check the paper. Okay, it's finished. Thank you very much. Thank you everyone very much.
Thank you very much, Zahed. And I hope everyone was inspired by this talk. The next talk will be by another former student of mine, who is now head of laboratory at Moscow Institute of Physics and Technology, Ivan Kruglov. And Ivan will tell us about extension of USPECH for high temperatures. This was actually one of the questions which was asked to me today. Ivan's talk is the answer. Please start.
Good afternoon, everyone. Let me share my screen. I think you can see it, yeah?
Yes, perfect.
Oh, great. So thank you, Artyom, for introduction. Today I will tell you about novel USPEX method for crystal structure predictions at finite temperatures. And first, let's try to answer the question, what is materials design or crystal structure prediction? Let's say that we have a chemical formula like this one, and we want to predict its crystal structure at given conditions, different pressures. So there are a number of codes which can do it. And if we know crystal structures, stable crystal structures at these conditions, then we can build phase diagrams or calculate different properties. So we can find novel thermoelectric materials, superconductors, super hot materials, and so on. So during this talk, I will tell you about USPEX and about USPEX, extension of USPEX for finite temperatures. So first, I will show you some cases, some problems which we solved with USPEX for different systems like boron sulfide and uranium hydrides. Then I will show you extensions of USPEX with interatomic potentials and also machine learning potentials for molecular crystals and aluminum and uranium. And then as a combination of these two parts, USPEX and interatomic potential, how they can be implemented in the USPEX method for the calculation of finding novel structure and finite temperatures. So let's start with the first part, this one. So first about boron sulfide. There was an experiment at high pressures which found a novel boron sulfide structure at about 36 GPa here. Then it's XRD pattern. You can see it here, and there are new peaks which appeared at 36 GPa. So we were asked to find which structure appeared at these conditions. So we used USPEX to find which structure is stable at these conditions. So we found novel high pressure boron sulfide system, and this new structure is a bit different from the initial one. It's different in stacking of the layers. You see it here, that was ABA. So now it's in novel high pressure phase, it's AAA. So it's different stacking. And you see that this novel high pressure phase, it describes XRD pattern quite well. Only some peaks, small peaks are undescribed. And these peaks, they appeared even before the appearance of the new phase. So we believe that it's something else, not this phase. And also compared the latest parameters of the novel phase and calculated latest parameters and experimental ones. And you see here quite good agreement for A parameter and for C parameter. And this one was done with USPEX. So the next case, it's uranium hydrides. And previously it was known that for uranium hydrides, there are two stable compounds, stable phases. It's alpha phase and beta phase. They're shown here. And we tried to answer the questions, are there any other uranium hydrides at high pressures? So we did USPEX calculations at different pressures from 0 to 500 GPa at different pressures and built phase diagram. Here on the x-axis you can see pressure, and here it's ratio of hydrogen and uranium. So at 0 GPa, only UH3 is stable, as it was known from the experiment. But then we found a lot of new previously unknown phases like UH5, UH6, UH7, UH8, and so on and so forth, up to 500 GPa. Let's take a closer look on these structures. First, UH7. UH7, it's HCP structure, and where uranium forms HCP sublattice, and hydrogen, they form these substructures. It's cubes which are connected in one point and making infinite one-dimensional chains which go perpendicular to the screen here. If we delete one atom here, leave this one, delete the next one, and so on and so forth, we'll get another structure which is stable, U2H13. Also, we found UH8. It's a sodium chloride type structure. You see uranium atoms, they occupy sodium sites, and H8 cubes, they occupy chlorine sites. And this structure is stable at about 50 GPa. Next, we found UH5 and UH6. And if we will keep deleting atoms from this chain of H8 cubes, then we will get UH6, UH5. But if we will insert one hydrogen here, then we will get UH9 phase, which is also stable according to our calculations. It's shown here. Also, we found U2H17 structure, which is a derivative of cubic UH9. It's shown here. If we delete one atom connecting these cubes, then we will get U2H17. We also calculated superconducting properties, and these structures, according to our calculations, can be superconductors with not such high TCs in comparison with the system which Artem showed you before during his talk. But you can see the pressures here are really low, about 20 or 50 GPa. Next, our colleagues from Carnegie Institute, they synthesized uranium hydrides in diamond anvil cell, and they found UH5, UH7, UH8 or UH9, it's something in between them. And also after decompression, they found HPC UH5. Next, this year, there appeared one more work in PRB by the group of Paul Lubert from France. And they also synthesized UH7 and UH8, which confirmed our previous theoretical work. And you can see very good agreement between our calculated crystal structure and experimental XRD pattern here. This phase diagram, which I showed you for uranium, it was built at 0 Kelvin because all the calculations, they were done using a density function of air. And here comes the question, how can we do USPEX calculation at finite temperatures, and how can we cover this high temperatures, this space at high temperatures? There are a lot of high temperature phases at different materials, like for iron, you can see here high temperature phases, for titanium, for uranium, for tungsten borate system, for many systems, there are high temperature phases which may not be found in a usual USPEX calculation at 0 Kelvins. So we tried to make algorithm which can work at finite temperatures. What's the difference between calculations at finite temperature and at finite temperature and at 0 temperature? The main difference is how we calculate our fitness function. It's here. So previously we calculated potential energy or enthalpy if we calculated finite pressure. So now we have to calculate Gibbs free energy, which also takes into account entropy. So it's here. So now we have to calculate this term TS. As Artem told you, it's much more complicated calculations, and there are a number of methods which can do this, and you can see them here. The most exact one method is thermodynamic integration. Its advantage is that it includes unharmonic terms, it's mathematically exact, but disadvantage that it requires big systems of more than 1,000 of atoms. And this is why it requires interatomic potentials or machine learning, maybe machine learning interatomic potentials. There was a work in which authors compared different methods for calculating free energy. You can see it here, that's for aluminum and for molybdenum. And this line, it's free energy calculated with thermodynamic integration. And all these lines, there's a difference between free energies calculated using all these methods which I showed you before and thermodynamic integration. And you see that they show quite a good agreement at low temperatures, but then thermodynamic integration gives a bit different result from all other methods. So this is why we used thermodynamic integration as a method for free energy calculation. So now I will tell you a bit about interatomic potentials and also machine learning potential and how we use them and solved some problems for the search for molecular crystals and predicting properties of aluminum and phase diagram of uranium. So now we can split interatomic potential into classes. One class, it's classic interatomic potential. We use them for a long time. It's Lennard-Jones potential, it's Buckingham potential, maybe AM potential, or some other potentials. This potential, they have fixed form, known coefficients. They are fast. There is a database for, let's say, AM potential, but they work only for some specific problem. And if there is a new structure, new compound, we have to make new interatomic potential. This is why maybe about 5 or 6 years ago, there appeared first machine learning potential, and now there are a number of them, and you can see the comparison of the accuracy of different machine learning potential on this figure. And MTP potential developed by Alexander Shapiev, he will give his talk maybe tomorrow, I don't remember, or the day after tomorrow. And this potential developed by Alexander Shapiev and his colleagues, it showed the best accuracy at the lowest computational cost. This is why in our future works for TU specs, we used MTP potential. Now, let me show you our recent work with classic potential for molecular crystals of energetic materials. Energetic molecules, you can see them here. There are a number of them. It's HMX, TNT, Cl20, and so on. So our question was, can we use USPECs to predict structure of molecular crystals of these energetic molecules? And for that, we used USPECs and with classic potential, with reactive potential, ReactFF, implemented in the LAMMPS code. So we predicted molecular crystals of all these molecules, and you can see comparison of densities and energies predicted by USPECs and for the real structures. And you can see here that energies, they're all the same in experimental and predicted by USPECs. And also densities, they are the same. This means that the structures, they are really close or the same, calculated by USPECs and the real molecules. And one of them is shown here. It's TNT, I think, this one. And the next question was, can we use USPECs to predict structure of SAW crystals of different molecules? Let's say HMX and TATB, HMX and TNT, and so on. And yes, using classic potential, ReactFF and USPECs, we can predict structure of SAW crystals. And some of them are also shown here. And this was published in this work recently. One disadvantage was here that even if this potential ReactFF is fast, but still its accuracy is not as good as DFT accuracy. So this is one machine learning potential. Potentials have to be developed because their accuracy is higher. And let's speak a little bit about them. So first, what is machine learning? Let me give you a quick explanation of it. So let's imagine that we have a vector X with a number of properties. And Y, it's a property which we want to predict. And so the task of machine learning is to find the function which transforms X to Y, so which can find transformation from this space to that space, from our X to Y. In case of crystal structure, we have our X, that's our crystal structure of coordinates and lattice parameters, and our property Y, its energies and forces. So this is why task of machine learning interatomic potentials to find the function which transforms our crystal structure to energy or to forces. And then when we know this function for any new structure, we can quickly predict energies, forces, make run molecular dynamics, and so on. So here I show you one type of interatomic potential which we used. I don't want to stop in this mess, but you can see here that that's a form which we used. So that's a sum of exponents with 3 parameters which are cut and pk. And so we can take a number of different parameters and make different vectors x which describe our crystal structures. And using these interatomic potentials, first we calculated thermodynamic properties of aluminum. Here you can see the comparison of errors for predicting forces, interatomic forces in aluminum structures. And you can see that at 300 kelvins, our potential is here. It gives almost the same error as AM potential, but still lower errors than other published potentials. At high temperatures, our potential gave the lowest error. And using this machine learning interatomic potential, we calculated Von density of states. You can see it here. And black, it's experimental one, and red, it's calculated with our potential. Here's pretty good agreement. And we also calculated melting temperature for aluminum. And again, that's experimental value, and that's value from our potential. Again, good agreement. The next question was, can we calculate phase diagram of uranium, again, using machine learning interatomic potential, but at much higher temperatures and pressures. Previously, this phase diagram from experiment was known only up to 100 GPa and 5,000 kelvins. And it was known that at normal condition, alpha phase, it's shown here, is stable. At higher temperatures, BCC phase is stable. First, we studied the system using USPEX at 0 kelvins on this axis. We found that at 0 GPa, alpha uranium is stable, and then we found that at higher pressures, alpha uranium transforms to gamma prime uranium, which is shown here. It's BCT phase. Next, we used all these 3 phases and calculated their free energy and made interatomic potentials for them, and then calculated free energies. And here you can see errors at different densities and at different temperatures given by our potentials. And in average, error is lower than 10 millielectron volts per atom for different densities and different temperatures. So that's quite good accuracy for machine learning potential. Next, that's errors on forces. Again, that is our potential. It's AM potential, and these are other published potentials. And you can see that error, it's here for our potential, it's lower than given by any other potentials at 1,000 kelvins and 5,000 kelvins. So then we calculated free energy using thermodynamic integration. And you can see here this dotted line, it's from quasi-harmonic approximation. And these lines, that's with thermodynamic integration. You can see that here is a big influence of anharmonic terms for free energy of uranium. Next, you see that free energies of different phase of uranium, they're pretty close. So we subtracted free energies calculated from quasi-harmonic approximation from all these lines. And we got, for example, this line. So that is how we found transition lines from one phase to another. And you can see that at this density, alpha phase of uranium has the lowest energy up to 1,150 kelvins. Then it transforms to gamma prime uranium. And then at almost about 3000 kelvins, it transforms to gamma uranium. We did these calculations at different densities and built a phase diagram of uranium. It's shown here. You see here is region of stability of alpha phase, it's region of stability of gamma prime phase, and that's region of stability of gamma phase of uranium. And these black lines, that's experimental lines. And so here's a pretty good agreement between experiment and our calculations. Also, one good sign for us is that in cerium, for alpha prime phase, region of stability has this shape, dome-like shape, and it's the same for uranium. That's also good agreement between the different systems, but with the same structural type. Next, let's move to T-USPEX method. It combines USPEX and machine learning interatomic potentials, because here for uranium, we used previously known structures, and for them we calculated free energy. Now we have to find stable crystal structures at a given pressure and temperature, knowing only chemical composition. First, let's take a look at T-USPEX scheme. So if we'll combine everything which I said before, we'll get this one. So it's split it into parts. First, it's crystal structure prediction, and the second, it's free energy calculation. For the crystal structure prediction, we first relax our structure at 0 kelvins. Next, we run molecular dynamics at finite temperature. Then we calculate pressure corrections, because molecular dynamics is made with machine learning potential. And of course, it's not perfect, and we have to make corrections from DFT. And next, we run molecular dynamics at finite temperature with pressure corrections. And then for this structure, which we got here, we calculate free energy. So we calculate free energy using thermodynamic integration. And again, we make corrections from thermodynamic perturbation theory. And we take into account this correction and calculate final free energy. Let's take a look at how crystal structure can be transformed during this scheme. So first, you can see here it's random structure. Next, it's relaxed at 0 Kelvin. And next, that's molecular dynamics of this structure at finite temperature in about 60 atoms. Then we symmetrize the structure, and here you can see BCC phase. Then we make molecular dynamics for this structure with pressure corrections, and then again we have the same BCC phase, but only with a bit different lattice parameters. One more example, again, random structure simulated by USPEX, generated by USPEX. Then relaxation at 0K. Then we run molecular dynamics for this phase at finite temperature. Then symmetrize it. Again, nice structure, and the same structure with pressure corrections taken into account. First example, which we tried to solve using T-USPEX, it's aluminum. For aluminum, you can see two different phase diagrams from different works, and they show pretty much the same phase regions for different phases. This region where FCC phase of aluminum is stable, and it's stable at normal conditions. Next, it transforms to HCP phase, and then it transforms to BCC phase, and the same here. And we tried to first find which aluminum structures are stable at different conditions using T-USPEX, and then maybe build a phase diagram of aluminum with our method at finite temperatures. Here you can see the result of T-USPEX for aluminum at 0 GPa and 300 kelvins. And these are structures from first generation. So what can you see in this table? First column, it's space group. So you can see 2 to 5, 2 to 5, it's FCC. Then number of atoms, then it's energy from thermodynamic integration, free energy. Then it's two corrections from thermodynamic perturbation theory. Then it's PV term. Then it's energy of Einstein crystal. It's we need it for thermodynamic integration. And then free energy is a sum of all these terms. What is interesting that for aluminum, even one generation in T-USPEX is enough to get the final structure, which is stable at normal conditions. You can see that all randomly generated structures, they relax to FCC aluminum with 2 to 5 space group, and this structure is stable at normal conditions. The second that is free energies of all the structures, they have difference only in the force value after point. So again, it's accuracy of our method is pretty high. So it energy of all randomly generated structures which transform to FCC structure is the same, and it's shown here. So TU specs can find stable crystal structures for aluminum in this case, even in one generation. Why can it be so? Here is some schematic view of free or potential energy surface at lower temperatures and how may it look like at higher temperatures. And you can see that at low temperatures there could be a lot of local minima and global minima, of course. But then at higher temperatures the number of local minima reduce, and there are only one global minima and maybe a number of local minimas. This is why when we increase temperature, all our randomly generated structures, they go to deep local minima or global minima. And we saw it here for aluminum. Next, we did the same calculations at different temperatures and phase and pressures for aluminum. And you can see results here. So this letter, it means which structure is stable at which condition with TU specs. So here you can see FCC aluminum stable at 150 GPa and different temperatures. Then here HCP phase stable, here BCC phase stable. And according to this data, we plotted phase stability regions. They are a bit different from the ones calculated before, but they didn't take into account anharmonic terms. So this is why you can see that's the final phase diagram for aluminum which we got. So now TU specs can also be used for the building PT phase diagrams of different materials. So the next case is magnesium silicon oxide. There are two known high pressure phases. It's perovskite phase and post-perovskite phase. And it is known that perovskite phase transformed to perovskite post-perovskite phase at pressures higher than 100 GPa and high temperatures with this transition line. So we tried to calculate the same transition line from perovskite phase to post-perovskite phase. And for magnesium silicon oxide, there was a potential developed by Artem maybe more than 10 years ago. And so we used this potential and we used it in TU specs. So we did first two global searches at different conditions. And we found that yes, here perovskite phase is stable and here post-perovskite phase is stable. Then we found the transition line from perovskite to post-perovskite phase. And it's shown here with this line. And all other lines, that's calculation and experimental works from other groups. And you see that they lie in pretty much the same region. And our line is in good agreement with all the previous works. So this can be done using TU specs and with classic potential. So that's very fast. And we can find these transition lines from different phases. Next case is tungsten boron system. Here you can see experimental phase diagram of tungsten boron for different concentrations of boron atoms, so from tungsten to boron. And we studied one-to-one composition, so at 50%. And you see from this experimental phase diagrams that alpha tungsten boron system is stable in this region, and beta tungsten boron system is stable in temperatures higher than 2000 and about 500 kelvins, Celsius, sorry. And we did TU specs calculation at 0 GPa and 2000 kelvins, and you can see that we found 2 to 5 structure with 2 to 5 space group, which is stable. Then structures with 63 space group, 141 and 62. And alpha tungsten boron, it's this structure with 141st space group, and 63 is beta tungsten boron system. So TUSPEX method found alpha and beta tungsten borates, and then we used the structures and calculated phase transition line between them. So we did calculations at different temperatures for these phases, calculations of free energies. And then we found at which temperature one phase transforms to another one. And we also used this 60 seconds structure with 60 second space group. It's PNMA, tungsten boron system. And we found that alpha tungsten borate transforms to beta at about 2700 kelvins. So again, it's a pretty good agreement with previous experimental works. So this transition was almost in the same region. So first, TUSPEX found previously experimentally known tungsten boron systems, and it is able to calculate transition in temperature from one phase to another. So in general, now we can calculate the same phase diagrams only using TUSPEX. One more example, it's tungsten carbide. Again, here on the left, you can see its experimental phase diagram. In this region, alpha, or somewhere it's called delta phase of tungsten carbide is stable. It's hexagonal phase. And then at high temperatures, gamma or beta tungsten carbon system is stable. It's sodium chloride type FCC structure. And it's stable at about 3000 kelvins, or somewhere here, 2,000 or 3,000 kelvins. Then again, we did TUSPEX calculations at different conditions, and the results of at 0 GPa and 300 kelvins, you can see it here. In the first generation, you see there are a lot of different structures, but this one, 187 here and here, it has the structure has the lowest energy, minus 11.25 electron volts per atom. And this 187 structure, it's of course this phase. So TUSPEX in one generation at 0 GPa and 300 kelvins found the most stable tungsten carbide system. When we increased the temperature to 2000 kelvins, TUSPEX relaxed almost all the structures to FCC structure. And this is again experimentally known phase, this one. So in tungsten carbide, TUSPEX again predicted experimentally known phases. Next, the final case, yesterday I tried to calculate what's happening in uranium hydride UH8 using TUSPEX. I ran maybe about 10 structures in the first generation, and 2 of them relaxed to, again, previously known experimentally and theoretically phase with FCC space group, and it's shown here. So again, TUSPEX in one generation found a stable UH8 phase at 50 GPa and 300 kelvins. So now this method, it works for any system, any number of atomic types. It can be used in variable composition search. So it can work at any temperature and any pressure. So it can be used like an experiment where you choose point in pressure and temperature and predict which crystal structure is stable at these conditions. So in this work, we developed TUSPEX method. I showed you how it works and show you examples for the how phase diagrams can be calculated using these methods and transition lines from one phase to another one. So thank you.
Thank you very much, Ivan, for a great lecture. Any questions? Well, we actually have 2 questions in the chat. Do you want to read them yourself, or should I?
Yeah, I can read them, no problem. First question, how would you know many atoms about 62 DMD on the TUSPEX method? From Alexander Shapiev. First, yeah, we used, as I told, MTP potential developed by Alexander Shapiev in this work in order to predict stable structures at finite temperatures. So we used 60 atoms because we trained actively our MTP potential on the system. So if we train it actively on the fly, so the system size should be calculated in DFT for a reasonable time. So for the training of MTP potential, we used this system of about 60 atoms. And then when we trained potential, we calculated pressure corrections for this system, and we run dynamics in much larger system of about 1,000 atoms. So the next question, does TUSPEC work only in fixed composition mode? Is it possible to run variable composition in order to obtain entire PT phase diagram in one run? Yes, it can be run in variable composition. There are no problem. The only problem is that it's computationally expensive a bit. And for this case, a general type machine learning potential should be used. Now we work on it, how they can be done. How do you take the unharmonicity into account in the case of aluminum study? We used thermodynamic integration method, which by its definition, it takes into account unharmonic terms. So we use this method for the calculation of free energies, and this is how we took into account an unharmonicity there. Could you find temperature, the number of local minima reduced to somewhat lower values? How does computational time vary in these two 0K and finite K cases? Of course, the USPEX is more needs more computational resources than normal USPEX. We compared it. Maybe it takes. You saw that for aluminum we need, and for almost all systems, we need only one generation there. So we need maybe about 20 or 30 or 40 structures, no more. So TUSPEX is more computationally expensive, but not so much, maybe in 50 times, I would say. But it depends on how good would you like to train your potential, and how many structures would you like to take, and how many structures would you like to use for the calculation of free energy corrections. Usually finite T predictions are done as post-processing after 0 TUSPEX completed. Do you have any examples that TUSPEX gives a completely different answer than post-processing TUSPEX? That's as I know, post-processing for TUSPEX could be done using small displacement method in phonome. It was done, or using, as we did for uranium, using thermodynamic integration. But if we, let's say, take into account uranium and predict its crystal structure with simple USPEX at 0K, it will never find BCC structure because it's dynamically unstable at 0K. But if we take TUSPEX, it of course will find BCC uranium, and we checked it. So, for example, uranium system. Thank you for an informative talk. Is external package with TUSPEX is LAMPS in your calculation or any other? Yes, we use LAMPS for the for molecular dynamics and free energy calculation. This question I answered.
Did you use LAMPS? Oh, yes, you did.
Yeah, LAMPS. And did you test on covalent system with covalent bonds, binary system or more?
Yes. Tungsten boride.
Yeah, and also we tested on what we tested on carbon. We tested it. It works well. So on any system we tested it, it worked well. What can I say? What is the cost of TUSPEX method? As I told you, it may be to about maybe 50 times more computationally expensive, but it depends on how many free energy corrections and pressure corrections can be used there. So now how we do it, we first run a calculation with a small number of corrections, then we get stable structures, and then with a much higher accuracy, we calculate the free energies and find the transition point from one structure to another one at temperature, as we did for tungsten boron system.
Yeah, I would like to say that if you want to find the temperatures, then you need to sample many states that the system visits, and this would be thousands of states. And to explore these states, you would normally need to have a large supercell. So we're talking about an increase of computational complexity by 4 or 5 or so orders of magnitude. Doing it by DFT at the acceptable level of accuracy is totally unrealistic. Using various computational tricks, we were able to decrease the complexity from, let's say, 100,000 times of normal USPEC calculation to only 50 times normal USPEC calculation. That's a big speed up, but it is still quite expensive. It cannot be done cheaply, it cannot be done routinely. It's not something that you will do every day for all kinds of problems. It has to be done for really problems where you have to do it.
Yes, I agree with that. I can also add that if we know a good interatomic potential for a given system, as we had for magnesium silicon oxide, then this calculation is very fast. It's much faster than usual USPECs because no DFT calculations can be done for it.
Mm-hmm.
Again, about system size of the supercell, 60 atoms. We use 60 atoms because we trained interatomic potential on this system, machine learning potential. And we trained first, before that, we trained it actively with MTP potential. So we sampled structures from molecular dynamics, calculated their energy forces, stresses in DFT, and trained potential on these structures, and so on and so forth. So this is why we took system which could be calculated well for reasonable time in DFT.
Also, 60 atoms is a right system size for calculating free energies. If you do free energy calculations using thermodynamic integration for very small systems, then you do not capture at all long wavelength phonons, and these are very crucial for free energies. So your supercell has to be sufficiently large. Starting from about 60 atoms, it becomes sufficiently reasonably accurate.
Yeah, and for integration, we sometimes use even much bigger systems because at this moment we have interatomic potential, so we can use much bigger systems for about thousands of atoms to get much more accurate values.
Mm-hmm. There is another question. Does TUSPEC calculate the enthalpy completely from LIP, or rather it's TS applied to DFT? Neither of the two. It calculates free energy at the same level of accuracy as DFT, but it uses machine learning potential as an intermediate step for thermodynamic integration. So it's full DFT accuracy free energy. And when you see the phase diagrams of Ivan, it actually is done at the DFT level of accuracy.
Yeah, and I can show you maybe again this table, this one. And you can see that free energies after thermodynamic integration for different aluminum structures, they're different in maybe 10 or 20 millitron volts per atom. But final values of free energy with corrections taken into account, they're almost the same for all FCC aluminum structures.
Mm-hmm. Okay, other questions? If not, let us thank today's second session speakers, Zahed and Ivan. I think the talks were really well done. Thank you.
Okay, thank you.
And now we have a break, right? Do we have a break? And after that we have a practical session, installation party, which will be led by Zahed. Okay, so the program is okay. So for lecture programs, we are done for today. There will be lectures tomorrow, And at 4:45, just in a few minutes, we start the tutorial. For the tutorial, let me make an important announcement. Well, we had more than 250 people registering for the workshop. It actually is the record size of a workshop for us. And I like it that so many people can participate. It's really wonderful. But we cannot provide 200 or even 100 people with accounts on our cluster. So what we will do, we have given some selected participants, selected on the basis of their experience in this field. We have given them access to our cluster. The number of such accounts is 65. These people will be able to run calculations in real time. All other people are invited to attend the practical session without actually accessing the computer, but having the opportunity to observe how these calculations are done, having the opportunity to ask questions and discuss anything they want. So in a few minutes, please, let's start the practical session. Second question, a second issue I want to raise with you is this. It's very important that people using our code, like any code, in fact, read the manual and read the manual carefully. Everything related to input files, output files, all these technicalities, everything has to be understood. Many questions that you may have, many uncertainties will be resolved after reading the manual. So I invite everyone attending this workshop to register for the code on the website if you have not done it yet. Download the code and study the manual and prepare your questions. You can ask them throughout this workshop. You can ask them in the chat, in the discussion rooms. By the way, if you want to discuss anything with any of the speakers, you can ask the organizers to organize a separate discussion room. And there you can have a private discussion between the people you want. Okay, that's all. I suggest that we have a 5-minute break, and in 5 minutes we reconvene for the practical session.
Okay, shall we start?
Yes, please. I think it's time to start.
So, do you see my screen?
Yes.
Okay, unfortunately, I cannot start my video for the problem which I mentioned earlier. Okay, guys, I think we can be more interactive in tutorial sessions. You don't need to be silent and invisible like in lectures. So if you want to turn on your video, you can do it. If you want to ask questions during the tutorial session, you can do it. But because we have more than 100 participants now, I suggest people who has question raise hands first and make short questions so every people can ask questions. And I will try to answer them time to time.
Sorry, there is a real problem with microphones, so we don't really hear you well. So could you maybe adjust some?
Okay, wait a minute.
Yes, either maybe lower the level of your microphone or lower the voice. I don't know.
Is it better or worse?
The same.
Is it better or worse now?
This is much worse.
Much worse. Okay.
Now we can't hear anything.
What about now? Now? Okay, I hope we can solve this. Is it good now?
No. It's doable, but well, it's not really good.
Oh, okay, I got it. I think it's good now.
Yeah, now it's much better.
Okay.
Thanks a lot.
Okay, thank you for telling me.
You can do it a little higher, I think.
Okay, is it good?
Yeah, perfect.
Okay, so let's start. And Vova.
Yes.
During the workshop, I think, can you handle the people who wants to ask questions? I mean, those who raise hands, because I don't see actually where people can raise hands, and I can see them.
You can click participants, and I will also look at the list of participants if anyone.
Okay. Okay. So among you, there are people who have already used the Spur. There are people who are maybe used the Spur for a long time and know many things, and people who are beginners and wants to know how to use Spur and what aspects does. So basically, in this tutorial, in the first session, I'm going to show you how to install Spur, and then I will show you how to change files for submitting jobs for remote and local submissions. So many of you may have problem there too. So, okay, so if you think you know how to use Spur, you can, I don't know, stay a little bit away or enjoy some tea and come back when we are showing the submission job part. Okay, so first of all, you need to register on the Spur website and download the Spur. So if you see my screen, I have already registered, so I just need to log in, and here in the download page, click Spur 10.4 and download it. So I have already downloaded, I don't need to download, and I will show you how to install it. People who have account in Oleg can do it according to the manual I showed there. I will explain now. People who are going to install Spur on their own machine can do it for just following our lead, and people who have Mac or Windows and so on cannot install Uspech because this version is only for Unix. So for Windows, we don't have it. For Mac, at the moment, we didn't compile it, so we don't have it. Okay. So let's start. I will try to install it on Oleg, just as you, so we can go all together. I will also look at the manual to make sure. Okay. So you can first make some directory, whatever, for installing Uspech. I called it soft, and you can, if you're in Alec, you can copy the source of Uspech installation file from this directory which I mentioned in the handout, and copy it in, I don't know, any folder that you want to start an installation. I copied this file in my soft folder.
Zahed, sorry to interrupt you. There is a question from the chat. People ask you to precise which account are you talking about. So there are two kinds of accounts, one on the in the USPECs and one in the supercomputer. But not everyone was given the account on the supercomputer.
Okay, look, at first, when I told you that you can download it, it was your account on the website. But right now, I'm generally talking for everyone, but those who have account on the supercomputer, they can copy the spec file from this directory, specs workshop and specs version 10.4 to their own home and then try to install it. But those who don't have account on the supercomputer, they need to...
Zahed, I'm terribly sorry to interrupt you again, but can you please try to adjust the mic again? Because it was better for some time, but then it just got worse again. So the sound is really distorted. Yeah.
Okay.
Yeah, now it's much better.
I need to manually handle it in my Linux.
Yeah, because
you see it goes up.
Yeah. And can you somehow turn this auto adjustment off?
Okay. So please copy Uspech in your home directory or in soft. I copied it in soft, and you need to untar it using tar xzxvf in the name of the file. And wait for Uspech to be untarred. Okay. I will wait a bit so everyone do it. Okay. So let's go to the folder Uspech underline v10.4. Here you need to see these 5 files. I will make it a little bit bigger. In the README file, you have some. In the README file, you have some notes that you must read it before installing Uspech, because all the prerequisites that you need for Uspech and some information about Uspech installation and Uspech itself is written there.
Zahed, I'm sorry. First of all, we can barely hear you. can you try the Zoom volume settings? It's the first. And secondly, there are some comments. People say you go too fast. Could you please repeat the steps?
I'll go faster. I have a question. Alisa, Elibova.
Uh-huh.
Is it possible for me to connect to Zoom by my phone and my laptop, so I show my screen by laptop and talk by phone?
Let me find this out. So simultaneous the Zoom and phone. I think you can do that. Well, let's try.
By Zoom from 2 devices.
Yeah, phone and laptop. Yes, try. Let's try this.
Zahet, can you hear me now? Zahet?
Much better. What?
Okay, I think everyone hears me well now.
Zahet? Do you hear me now?
I'll wait a bit, please. Yes, I hear. Yes, I hear you.
Zahet, so this auto adjustment of the volume is in the Zoom settings.
It's fine. I'm talking now good by phone.
Okay.
Okay, so let's continue. So what you need to do is just to try to install Uzbek using /install.sh, and you will see probably in your version it will show 10.3, but it's 10.4. We change it later. If there is some inconsistency. So there are 3 options. The first option is graphical installation. I will show it a little bit later on my laptop. The second one is terminal installation that we will do it now. I'm installing it on our supercomputer. You can do it too, but please, since Uzbek is already installed on the supercomputer, all of those users that are installing Uzbek on the supercomputer, after finishing the installation and making sure that they learned and everything works, please remove all those installation, because we are not going to occupy, I don't know, gigabytes, a lot of gigabytes for all users for the installation of Uzbek, because Uzbek is already installed for all of you. You just need to load it. I will tell you later about that. Okay, so we go to terminal installation number 2. And then this is the license for Uzbek code. If you are agree, you can just write yes or Y. And then you need to agree with MCR license, MATLAB runtime compiler. You can enter or you can press Q. By pressing Q, you will go to the end of the license. And then again, you write yes or Y. And then you need to enter the path for installation. You can enter any path. Aspects will generate that folder and we'll install it there. I will install it in the same folder as I mentioned in the tutorial handout. Okay. Soft specs 18.4. I will install it in the same directory as I have the source and files of the spec, and just wait until it's finished installation. Terminal installation is so easy. It's basically finished, and all of the environment for bashrc will be automatically added to your bashrc files or other similar files if Uspech can recognize your system. If not, it will show you the environmental variables that you need to add to your bashrc. So you just need to, Uspech will show them to you, and you just need to copy them and paste them in the file that you need to paste. Boba,
Yes.
does everyone have the tutorials hands up?
Not yet. I am now uploading it.
Okay. Okay, takes a little bit longer than I thought, but it's fine. I think it's because everybody at the same time are installing it. On my laptop, it takes like 20 seconds, 30 seconds maximum. Right now, if anybody has a question, he can ask. Okay. I get this error. There is insufficient memory for Java runtime environment to continue. How do I resolve it? Mac NLT. Are you installing in Alec in our supercomputer in your PC? You can answer by voice. You don't need to write.
Yes, I'm actually trying both at the moment. The other one is waiting, but the one that would be in my home computer, or rather my home supercomputer,
Okay. So,
it's giving me that error.
okay, and probably something is not installed. I don't know actually. Oh, we can look at it on the internet later. I haven't seen this error before. Okay, what else? Does this version works on Mac? No, it doesn't work. I told you. We generally think that Uspech is basically is useful for supercomputers mostly, and that's why we made for Linux only. But we will make Uspech version for Mac, and we'll release it too. Probably many people like to run Uspech on their Mac book, so we will do it. Unzip. Not found, error, download process failed. You don't need to unzip. What are you writing and you get this error? You need to use tar, not zip, not unzip. Tar zxvf, name of the file. Loading share libraries, cannot open shared objects. No such file. Again, from Gigi, if I'm spelling correctly. Okay, can you tell me where are you installing Uspech? You can say, please.
Hello. Yeah.
Hello?
I install it in my university computer. So I saw it shows the USPX install successfully, but when I input USPX -h, it will not work. And I just input ./USPX, so it
Okay,
shows.
wait. So this error is after successful installation of USPEC or before installation?
Oh, after USPX is installed successfully. Yes.
Okay. Okay. So it's a bit soon to go to there, but I assume you didn't specify the bash RC correctly. Probably USPEC didn't write it automatically on your bash RC. Please check it, because USPEC needs to understand where the MCR is installed.
MCR.
Okay. Yeah, MCR is MATLAB runtime compiler. Yeah, okay, let me explain something which I missed. In this version and previous version of USPEC, you don't need to have MATLAB on your computer. It's MATLAB free. You don't need to have license for it, and it's basically easier. That's the reason that the size of USPEC has increased kind of dramatically to about 800 megabytes. Before it was like 200 megabytes. But it's good because you don't need to download 10 gigabytes MATLAB. So you just need to install everything from USPEC. USPEC already has a package of MATLAB runtime compiler. It is included in the package of USPEC, and you can just install it without having any MATLAB. You can run USPEC. And it is good for us too, because we can keep our codes safer. Not from you, from some other people. Okay.
Excuse me, but as a matter of fact, in my university computer, it might have, it has MATLAB. It has the right version MATLAB.
It doesn't matter. We don't need MATLAB. You have it or you don't have it. We don't use it. If you specify in your bash RC the correct path for MATLAB runtime compiler, MCR, USPEC will give you, when you install USPEC, USPEC will give all you need to add to your bash RC if it's not added automatically by USPEC. First, please check your bash RC, and then we can talk about that again, because maybe you can find the problem. Okay, after the installation has hung up. Okay, I think little by little people will install it. Mine is finished, you can see. How to installation could be done if we use our own supercomputer accounts. It's just the same, nothing different. Do we get right that we do not need to install it if we are granted supercomputer account from Upshot? You can install it on your own machine if you want to learn it, of course. And if you know, and if you have a user on the Alex supercomputer, in our supercomputer, and you have already installed it in your machine or previous time, and you know how to install it, you don't need to install it, because at the end you need to remove it. Okay, got this yesterday, installing on May 20. Okay, you have the same problem as the people, the Gigi, I think, mentioned before. And there is some problem with your with understanding of the directory that your MCR library is installed. You need to fix that. Okay, until Dennis, I wrote. I will go on a little bit and I will answer again. So you can see that USPEC is installed successfully, and it will show you this message, which you can see here. All of you need to get this. We can say 2 successful. One here for MCR and one here for USPEC. And if I check my bash RC, I think you know what is bash RC. Please mute your microphone. You can see that USPEC added, yes, here, added automatically anything that your system needs to know about the location of USPEC and MCR. So MCR root is a keyword for MATLAB runtime compiler directory, which is installed here for me. And then this is the path for installation of USPEC. And again, path for installation of USPEC source. So these three will be added automatically if USPEC can recognize your system. If cannot recognize, after showing probably before or after showing this USPEC is installed successfully, we'll show you these 3 lines, and we'll tell you to add it to a file similar to bashrc that you need to add for your system. Okay, so I installed in this path here. I can do aspects minus h, and you see everything works. And aspects minus v gives me, okay, this is because I have already installed USPEC before. I need to remove that from my bashrc so I can get the right version. Okay, so USPEC minus USPEC version 10.4 is installed for me without any problem. So it works now. And I don't need to test it anymore because aspects minus h is just like a test. And after installation, there are 4 additional folders. This app data application here, uninstall, and v91. v91 is the place that all the files for MATLAB runtime compiler is stored, is installed. So if we go there, there are anything about MATLAB runtime compiler, it's not related to us. If you remove it, if you don't know where is installed, you will face those problems. You cannot run USPEC. And the code of USPEC is installed in application and then in archive. So in the archive, we have examples, we have everything, but you don't need them. I just showed. You don't need any of them because you can, for example, see examples here using USPEC minus E. You can, I don't know, copy them, for example, C12. Okay, these are for later. People will tell you in the next tutorials. But basically, this is USPEC help, and it is installed just successfully without any problem. From people in the who installed USPEC in the supercomputer, is there anyone that couldn't install it? You can say by voice, please, if there is anyone.
Hi. I know that in principle there are a couple of persons who didn't succeed. So is it possible to use some USPEC from any user account? I mean, pre-installed, just on your cluster.
Yes, of course. Look, this in a please. Some people mute the microphone. This installation just to understand how to install it. And then everybody needs to remove their installation and use the USPEC which is already installed for all users on the supercomputer. So there will be no problem for running USPEC later. I just asked if somebody still didn't finish or we need to wait or something like that. But basically it was very easy. So I will also, okay, let me remove it.
As I said, there are also a couple of questions in the chat.
Okay, let me see. Okay, there are thousands of questions. Where I stopped? Denise, it was Denise, I cannot find it. Yeah. Okay, is it possible? Okay, I will start from the end, unfortunately. Okay, no, it's not fair. Wait. Okay, do we get right that we do not need to install it if we are granted supercomputer account? Yes, you don't need to install it. If you install it, you need to remove it. I ask you to install it to understand how to install it. That's the reason. For those who don't know. Got this yesterday and so am I loading. Okay. Dennis, I understand. Okay. Dennis, I'm not sure because it's like it doesn't work. Doesn't work where in okay. I will tell you how to people guys. Uzbek is already installed in our supercomputer. So those people who are in the supercomputer, later, please all remove the files and I will tell you how to use Uzbek. You need to load the module of Uzbek. I will tell you. Okay. Question, if I have previous versions on my computer, is there a way to update it to 10.4 or is it easier to just remove it and install again? It is better to remove and install again. Is it enough to remove it? And bash RC. If you have 10.3 installed before, if you are running some calculations, please finish your calculation and then install 10.4. If you are not running, I suggest you remove 10.3 from the folder that it is installed and from your bash RC and install 10.4. It is mandatory to have MATLAB. We don't need MATLAB. If you have it, we don't use it. Is it possible to run Uzbek in a laptop? Yes, it is possible. I mean, I do not have access to a supercomputer, so isn't Sanders. Okay, look, Albuquerque. I hope I. Okay, Marcelo, it's better. Marcelo, generally, Uzbek calculations are huge, especially it depends on your ab initio calculations. If you're running Uzbek with WASP or I don't know, some heavy codes, I never suggest to run it on your laptop. But if you're running Gulp, I did it a few times. It's not dangerous, but still I would suggest to do on your supercomputers, but Gulp is very easy. Okay, I get the message installation failed. Okay, Alexandra, where did you get this message? On our supercomputer, on your computer, or and at which step? Please say it. Yes, yes. Please turn on your microphone and say it. Okay, I don't hear you. I will go to the next question. You can tell me a bit later when you can. Okay, for downloading Uzbek, you need to go to the website of Uzbek, uzbek-team.org, and then you go to the, here I go again, home, and then Uzbek, and then if you have not registered, you need to go to download page, and then here click the registration. Where is the registration? Here. If you like the yeah, I already registered. That's what entered. Okay, I will go out. Okay. You need to go to download, register, and then when you register, it will give you account, and then using account you need to log in, and then when you log in, there is a download page which you can download it. Okay. Quick question. When I enter,
I think Alexandra can speak now.
Oh.
Okay.
So I tried to install. First, I got the error message, but later it's installed successfully.
Okay. Okay.
And works. Thank you.
Okay. If to Henry Powell, if you get version 10.3 by aspects -v, it means that in your bash RC you have the environmental of older version. If you already before, I mean, installed Uzbek 10.3 and remove it, you need to again, you need to also remove the bash RC environment for USPEC 10.3. Otherwise, it may show you that it depends on the order of these things. Please check your bash RC. Is that correct? No, it's not correct. I mean, you need to see 10.4, and the date should be in 2020. How to install MCR? I just showed it. I mean, everything I did was installation of both USPEC and MCR. Specs error while loading. Okay, again, the same error as before. Installed in my PC. Is it okay to run it on it? Installed in my PC. Yeah, it's okay. For people who wants to run USPEC on their own computer, if it is a laptop, you need to have ab initio code installed on your laptop. It might be Gulp, it might be Quantum Spare, so it might be VASP or whatever. Except for Gulp, I don't suggest you to run it on your laptop because those ab initio calculations are expensive. But you can run USPEC with Gulp. That we have a lot of examples with Gulp, just for you to understand how to work with USPEC. Okay. You need not change once. Okay. Export. Home key test USPEC.
Guys, here's a small announcement. I created a page for the tutorial materials on our website, on the website of the conference, not the USPEC's website. So USPEC School 2020.skoltech.ru.
Mm-hmm. Okay. Kiki, this is your bash RC. I don't know if it is correct or not. It seems to me correct, but it depends. Is it really the place that it is installed or not? After having this bash RC, you need to refresh your terminal by writing bash or closing and opening a new terminal. And let's see, again, you will face that problem or not. If you face the problem, please remove all you installed and reinstall it, maybe from bash RC and from your directories. Try closing and opening the terminal. Okay, owner, it is going. Will finish successfully. There was available. The tutorial file is available. It's not possible to upgrade from one version to another version. You need to remove the old one and install the new one. Can we use? Yes, I will tell you about USPEC, which is installed already. Okay, how about staying there? I will tell this one too. How to set if I use CH instead of bash. USPEC will give it to you, I think. USPEC for TCH also will give you the environment that you need to push in your bash RC or similar file. Okay. I will right now, I think we don't have, we are out of time actually. I wanted to show you also how to install it graphically. I will show just, you don't need to install it. You cannot install it on our supercomputer. On your laptop, you can install it. I will just do it very quick on my own laptop, and then you can see. And then we will go to the job submission session. Okay. So for installing USPEC graphically, you need to go to the place that you have the source of USPEC. I put it in USPEC workshop, and then you need to untar it. And then, just like before, you will have the folder with the same name. So here is the folder for USPEC, and you will have these 5 files. So far, everything is the same. So install.sh, and here you need to use 1 instead of 2. And then you need to, yes. And then the first license was for USPEC. So you agreed. It will try to open the installation graphically for you, and you need to install it. It's very easy actually. So next, you need to just write where do you want to install it. I will choose the same folder on Specs Workshop here. Okay, this is the place for installation of MATLAB runtime compiler, I think. No, that was for USPEC. Here is the place for installation of MATLAB runtime compiler. I already have it, but I will install it again in the same place. Okay. And then just next, you need to agree with MATLAB runtime compiler license. And then you need to keep in mind the directories that USPEC will give you. So these the advantage of terminal installation is that it's much easier and you don't need to set up your bash RC. It will be set up by USPEC automatically. But in graphical mode, you need to set up bash RC manually. So for that, you need to have these directories in mind. And then it will install it. So after installation was finished, Aspects will tell you that you need to add these lines in your bash RC. So you need to open your bash RC, and I already have it. I will not add it. I will just show you. And add these few export lines. Yes. Okay, please note MCR is the pass before the folder V91. So I need to check in Specs Workshop. There is V91. So this is the place for Specs bash RC. So I need to install it here, write it here, and then plus pass, and then for installation pass of Spec, again you need to write it here, and then installation pass of Spec, you need to write it here. So everything is done. This is what you need to do manually if you install Spec graphically, and then finish. So okay, I will not save it. So it was just quick installation show of the second method, but terminal one is much easier. So let's go to our supercomputer and remove, please mute your microphone if you don't have a question. And remove everything because we don't need them. You can remove everything. I suggest removing using RM-RF Spec. B10.4. You can remove everything actually. Okay, until it removes, I will answer a few questions. Okay, existing with the stage 2 on the schedule. Okay. Oh, for Gulp, I don't know. I mean, you need to register in their website, and probably you need to have affiliation. But if not, ask someone to download it for you. Yeah, it's free, but you need to register, I think, using email from universities. Okay, it takes a bit longer because, again, I think we are all removing at the same time. I don't know. Okay, I will show you in another page. Okay, for using the USPEC, which is installed in the supercomputer, you need to write module load specs 10.4. Okay, sorry, specs 10.4. Okay, it has some dependencies. You need to first load Python 3, and then specs 10.4. So please have this in mind. Okay. This was the thing. When you push tab, it will show it to you automatically. And I will send it to the chats. Wait. Where is the chat? Okay. And then you can run USPEC. You see USPEC. Okay. Okay, I forgot to remove my bash RC. Please don't forget to hello, please mute your microphone.
Sorry, have you copied this command to the chat? I don't see it. I mean, this model.
I send it to the chat. You can see it in the chat.
No, I don't. Probably you sent it privately to someone.
Really? Okay, let me try again. Okay. This is okay. Yes, we have it now. Okay, people, after removing USPEC, please also remove those lines which are added by USPEC to your bash RC, those users that are using our supercomputer. And then use this. Please mute your microphone. And then use this line which I sent you to load USPEC, which is already installed in our supercomputer. You see, we can have everything. Okay. And when I write my NSV, okay, I don't know why it doesn't get me. That's strange. Okay, I can try something. Yeah, it's specs minus R. Okay, I need to go out and come again. If you faced such problem as mine, please log out and log in again. And then module load specs module load Python 3 specs specs 10.4. Okay, now we have specs minus dash works and version works. Okay, everything works. So, okay, I will, please, let's make a folder. Let's call it workshop. And then go to this folder. And let's just, I don't know, make one example of USPEC. I just want to show you how to change the submission files. Using specs minus C, it means copy one of the examples. Which examples? We have 34 examples. You can see the description of each example using the numbers. I mean, this is description of all examples. You can see them all here. Let's copy something just randomly. Let's make it 4, for example. So I will have here, okay, I don't want this because it's with lamps, but okay, it doesn't matter. You will have the examples at your directory. And then there is a submission folder. In the submission folder, there are 4 Python submissions that you need to change for submitting jobs in your own machine. These jobs are working now for this supercomputer, but if you want to run your calculations on your supercomputer, you need to change these files. There are 2 types of submissions, local submissions and remote submissions. I think in the tutorial session, people may say about that. For local submission, the place that you are submitting job is the same as the nodes that are running jobs. Okay, there is a, in the input file, let me go back. In the input file, we have one keyword, which is which cluster. Which cluster, you can read the manual, can take 3 different numbers, 0, 1, and 2. 0 means no submitting files. Basically is used for running USPEC on your laptop or head nodes of the supercomputer. I mean, in the place that you are running on the same place. 1 is for submitting jobs locally. It means you are on the supercomputer. You're running USPEC probably in some node or in the head node, and but submitting jobs in other nodes. So you're locally submitting jobs. So no, we are locally submitting jobs. And 2 is for remote submission. It means you are not in the supercomputer. You are sitting on your laptop and you are submitting jobs on the supercomputer. You are running USPEC in your laptop, but submitting jobs on the supercomputer. This is for remote submissions. And for option 1 and 2, I mean local submission and remote submission, you need to change these submission files. You need to go to submission folder and then change a few things according to your machine. So let's start with local submission. For local submissions, there are 2 files for submitting jobs and for checking if the job is done or not. First for submitting jobs. The file name is submit job _local.py. So when you open the file, it's an open source Python file. You can freely change it for your supercomputer. So the first important part is that you need to here write the job script that you use for submitting jobs in your supercomputer. So you need to write it. And here you will define, I don't know, everything related to your supercomputer. And then there is a command executable that means how to run the ab initio codes, for example, quantum espresso or wasp or whatever. You need to define this in input file and not here. And then another important thing is what is the system of your supercomputer? It's SPATCH, Q sub, B sub. and what is it? You need to write it here. How do you submit jobs? Maybe you submit jobs using dispatch, the job file, or you submit job using qsub, the job file, the name of the job file, and so on. You need to change this according to your supercomputer. Here we use dispatch. And then again, this job number, it works for this supercomputer. You need to check it on your supercomputer. Maybe the output is different from you. I mean, this job number is actually, this line gives you the job number. When you submit a job, you will get a job number using this. So you need to just edit it in a way that you get the job number here for your supercomputer. I think it works for most of the supercomputers. And then here you don't have to do anything. So basically you just need to define the job file of your machine. You need to define command executable in the input file. You will see it later. And you need to define how to submit jobs. And if this doesn't work, you need to change it too. Okay, and then after submitting jobs, you see, for example, we have a lot of jobs submitted. These are job numbers. These are running. This means running. Some of them are pending, still are not running, and some of them are finished. Okay. When a job finishes, Aspects will check it. If it is finished, it will read the results. So in this file, check a status local pi, Aspects will go to check the results of your calculation. So basically here we have a few things that needs to be changed. One is, how do you specify, how do you understand if the job is finished or not? For example, sq minus j and number of one of these jobs. For example, I choose this one. You see, it's not finished, it is running. But if I change it to something from myself, okay, invalid number. I think I need one more. Okay, let's do it. Okay, it says basically it's not. Okay, it cannot find it. It means it's finished. But I don't know why it says like this. I think like this. Yeah, it cannot find it, so it's finished. Okay, status local. So in this place, I think you can use this for a spash, for qsub. I think you need to write q. Those people who know, they can write for people who don't know, because many of you have similar systems. For qsub, I don't know, bsub or other things. Yeah, qstat. Yeah, great. qstat and number of jobs will be given here by Usper, so it will check. Actually, here we can check it with qstat too, because we have also qstat on this machine. So if I write it like this, you will see that this job is running. And if I change to something which is not exist, it will tell me nothing. So what is env? Well, I don't know, but env, I'm talking about env. I don't know, it is for environment, but I tried. If you don't specify it, it works too. I don't know. Okay, and then, so here in the first step, Aspects will check to understand if the job is done or not. You need to here write qstat or sq minus j number of job or whatever. If it is not finished, the output will be something like what I showed you here, something like this. So, and if it is finished, you will get nothing in the output. And then in the second step, Aspects will go to check if it is running, if it is pending, or if it is finished. So if it is not finished, at the end you will get running or pending in the output. You see here is running, for example, R, and for some jobs it is pending, like this. If your supercomputer gives different output, you need to define different keywords and not R and PD. You need to change in that case. And when Aspects understand that the job is finished, it will just make done to Uspech, and Uspech will go to the corresponding folder and read energies and whatever. And if it is not finished, it will for now go to the other jobs, discard this reading this calculation, and in the next round it will again come to check if this is finished or not. So I think everything here, I told everything here. I think we are out of time, so I would like to answer your question in a chat, but I will give the microphone maybe to Alexander because we are already out of time. And about the remote submission, maybe we can do it a bit later, especially if there are some people who need it. Okay, so let's finish for now. Vova?
Okay, so maybe it's now time to hand over to Sasha.
Yeah, I stopped because we have the second workshop, and I will answer those questions relating to my session in the chat.
Sasha, are you ready to start?
Yes, I'm here. I think I'm ready. Yeah. So does everybody download the file hands-on tutorial from my part?
Yes, it's available on the workshop website on the page workshop materials. I will write the address again.
I've just shared the link
Okay.
in the chat.
How can I share my screen and see chat? Okay, I found you. Okay. So do you hear my terminal screen? Do you see? Do you see my terminal screen?
Yeah.
Okay, so I think we can start. As most of you who have access to our cluster already find out how to load Uspech using the modules, you can do it like this. Python and Uspech 10.4, right? And then you can check whether it's that version which you need. So I have it because I already on the cluster. Then let's try some examples. As the head already showed you, if you will type uspech -e, you will get the list of examples. By the way, do you need me to turn on the camera? Or it's fine. Okay. That's fine. So we have many different examples. So it's 34, and actually we will stop today at the simplest example, which we can run right now and look at the results. And I decided to try example number 4. So it's here. So please create a directory where you can put the files. So I have my own. It called example 0.4. So just type uspex -c 4. And after that, yes, after that you will see this file, input.txt, reference folder, and that's it. If you, okay, question, is it reasonable to run this example on laptop? If you have LAMPS or Gulp installed on your laptop, you can try it. Is it okay? You can run this example with Gulp or LAMPS on laptop, it's fine. Okay, then why not? Do you have B driver? You mean this or this? I don't know. Actually, I think it doesn't really matter. It should be 10.4 and the date should be November 4th. That's it, I think. Yeah, so we will slightly modify this example, as you can read from the tutorial file, because here on the cluster we haven't got lamps for everybody. We have Gulp. So it would be a good practice to look at the input and slightly modify. Now, please write 1 or 0 if you have previously used USPECH or not. Yes, this built-in example has lamps. Okay, I think that's enough. So most of them haven't used USPECH previously. Cannot find the examples. So please write x -e. There is list of examples, and then -c4. After that, you will find the message that all the files copied in the directory, and then you can find the input file, a sh file, a reference folder, and some other file. So, as most of you haven't used USPECH previously, so let's go into the input.txt file to look what's going on there and what does each line mean. So type vi input.txt, or you can use another text editor if you like. So this is the main input file which we use to run USPECH. So let's go line by line. So first line is devoted to calculation method. Yeah. One thing, if you need to look, if you need to find what keyword means, you can go to manual and read lots of information about each keyword, which you will find here in the input, just in case. So calculation method, here we use USPECH because in our software we also have method VCNB, which usually uses for prediction of phase transition pathways. So it's like an extended version of NEB, which used for molecule calculations. We also have calculation method meta, which is devoted to metadynamics. And that's it. So here we need to specify USPECH because we perform this type of calculations. Then second line is calculation type. So here you can see that we have three numbers, 300, and each number devoted to each type of system. For example, first number is devoted to dimensionality of the system. If 0, it means 0 dimension, it's clusters. If 1, yes, it's 1D systems, polymers, I guess. 2 is 2D system, 3 is 3D system. So here our example is prediction of bulk carbon, the structure of bulk carbon, so it should be 3D. Then second number is devoted to molecularity of the system. If it's 0, it means that it's not molecular crystal, it's atomic crystal. If 1, it means that we will predict molecular crystal. And the last number is devoted to variable composition or fixed composition mode. So fixed composition when we restrict it to a specific composition and search for crystal structure within it. And variable composition when we vary the composition. In the case of a unary system where we have only carbon, we cannot do variable composition. Yeah, okay. Yes, so here we use 300. It means that we will predict bulk atomic crystal of a fixed composition. Then third line is out of rack. So I will tell about this keyword later when we investigate all the input file. Then there is a block called optype. So this also you can find in the manual that there are many different types of optimization and they define as a number. So number 1 is energy. So this is property which we optimize. In most cases, we optimize energy. We also can optimize volume, density, hardness, band gap, some thermoelectric properties, dielectric constants, elastic constants, whatever. And all these properties can be specified here. For example, here we specify only the energy, but if we'd like to specify, for example, to optimize simultaneously two properties, we can write something like here. For example, in this case, USPECH will generate structures and optimize two properties, 1 and 3. So actually, what does property number 3? You can easily find it in the manual. Let me just remind. Yes, so number 3 is hardness. Yes, you also can specify volume, some border, band gap, so there are something like 10 or something different properties which we can optimize simultaneously. But we need, in this example, we need only energy. Then the block atom type, which means what atomic types will be used in our search. So in this case, it's C, carbon, or you can even write it, carbon, whatever, or you can write down the number, atomic number, as you wish. If we have several types of atoms in our case, we can write it directly here, and so on. It depends on our system, how many atoms do we have there. Next block is num_species, which is devoted to the number of species. In our cases, it's number of atoms in our system. In our example, it's 16. So this is the maximum. Yes, this is the number of atoms in our considered unit cell, which we try to predict. In the case of variable composition, I will tell about this block later on the next example, which will be, I think, tomorrow. Then there is an important block which devoted to population sizes. So as you know, the basic scheme of our algorithm is started from the generation of initial population of structures, which are produced randomly by using random symmetry operators or random topology operators. And we need to specify how many individual structures do we need to create at the first and in the consequent steps. So the keyword initial pop size means exactly how structures do we need to generate at the first step, at the initial step. Population size is how many structures should we generate on the second, third, fourth, and other step. Num generations means how many generations shall be calculated. It's you can specify here like a big number, because if, for example, 50 generations, if Uspech doesn't stop before 50 generations, it will stop after 50 generations. But usually, if you will specify here something like 500, Uspech will stop faster, because probably it will find the solution of your problem within maybe several tens of generations. So this is like a stop criteria. Yes, in the case if you have some problem which cannot be solved within your input parameters. Stop crit is related to criteria where the Uspech should stop. In the case of fixed composition search, it's number of generations where the same structure is found to be the best. If some structure is the best until 20 generations, Uspech will stop and decided that it found the global minimum, and this is your crystal structure. Reopt old. This means that during the structure relaxation, so each structure which is generated by Uspech at each population then will relax using different codes. In our case, it will be gulp, and this keyword means whether we need to re-relax structure which we found as the best in previous generation now or not. So is it possible to specify the mass of the elements in the case? I'd like to use an isotope. Directly here, you don't need to do this, because this input file used to generate structures, and the masses of the atoms or isotopes, they usually used in the calculation of energy. In this case, you need to specify masses or define the masses directly in the input file of your code, gulp, wasp, whatever. So you don't need to do it here. Yeah, then there is a big block, variation operators. It defines the fraction of difference operators that will be used during the search, that will mutate your structures. For example, frag_gen means how the percentage of heredity operator that will be used during the search. So this is 50% of all variation operators is heredity. Then 30% of all operators is random symmetry operator. 20% is a soft mutation operator that will be applied for your structures to produce new generation. Yes, you raise your hand.
Yeah, I just unmuted to that. About this variation operators, then do we choose them based on some a priori knowledge, or are there any rules for that?
As far as I understand, There is some, in the example, there are some default values, and also in the spec there are default values which are quite well works with almost all jobs, almost all tasks, but you need to test this stuff prior the calculations. It's something that you need to test. But in manual, you can find some default values which usually works fine. Yeah, so this part is really important, and you need to try to understand how it works, read manual, maybe perform some tests in order to understand what will happen if you will change this percentage. For example, if you will reduce number of heredity and all other operators except of random, you will obtain a random structure search when it will try to find structure producing only random structures. If you like, you can play with it. What's next? Next block is ab initio code. This exactly defines the type of your code which you'd like to run for relaxation. So number 4 is for lamps. So as this is example for lamps, but we will not use lamps, we will try to use gulp. Here we need to change number 4 to 3. Yes. Why we need to use several steps of relaxation? Usually, yes, well, thanks. I forget about the after frag keywords. Yes, this one. That these keywords means that, right, due to process of the search, these after frag options try to adjust all the percentages of variation operators to some more or less good scheme. So it can change the fraction of different operators due to the search in order to obtain a more efficient way how to produce structures for consequent generations. Yes. So at the first step, you define this manually, and at the consequent step, spec changes these numbers. So the question, we installed runs only if rectop rand is set in input, otherwise yes, I think maybe the head can tell, but the new version, actually I don't know, new version can do the topological random, right? And do we need really to specify this keyword in the input file? I guess no. This point should be clarified with the head, I guess. So what's next? Here we use 4 steps of relaxation. Usually if we use VASP or other structures, we use in each step of relaxation, we try to increase accuracy, because when some structure generated, probably it will not very efficient way to relax it with a really high accuracy. We just need to estimate the energy, try to relax it with with a low accuracy, and then after that we symmetrize the structure and again perform the second step of relaxation with a high accuracy, and so on and so forth. So the last step of relaxation should be very accurate. And in another case, it's useful if we try to calculate some property of material, for example, thermoelectric properties, which cannot be done within one code. For example, we can firstly relax structure with gulp, then we can use wasp, and at the final step we can use something like bolt trap to calculate thermoelectric properties. So in this case we can use several codes simultaneously in one run just to obtain the properties which we like. But in our case we use 4 steps of gulp. Is it possible to run USPEC structure prediction with vacancies or defects within the system? I think no, it's not this case. Okay, I missed one question. Can this USPEC method be used as an alternative to semi-grand canonical Monte Carlo ensemble to find the concentration of impurity elements in bulk materials? I'm not sure that I'm able to answer this question. It's really need to think about. Yes, I cannot answer right now to this question because I have thought that probably we can do something somehow this, but not directly yet. Yes, and then, as Zahid told, we need to define command executable here. In this case, it was lamps. Yeah, and there was also some question: is there any reason to choose gulp over lamps? There are no reasons to do this. The only reason is that we haven't got lamps for all the users. That's the only point. So I can use only lamps in my account, but you can't. So that will be not a good idea. Then let's change here. Gulp. So what's next? Okay, I think it's okay. I didn't put it in my tutorial. Let me look at the my examples which I have just to. That should be gulp. You just need to change this line to this in order to run gulp. Then, as gulp is quite computationally cheap, we need to use the number of parallel calculations as 1, and just as an example, we can use which cluster 0. Which cluster 0 means that you will run gulp directly at the same compute node where you run USPEC, and USPEC will run gulp during his work. So, okay, you will understand when we will run. I think that's it about the input file, about this input file. What's next? Next, in order to calculate, to run USPEC with gulp, we need to load gulp modules. Module load gulp. And then we need to go to specific folder. What is specific folder? Specific folder contains all the input files for your code which needs you to perform the calculations. In our case, in our example, which is specified for lamps, we have 5 input files for lamps and the Tersov potential. For our case, we don't need this. We just need to remove everything from here and create input files for Gulp, as you can find in the my tutorial manual, which you have downloaded. So we just need to create 2 files, ginput, one, where we need to specify the number of the name for our interatomic potential. We'll use here Brenner potential and maximum number of cycles in for calculations. Basically, I think we may not do this, but still, let's specify it just in case. And also, we need to specify another file option. By the way, all these files for Gulp you can find in the other examples which we have for Gulp. If you don't like to create files by yourself, here we need to specify some keywords for Gulp. By the way, how many people in the audience knows how to work with Gulp? Okay, thank you, I understand. Great. So if you know and understand how to work with Gulp, then you understand what we are writing here. If not, you can just create the files and write what we need, and then maybe tomorrow evening or at the nearest time, try to look at the manual of Gulp, or maybe ask somebody who is working with Gulp in order to understand. So if briefly saying, we specify here the keywords which we'll use for calculations. So where to take these files? The information, the data which we write in the files, they are written in the tutorial manual for this part. So this only a few lines which needs to be written. I can copy them into some shared folder. Let's do this. So I already have example. Let me copy specific folder to TMP for tutorial 1. And you can take this folder specific, you can copy this specific folder into your directory with this example. And it should look like this. You will have here 4 input files with the name ginput and 4 files with the name goption. So if you already did this, by the way, have you did this? Okay, if so, you can also find in this directory, you can copy from there file called gulp.sh. Please also copy it into your folder, not into the specific folder, but in that folder where the input txt locates. Submission folder will be copied from the uspech folder when you will run uspech. So right now you don't need to create them manually. Can you please share the files for different codes? Okay, I think we can. So I just will share these files which we run here. Yeah. So have you copied the run uspech.galt.sh into your directory? If no, please do it. If yes, then we can go. So now you have here in your directory, you should have input.txt, run uspech galt.sh, and specific folder. Yes, it should. In the question, does the number of input files correspond to the number of relaxation settings in input.txt? Yes, it should. It should be less or equal to the number of relaxation settings in input.txt. But usually they should be the same. For example, if we have 4 input files in the specific directory, and then we can specify in the input.txt only one number. In that case, the only input files with the number 1 will be used. Other files will be avoided. Yeah, by the way, in order to do our calculation faster, we can change the number of relaxation sets to 1, just one letter 3. Because all our relaxation steps are the same, so the keywords for gulp are similar, so it will be the same relaxation. And I have already tested this example with the one relaxation step. It works really fine and fast. Do we need the postcard files? In this case, we don't need them. Yes, I think we don't need them at all, because these postcard files create during the uspech works. Because I have already run this example, that's why I have them. I can remove them if I like. That's it. Okay, now let's move to the run uspech gulp sh file. And then you can see the configuration for job to be submitted in our cluster. So we will use one node, we will use one core. You can specify here the name. Here we load our modulus. We also need to, I think, load. Okay, thank you for the question. So let's, I will answer this question when we all will run the uspech. And you can check whether you did the same as we did right now. Yes. So for this case, we can comment these 2 lines. That's it. Just comment these 2 lines, and then we can run our calculations. By the way, everything what I'm doing here, it's written in our in the paper version of this tutorial. If you miss something, you can look at that. So, and then we can submit our job as batch, run, and yes. And in order to show you how this process goes, I will run this uspech directly here. In the head node, please don't do this. You need to write as batch run uspech.gal.sh. I will just show how the uspech works and what it tells you. Okay, the question from Lucas: how the number of atoms for each element can be decided? Compound may have different number of chemical formulas. If one wants to, for example, predict values of engraved atom size, it should be used to account for possible. Yeah, that's a good question. So actually, the details of this search I will show in the variable composition tutorial, which will be tomorrow. And indeed, we can specify the borders of the number of the total number of atoms in the unit cell. We can specify the minimum number and the maximum number. And the search will be performed within these borders. So I will run uspech like this, just to show you what it will tell you. So here you can see that these messages, it gives you information about using which space group the initial structures were created. So here you can see 17 structures were created with the random space groups, while other structures were created with different topologies. Then we've got this message, structure 1, step 1, calculates at calc-fold 1. Relaxation is done. Then structure 2, structure 3, structure 4, and so on. Coming back to question from Ashley Williams, you have message structure 1 calc-fold 1 bin bash input, no such file directory. Have you specified the command executable correctly? Because there you need to write command for gulp. You can answer. You can say the answer if you can.
Yeah, I thought that I did it. It's just gulp and then caret and then input and then the other way caret and output.
Yeah. So you need to specify this line in the command executable, right?
Yeah, that's what I put in my input file.
Yes. So you still have this error, right?
Yeah.
Okay. So yeah. So let's wait a little bit. I will show what the uspech did here right now, what it is doing right now, and then we'll come back to your question. So you can find here that we specify the input, the initial number of population, the number of structures is 30. So we finish the structure number 30, and after that, the status of the calculation is local optimization finished. So we perform the relaxation of all structures from the first generation, and then we generate another structures with different variation operators. So it's heredity, 12 structures with heredity, then with a random space group and random topologies. And yes, and then the second step of relaxation, then the relaxation of the crystal structures from the second generations started right now. Example. So have you run Uspech on a cluster on your own laptop? Vova, are you here?
Yes, I am.
Can you ask the head about this?
The head is not here.
I don't know.
No, I can see him.
The head, are you here?
I'll write him.
Okay, so I can stop the calculations. Still working is pen. Okay, I see what you mean. Let's say you have each of the generated structures running on different node. You always need to keep one node for the run of the script. You will generate a new session and submit this. Right. Is there any space for not to occupy? Actually, you are not occupying full node for this. You occupy one core of the node because the Uspech requires only one core for the calculations and other resources occupied by the calculations of each structure. So you don't need to occupy the full node for this purpose. Okay. For those who have problems, if you have not yet file appears in your folder or you have error file, it means that something wrong with your calculations. Maybe something wrong with your gulp or lamps, whatever. Okay, the error from Philip. Yes, I think this probably something with your lamps. Yeah, because there are actually which type of Linux do you have?
So this is a. Can you hear me?
Yeah.
So this is a Ubuntu shell for Windows.
Ubuntu shell for Windows.
Yep. So, but I have lamps installed, so I don't know. But
yeah, I know. Why I'm asking, because we faced some problem with the lamps coupled with the Uspechs on Ubuntu, and actually I don't remember right now how we solved it. Probably the reason is that you have so the reason of this error is the library, right? libstdc++.
Yeah.
And there is a conflict between libraries in your Ubuntu and in these libraries from the MATLAB runtime of Uspech.
Oh, I see.
Probably your lamps is linked with the Ubuntu library, and during the run of the Uspechs, it didn't see your environmental library and it tried to link to MATLAB library.
Okay, okay, thank you. So I'm gonna try with Gulp once you share the files.
Yeah, that would be better way. Yeah.
Okay, okay, thank you.
So what's next? We have IS badge before. No, that's fine. That's fine. That US badge. Because I show just by typing uspech -r just how the workflow of uspech goes, and you should run the calculation using the sbatch. That's correct. Command exec. So the question about from Hank Bean, right? Have you loaded the Gulp module?
I loaded.
Okay. Sure. Submission. And you specified which cluster 0 or 1 in the input.
Cluster.
Which cluster is the keywords in the end of the input file? This one.
Oh, 1. I should use 0.
I think for 1 it should also be working. Yeah, try to use
Okay.
0. And another question to you: have you specified in uspech gulp sh the module for gulp?
I loaded also modular gulp.
Okay. So yeah, I don't know what's the reason.
I will try and let you know.
On the cluster, I got many stashes failed. Yes, if you got such kind of messages, means that something wrong with your relaxation, something wrong with your gulp calculations. Then you will need to use one single core on the head node. If that's not allowed, that's happening now. Yes, the question is correct, and it is exactly what we are doing. We specify here, we create here the run file in order to submit uspech job on a compute node to occupy one core for this, and then uspech will submit another jobs for gulp plus whatever on your other compute nodes on the cluster. It's answer for Julio, I guess. Yeah. Okay, please type something if you have successfully run the uspechs and you found in your folder the results one folder without any errors. Run but not finished, but you can check the folder. Okay, for most of you the problem is solved. Is there any problem with WASP? Actually, we are always working with WASP, and we didn't find some kind of these types of errors. Maybe again the conflict of libraries, but I didn't face this problem. Okay, Alexandra, I got the folder, but the calculation still running. That's fine, because the calculations cannot be run within 10 minutes. It will take maybe 1 hour, but still you can wait until it will finish, or you can interrupt them by using the command as cancel and the ID of your job. If you check the queue, then you will get the ID and you can kill your job. Yes, so here in the folder, you will find results1 folder where you can find all necessary files which Uspech produce about your crystal structures. For example, let's start from the best individuals file and look at it. Oh. Okay, let me change the screen. How can I change the screen? Okay, I will stop the demonstration. Okay, did you see my blue screen? Results folder, best individuals. Oh. Best individuals. So what does this line mean? So in these files you will find the information about the best structures from each generation. So this is a number of generation. At the first generation, the best structure has ID number 20. Then it was produced by random topology. It has composition 16 atoms in the unit cell. It has enthalpy, this number. It has this volume, density. In our case, our fitness function is the enthalpy. And for Gal, we don't use the K points. It's for ab initio codes. And the symmetry of the structure is 8. And there is some parameters for structure order and some other features of the structures which you can read about in the manual. And if you look at the second generation, the best structure is number 61, which is kept best, means that it comes from the previous generation. So it's the same structure as this. Okay, chat. Yes. Yes, and we have here the same energy, and we can look the history of the structures, but in our case, all the structures are the fifth generation have the same enthalpy, but slightly different the symmetry. And all the structures that listed here in the best individual file, you can find from the best gathered postcards file. Here you have the postcards of each structure listed in the best individuals at exactly the same order. So you can just take the structures and do with them whatever you want as a post-processing. Also, you can look at these structures, at the postcard structures, for example, using Vesta software. Yeah, so let me show you. We have best gathered postcards. I will open them with Vesta. I think I need to change the screen. Can I somehow change the screen without interrupt the demonstration. So now I open the best gathered postcards with Vesta. If you are familiar with Vesta, you will understand what I'm doing here. So here we can find, this is the first structure. Then if you go into the objects, we can move through the postcards. This is first, second, third structure, fourth and fifth. And here you can see that this is structure of graphite. Yes, the stacking of the layers of graphite is a little bit difficult from the known one, but it's due to we have only 5 generation last, and due to the Brenner potential, which may not accurately describe this structure. So what we have next? We have there also some PDF files which you can open and find some statistics, some information about the convergence of your system. So we have here 4 types of relaxation, and you can find here that at the first step, this is the relative comparison of the energies of the calculated structures at different calculation steps, at different relaxation steps. So if basically if you have this straight line, it means that our calculations are well converged and we haven't got some points which are significantly different from step to step. This is the good sign of your calculations. So we also can find some other PDF files with the dependence of energy, how the energy changes with the number of structures. So here we have 160 structures, and we have that some of them have really low energy. So I have some problem with the install Gulp. Have you tried to install it on cluster on your own laptop? On your computer in the university, I understood. I see, but yeah, for answer for Mehmet, have you checked the input file for Gulp? Have you specified there correctly? Because this error means that something wrong with the calculation. Okay, so in the specific folder, you should have 4G input files and 4G option files, right? With yes, with this type of these lines. Yes, that's great. Then you have should have G options with keywords, optic, conjugate, and others as specified in the document, right? Then you need to, yes, correct. Then you need to specify in the input file in the block command executable this line. If this was done, means that this right. And you also need to specify in the run user gulp sh the modulus for gulp, and that's it. Yes. Okay, maybe it would be better if you can go to calc fold 1. Calc fold 1 and look at the output file and find what the error in the output file of the gulp. And do you have the input file which was created by Uspech? So who else has problems with gulp relaxations? So the same problem and with the same error, or you haven't got input files in the calc fold? Oh, both. That's interesting. Okay. Okay, let me try it. So you have exactly the same file as I have, right? Okay. Then I have G. That's interesting why structure is wrong. So, okay, I submit this job you can find here, right? Then let's look what's going on. This is the log file. So Uspech creates the structures. Yes. I see. I guess I understand what's going on. It should be not G option, it should be G options. It's G options. Yes, probably typo in the manual. And okay, let's try to do it one time. Yes, it should be the options, but it still doesn't work. And actually, I don't know why. Because yesterday it worked fine with all of these cases. Why we have okay. Why it doesn't work? Go. Let's try to do this. No. Ah. Okay, let me try one more thing. Yeah, if some of you have possible solution, maybe let's try. Maybe this should be empty line here. Okay, if you have the links from the option to the options, it works. Why it doesn't work for us? Because I think some problem with the gulp input file. It somehow merges the lines and doesn't understand the keywords.
Sasha, I have a question. You're running example number 4, right?
Yes, but modified for gulp.
Okay, but you didn't have the input file for gulp in the specific folder, so you took it from somewhere, right?
Yes.
And definitely the problem is with input file because people cannot run gulp. I mean, if anyone is expert in gulp, I'm not. They can probably
Okay.
check the input file, but using some input file randomly, of course, will cause problems.
Yes, I just put the input files from another examples of gulp, just change the potential. So now it works fine. The error was in the G input and G options, you need to have empty line after the keywords. Otherwise, gulp merge the lines and the input file is wrong.
Yes, there should be one blank line after it.
Yes, that's the point which we missed. But the question, yes. So try to insert there the blank line and restart the calculation, and it should goes in a good way.
I would suggest first go to one of the calc folders and try to run just manually one gulp example, trying to see if that works or not. And then change the specific in the specific folder.
Yeah, but for gulp example, you need the structure and the whole input file. Yeah, but still, this solution should work. Yeah, you need just a blank line, and the name should be G options and G input, and the blank line after the keywords. So please write who is working in this way and who have successful run of gulp. Okay, we have one successful run. Who else? Just yes, check your log. Whether in the log file you should have something like this. That structure, number, and the relaxation is done. Okay, if some of you copied this G input and G options from the TMP folder as written in the manual, then they should work because that files are correct. Okay, it seems that everything goes fine. Why you need kill your job? I think we have enough resources to calculations. I don't know why the jobs in a queue, because you occupy only one core. It should be fast. Okay, I have one generation finished, and second generation is calculating now. Yes, and in the results folder you will find all the information about the crystal structure, which then later you can use for some other advanced calculations if you need, for example, electronic properties or some others, just for further investigations. So do you have some question about these parts? I don't understand how it still copies to calc folder if you remove them. Because only those files which are located in the specific folder will be copied to the calc folder. Yeah, that looks strange. Okay, actually, the next step of this tutorial will be the calculation at some finite pressure, at external pressure, and the next example will be with WASP. Yeah, I just would like to ask, would you like to try it or not? So the answer to Dmitry about how can I check how far the code is from conversion during the calculation, you just need to look at the best individuals and find whether the last structure and how many structures, how many generations the USPEC get best structures are the same structures. For example, here we have the symmetry of the structure is 12, the energy the second is the same symmetry, the same energy, the same parameters, which means that structures of all these three generations, the best structures is the same. So, for example, if you have until 10 generations the same structure in the fixed composition, it means that probably you already found the best structure. Okay, if most of you would like to look at the WASP examples, so we have actually the same input file as for GALP as we used here, but you need to do some changes. Just to perform the calculation faster, okay, just create a new folder like I did, example for with WASP, and type there the same USPEC -C4. Then you will obtain all the input files from scratch, just not to mix GALP with WASP. Then you need go to input file. I changed here the number of species from 16 to 8 just to make the WASP calculation faster. Then all other parameters you don't need to change. Then, as you can find in the paper manual to our tutorial, then you can change the ab initio code to 1. Here we will have only the one step of relaxation, again, to do this example faster. Then you need to add this block, k-resolution start. As WASP is ab initio code, we need to define the key point mesh, and here we define it by specifying the resolution for key space net. So yes, and then we need to change the command executable to this API run wasp std log. And we need to add one more line, this one, with the keyword external pressure. Here we'd like to find something at the pressure, because previous example where we found graphite, it was at zero pressure. Now let's specify, for example, 10 GPa, the pressure here in gigapascals. So specify external pressure 10 GPa. Then you can also need to change which cluster to 1, because now you need to submit separate jobs for VASP calculations, not just running on the same node, on the same core as you running USPEC. And Vova, how many parallel calculations do we need to specify here? Do you remember?
I think 4 will be okay.
Okay, thank you. So 4, number of parallel calculations 4. It means that simultaneously 4 jobs with VASP will be submitted on a queue. 4 structures will be calculated simultaneously. Okay, do you have questions for these changes? About these changes? If yes, you can directly say.
Sorry, which example was that one?
Is the same example 4, but we slightly change input file.
Can I ask a question?
Yeah, sure.
My question is about the technical procedure that USPEC works, especially for the VASP. So if I understood correctly, so we submit USPEC itself as a job to the queue, so it will get some, let's say, one node with a few cores. Then it will submit separate VASP calculations, and until all the structures for the, let's say, first generations are computed, then it evaluates them, and based on that, it will generate the next generation, and so on and so forth. Am I correct?
Yes. Generally, you're correct, yeah.
And then what happens if, for instance, VASP calculations crash due to the wall time exceeding or any other errors? So can we restart the whole USPEC procedure, or what would be the case in that situation?
So in the case if it crashed due to the time limit, I think the energy for this structure would be taken from the output file as the from the last step, right? And that's it. And anyway, after the first relaxation step, we have usually 4 or 5 relaxation steps. So this also allow us to perform quite good relaxation without losing some information about the structure. But usually
may I add something?
Yeah, sure.
If you are talking about all of your VASP calculations, then you will face a problem, and of course you need to restart the SWIG and probably change your input files. But if you are talking about 1 or 2 jobs that are not finished or are not converged or just stopped by some error, which by VASP, then that structure will be discarded from USPEC. USPEC will discard that structure because it cannot read the energies and so on, and just will go to the next structure.
Okay, thank you. And then one very last question. Is it possible to sort of use another package to manage the calculations? To be more specific, for instance, someone would like to use Fireworks or AIDA to run VASP calculations and get the results without any error, and then tell USPEC to, okay, now these are these 100 energies, and based on that decide and generate the next generation of structures. and doing this loop until we get our desired crystal structure. Is it possible generally or no?
Generally, it's not possible, but if you want to do a lot of manual works, you can do it. You can make it possible. So for that, you need to go to each of the calc folders and do manual VASP calculation using your third software. And before that, of course, Uzbek needs to run that calculation, needs to submit that job, okay? But you need to stop that job and then run it using your cert program. And then when it finished, all the calc folders, when all of them got finished, you need to run Uzbek again to go and read energies from those calculations which you did.
Okay, thank you.
Okay.
So if we finished with the editing of input txt file, then we can move to specific. Yes, and in your specific folder, we will have a lamps file, so just clear everything and copy the files from TMP for tutorial 1, the in-car one, and postcard for carbon. Copy them to your specific folder. So there is a question, could you please explain later how the remote submission works? Okay. Yeah, probably it can be explained later, maybe on other tutorials. So have you copied the in-car and postcard to specific folder? Yes. Okay. Yes. Then also please copy the run uspech.wasp to your folder with the input txt and yeah, and run it like as a batch run uspech.wasp.sh. So if you run the script successfully, you will have the log file, which will look similar to those from GAL, but also you will obtain, okay, let me look here. No, this is not a log. So have you submitted jobs? Then you can check the queue and found that there are 4 jobs in your queue. The question to Giuseppe answer is no. Uspech use external codes like WASP or others for perform local optimization of each structure. So if you submit it and everything goes well, then you will obtain again the results folder with all the files with the information. If you will go into the best individuals file, you will find, for example, I had 10 generations. I ran this 2 days ago. I have 10 generations, and the best touch is the final line with the space group 227, which corresponds to F-43M. It should be cubic diamond structure. And then let's look at it. So here's the best structure from the first generation. It's obviously graphite. Then best structure from the second is also graphite. From the third, graphite. Fourth, graphite. Then something not graphitic. Yeah, they are the same. And this is, let's look at the supercell. Yes, and obviously we predict diamond structure. So at 0 GPa, the best structure was graphite. At high pressure of 10 GPa, the best structure is diamond, which is totally confirmed our nature. How long does it take after finishing the last optimization to run to the individual file? That's a good question. I think it's after when the first four structures were relaxed and the second set of four structures will be submitted. Between this, the data in the individual's file should be written. Am I correct?
I didn't get the question. Can you tell me what was the question?
So when the data about the structures appears in the individual file, it was step?
For individual files, you will get the results of each structure just immediately after the last step was finished. But you will get all the results except for fitness column. The fitness column will be available after the generation was finished.
Yes, and yeah, you have for calculation finished, but you have number of you have initial pop size 30, so you need 30 structures to be finished. After that, they will generate second generation. So to move from the first generation to second, USPEC should relax all the structures which specified in the population size. Yes, now you have no jobs because your VASP calculations are now finished, but here in the SBatch file you have a sleep command, which means that now your script is sleeping, and after 150 seconds it will resubmit himself just to run USPEC and proceed the data which it obtained from the first four calculations. Right. Alexander wrote the good comment. That was a typo because our script called run uspech.was.sh, and in the last line we have the name job.sh. That's why it cannot find this script. You need to change the name. It should be exactly the name of that script that you ran. So it should resubmit itself. Yeah. Thank you for this comment. It was a typo. Yeah. Yeah, probably all your jobs will be stopped with this error message. Please fix this line and resubmit them. So if everything will be fine, this calculation may go maybe several hours until you will obtain something reasonable. So I think if you have questions, please ask. If not, I guess we can finish our tutorial for today. Yeah, about in cars, I think we will discuss this with our colleagues and then let you know about it. Uh, I don't think that you need to cancel jobs. What do you think? Maybe let them calculate whole night and tomorrow they will look result. Okay, I think if everything fine, I will stop my presentation and okay, so thank you for participation in this tutorial. I will meet you tomorrow.
Okay. Thank you, Sasha.
Yeah, thank you. Okay, now I need to go, so see you everybody
See you
tomorrow.
all tomorrow. Yes.
Thank you very much.
Thank you. Bye bye.
Thank you.